Hi, Dr. Choi. Are you there?
Yes, I'm here.
Welcome. Do you want to test your, screen sharing, um, or you tested it before? Just want to make sure it's no problem.
Uh,
Hi, Dr. Choi. Are you
yes,
there?
yes, I'm here. Yes, I'm here.
Welcome. Do you want to test your, wow, screen? This is a very long echo. Before.
Let me see. What should I do? Actually, I'm not familiar with this, Zoom system. So, should
Under
I share my screen?
there is a on the bottom there is a green button should share screen, and I think you should click it first. And if you are using Mac, especially the new
I'm
OS,
sorry. Hold on. Actually, I'm hearing some crosstalk.
yeah, I too.
What should I do? Actually, I'm not familiar with this, Zoom system. So,
Under hello, hello, can you hear?
yes, I'm seeing that. Uh-huh.
So there is a on the bottom there is a green button, and you can try to share your screen over there. Did you see that?
Hello.
Hello, can you hear me?
Hello.
Hello, Dr. Troy. Can you hear me?
Hold on. Let me try.
Hi, Wang Hao. Can you hear me?
I can hear you.
Okay.
Okay, the Zoom is sharing.
Does it work?
Can you hear me? It works.
Yes, I can hear you.
Okay. But our delay is very long. But that's fine.
I can hear you. Okay, the Zoom.
Yeah, delay somehow is extremely long. Hello?
Yeah, I can hear you, but I think my words will take a long time to reach you.
Hello?
Do you want to, Dr. Troy, do you want to just rejoin this bridge?
Uh,
Because I think the delay between me and others are normal, but the delay between you and me are very long.
hello? Hello?
We can hear you, but
Can
somehow
you hear
the delay
me?
seems to be very, very long. Do you hear me?
Now I think I can hear you.
It's like seconds of delay, I think.
Right, right.
What's going on?
Uh, I think it's okay now, right?
So, Dr.
Okay.
Troy, can you hear me now?
Yeah, I think I can hear you.
Okay.
Okay. Sounds good.
Can you see my screen?
Yes,
Okay.
yes.
Okay, sounds good.
Okay, maybe let's just wait for 2 more minutes, and I will start to introduce you.
Okay, sure.
We can start the talk at 10.
Mm-hmm.
You, you 21. Let me see the YouTube. I see people are joining. Let's just wait one more minute.
Okay.
Okay, let's get started. Um, Hi everyone, welcome to the second day of APNet 20. And today we also have very exciting program. And first of all, we have great pleasure to have Dr. Choi to give us the second keynote speech at the beginning of this day. And let me briefly introduce Dr. Choi. Dr. Choi is the Senior Vice President and the Head of Advanced Communications Research Center at the Samsung Research. He was a professor at the Department of Electrical and Computer Engineering, Seoul National University, and served as the Vice Dean for Academic Affairs and the College of Engineering. He received his bachelor degree and master degree from electrical engineering from KAIST and the PhD at University of Michigan. And he's currently heading the researches and the standardization for 6G, B5G, and IoT connectivity at Samsung Research. And he co-authored over 250 technical papers and holds over 160 patents. He serves the academic communities such as ACM Mobicom and IEEE Infocom. And he was named IEEE Fellow in 2014. And today he will give us a very exciting talk talking about 5G and 6G in the future. And the title is Challenges on Next Generation Mobile Communications. So, Dr. Choi, please.
Okay, thank you. Thank you very much for your introduction. I'm very honored to give a keynote speech today at APNet 2020. As introduced, I'm currently heading Advanced Communications Research Center at Samsung Research. In this talk, I'll be sharing some of our thoughts about challenges and prospect of next generation mobile communications. So actually, in this talk, I will start with some of the current situations about 5G commercialization and challenges, and the usages of AI, ML technologies for network automation. And for the second half of my talk, I will talk about the next generation communication, so-called 6G, which we are preparing for 10 years down the road. So as all of you might know, 5G commercial service started last year, actually April last year, starting from Korea, the US, and so on. And actually 5G commercialization is getting wider and wider. So as of April this year, 75 operators across 40 regions and countries announced 5G commercial services. And out of them, 67 provides mobile service, while 25 provides fixed wireless access. Well, actually, it has been slightly over 1 year since the very first commercialization. And at this speed, we believe that 5G commercialization will be widespread at very high speed and very fast rate and so on. So if you take a look at 5G services which are provided by Korean operators, yeah, by the way, in Korea, there are 3 network operators. And given that 5G is one of the key features is providing higher data rate, actually, all 3 providers, network operators, started providing high-speed broadband services, including VR, AR, and cloud-based applications. Initially, more focusing on entertainment, such as cloud gaming, UHD, ultra high definition video streaming, and so on. And then it's kind of moving toward some wider applications involving AR and VR. So as you see in the screen, VR live performance and AR broadcasting of baseball games and so on, and also AR video calls. And these kind of applications are moving to wider applications, including education. So as you see on the right-hand side, we see some of, some of these, education using, VR and also book applications utilizing AR applications. Actually, given today's COVID-19 pandemic situation, I think the needs for online and virtual applications are kind of emerging even more highly. And we'll see that more and more AR, VR, cloud-based 5G content applications will be more widely used in the near future. So what's going on with traffic amount along with the emergence or introduction of 5G services? So according to SK Telecom, which is the largest operator in Korea, as of February this year, actually seems like due to or along with the introduction of 5G, the data usage or consumed by consumers or subscribers is increasing tremendously. So what we see on the left-hand side is, compared with LTE, with 5G, the data usage by subscribers actually doubled from 14.5 gigabytes per month to 28.5 gigabytes per month. And if you take a look at some particular usages by the subscribers, for VR and video streaming and gaming, we see that 7 times, 3.6 times, and 2.7 times more usages of the subscribers. While the VR and kind of online gamings are kind of niche applications, if you think about the fact that video streaming should be the major application utilizing 4G or 5G or internet and so on, the increase of video streaming by 3.6 times means actually a lot. So given that 5G provides a lot higher data rate, and also along with 5G introduction, many or actually all three operators, introduced unlimited data plan. I think subscribers are kind of using more data, by utilizing 5G data service. So let's take a look at 5G requirements and use cases, which people had in mind when they developed 5G. So different from the earlier generations, 5G was developed, to support. Hold on, yeah, to support different kinds of use cases, including eMBB and URLLC, MMTC. So eMBB represent enhanced mobile broadband, and it's supposed to provide ultra-fast data transfer to users. So for example, if you take a look at some of the numbers, using eMBB service, the peak data rate for user should be 20 gigabps, while user experience data rate should be 100 megabps. So by using this eMBB service, multiple heavy data, centric applications can be supported, such as HD or UHD video, AR, VR, and so on. The next use case is URLLC, meaning ultra reliable and low latency communications. And for URLLC, latency is very important. Of course, reliable communication is important as well. So in terms of the performance measure, the latency over the air link is supposed to be 1 millisecond. So using this kind of technology, a lot of new applications can be supported, including remote robot control and connected autonomous vehicle support and so on. The last one is MMTC, meaning massive machine type communications. So this is for massive IoT, Internet of Things, and so on. So in terms of the requirement, million devices per square meters should be supported. So this kind of use case can be found in smart cities, smart agriculture, which involves a lot of sensor devices and small devices, small things, and so on. So to support these three requirements, actually some of the new features were introduced as part of 5G technology. The first one could be network slicing. So if we take a look at this figure, starting from 2G, which supported only voice, and with 3G, voice and data were supported at the same time, where when I say data, it's based on packet switching based data service. And if you go to 4G LTE, where it was purely IP based, and even voice was supported using IP over LTE. But if you take a look at 5G, along with the introduction of network slicing, actually, as I mentioned, three different use cases like eMBB and URLLC and MMTC are supported at the using the same frame, but because their requirements are very different, in 5G, by making multiple network slices and by allocating a slice to a different service or use case, basically, multiple services can be supported as if multiple network technologies are used for different services, even if all three use cases are supported using the same or common 5G framework, but with using multiple network slices. So all these became possible thanks to the usage of SDN and network function virtualization. Another very important feature of 5G is the usage of new spectrum. So as you might know, beginning 1G, 2G, and so on, the carrier frequency went higher and higher. Because by using higher frequency carrier, we can enjoy wider bandwidth. And by using wider bandwidth, the transmission rate can increase accordingly. So what you see in here is in 5G, basically the spectrum can be divided into below 6 gigahertz or sub 6 gigahertz and above 6 gigahertz. So below 6 gigahertz, in many countries, 3.5 gigahertz bands are being used for 5G. So as you see, Europe, Korea, Japan, India, and China, all these countries or regions are considering utilizing spectrum around 3.5G and 4 gigahertz and so on. Another new spectrum is above 6G or 6 gigahertz. So as you see in here, in many countries, 28 gigahertz and around, and also 39 gigahertz and around are being considered. Especially, I think, in the US last year, April last year, US started 5G service utilizing this above 6 gigahertz spectrum, namely 28 gigahertz and 39 gigahertz and so on. Collectively, these above 6 gigahertz bands are often referred to as millimeter wave bands. Okay. Given all these new features and characteristics of 5G, what are the challenges in 5G? So earlier, I mentioned the usage of above 6 gigahertz, namely millimeter wave usage. Well, actually, I said that by utilizing higher frequency, we can enjoy higher or wider bandwidth. But that's the advantage. But the downside is the higher the carrier frequency, the shorter the transmission range for a given transmit power. So the end result is, compared with earlier generation, by utilizing higher frequency in 5G, because of the short range of the transmission, we ends up needing a lot more base stations to provide service at in a given area. So that means increased management complexity is kind of incurring. Another thing is, as I mentioned, we introduced new technologies such as network slicing. And by using network slicing, we can provide various services requiring various requirements. And thanks to that, we can provide, services for connected cars, smart factories, smart cities, and so on. But again, kind of managing multiple slicing can be another burden. And as I mentioned already, 5G supports, new use case called massive machine type communication. And that means, a lot more devices will be kind of connected in a given area. So what we see is a lot more base stations, a lot more devices, and also more complicated network management to support various types of requirements and services. So the end result is, with 5G, we can imagine a lot more complicated network management. So in here, we can definitely clearly imagine that the needs for network automation and the network, adaptation in a very scalable manner is very important. And in old days, all these were kind of supported by using some of, expert, system, by using, some of the rules, which learn based on our understanding of the system and which we kind of had in mind, in the design system, design phase and so on. But again, with 5G, we can imagine this kind of, very complicated system. And in here, the traditional rule-based, adaptation and automation is not good enough. And now many people and companies started using AI and machine learning technology for scalable network automation. So where can AI and machine learning be used? So actually, we can think of basically three pillars, namely planning, operation, and analytics. So for the planning phase, earlier I mentioned that, a lot of base stations should be deployed in the network to cover or to provide service to the users, and where to place base stations and how many base stations and what's the coverage, by utilizing a given set of base station. And if there are some coverage holes with the given set of base stations, all these questions are very important at the network planning phase. Especially, as I said, with millimeter wave, because the coverage is short. And also millimeter wave often, actually shows very directive transmission, characteristics, understanding or kind of predicting the coverage and the service quality before deploying the network is very important. For this purpose, actually, especially to predict, the RF, signal propagation, ray tracing was kind of traditionally used. But ray tracing is involving very high computation. So actually in here, AI ML can be utilized to reduce the kind of computation time for the prediction and so on. And so after deployment, the network will run over time. And during the runtime, the optimization of the performance is very important, especially along with network slicing. And basically, we need to orchestrate the network functions in a very proper manner. So basically, end-to-end network slice life cycle management is very important. And over the kind of course of the network running, we need a lot of optimization. In here, it shows that load balancing across multiple cells is kind of shown. So basically, based on the network operation, the observed network KPIs is kind of fed back to the network AI engine. And then AI engine kind of does a lot of prediction and forecast and so on. Based on that, actually load balancing parameters should be configured so that loads across multiple cells can be balanced properly. So that is one thing. And the other one is, over the network operation, basically in the background, network performance should be monitored properly. And then if there is any problem or KPI degradation, basically root cause analysis should be performed. and also the prediction or forecast for the future should be properly kind of managed too. So in this example, what's shown in here is if there is some throughput degradation in a given cell, there can be multiple kind of reasons. And what's shown in here is in certain cases, the IP throughput degradation could be due to heavy traffic load. And in certain cases, it could be due to poor downlink channel quality. And also sometimes it could be due to imbalanced load balancing across multiple cells. So anyway, the point is kind of monitoring and also based on that root cause analysis and prediction is very important. And then based on that during the runtime, kind of performance optimization by configuring or reconfiguring network parameters is very important. So actually what's happening is many industry entities and standard bodies are looking at using AI and ML technology for network automation. So this table shows three kind of functions which are being defined by some of standard bodies, namely 3GPP and Open RAN Alliance. So the first one is MDAS, which means Management Data Analytics Service. And the second one is MWDAF, Network Data Analytics Function. And the last one is ORAN RIC, Radio Intelligent Controller. So the first one, MDAS, is targeting data analytics at OAM management plane for network performance and fault management. So some of the use cases of MDAS includes per NF network function and NS network slice load analysis and RAN coverage configuration optimization and RAN resource and congestion analysis. The second one is MWDEF. This one is for data analytics at 3G core network control plane for network performance and service quality optimization. Some of the use cases include per NF NS load analysis and analysis and prediction of per UE application service quality and UE mobility and traffic pattern prediction and analysis. So both of these are being defined by 3GPP, which is the main standard body for 4G and 5G technology. Another entity is ORAN Alliance, which is defining open interfaces for RAN nodes, including RU, DU, CU, and so on. So as part of ORAN Alliance specification, this alliance is defining RIC, which is called RAN Intelligent Controller. This is for automation of control and configuration of nodes, including RU, DU, CU at RAN. So RAN means base station in 5G terminology for OPEX minimization. So the use cases of ORAN RIC includes traffic steering, QoS-based resource optimization, and RAN slice SLA assurance. So I will be briefly talk about some of the examples of intelligent RAN, which could utilize AI and ML technologies. So the first one is cell design. Earlier, I talked about cell planning, but in here, I'm talking about some of functions which is possible during the network runtime. So cell coverage can be adjusted or adapted over time, depending on the performance observed during the runtime. There is a concept of antenna tilting. So by changing the tilting of the antenna, basically the coverage of the cell and also the received power strength at cell within the cell can change. In old days, the tilting should have been done using the physical configuration. However, these days, e-tilting, electronic tilting is possible. So this kind of antenna tilting and transmit power optimization is possible during the runtime of the network. And this kind of optimization should be done based on UE locations, received power, and transmit power, and so on. So I think the example is really simple. So if the coverage, cell coverage is poor, so that means cell edge performance is bad. So in such a case, tilting angle should be upwarded, right? And then coverage will be expanded, but as a trade-off, basically at the cell center, the performance will be degraded. On the other hand, if the coverage is good, tilting angle should go down, and then coverage will shrink and performance at the cell center will be improved. So what's shown in here is basically by observing the performance during the runtime and per cell antenna tilting and transmit power can be optimized so that the overall performance across the entire region can be optimized. Next one is basically there can be some more parameter optimization, and those could include handoff performance index and network scheduler. So as you might know, actually, when UE or terminal moves from one cell to another cell, at one point there must be handoff from one base station to another base station. And in order to avoid the ping pong effect, typically when UE moves from one cell to another cell, only if the received signal strength from the new cell is of kind of larger than the current kind of cells signal strength by more than some threshold. In such a case, the handoff actually occurs. But there can be a lot of parameters which kind of triggers handoff. Some of the time kind of threshold, and some of the signal strength threshold, and so on. So depending on the parameter setting for this kind of handoff decision, the performance of the handoff can be improved without incurring a lot of frequent handoff, such as ping pong effect. The next one is network scheduling. So scheduling is a very traditional problem to kind of maximize or optimize the performance. So there have been a lot of scheduling policies or algorithms developed with various performance measures, such as kind of providing fairness. The typical kind of performance measure is proportional fairness index. And or maximum throughput might be per cell might be another goal too. So the point is, well, they're having a lot of theoretical work, to develop schedulers and so on. But in reality, if you go to the kind of real field, there are a lot of key performance indexes, KPIs, which cannot be compromised from the network operator's point of view. So fairness is important, throughput is important, but there are a lot of performance indexes which should be considered. So the point is, in the real field, theoretically proven or theoretically developed scheduling algorithms cannot be used as they are, and a lot of tuning is required. And so and another thing is, depending on the region and depending on the cells and depending on the time of the day and depending on the weekdays and weekends and so on, this kind of situation can vary a lot. So for this kind of scheduling function optimization, again, AI, ML technology can be used. So far, what I said is, 5G is there and it's becoming wider and wider and more popular. And we see the usage of AI and ML in this 5G era, and we'll see more and more, AI and ML usage in the future. So I think, for the rest of my talk, I will talk about what's happening in the future. So what's after 5G? So 5G is still early in the initial stage, but isn't it best time to think about the next generation? So what's shown in here is from 1G to 5G, there have been a lot of new functions and evolution and new feature introduction and so on. But when you take a look at this right-hand side, it shows the timeline from the inception of the technology development to the actual commercialization or deployment of each generation, beginning 3G and 4G and 5G. What we see in here is, let me see. Yeah, so if you take a look at 3G, the inception of the technology development started, in 1985. Then it took 15 years for the standardization and so on. And then actual deployment started early year 2000. So it took 15 years. In the case of 4G, the inception was in year 2000. That's when 3G started, kind of commercialization. And then from there, it took like 12 years. And then finally, around year 2012, actually deployment started. And then 5G, actually the vision and tech standardization started in year 2012, which was when 4G deployment started, okay? And then, as we know, the 5G commercialization was realized last year, and it's kind of still happening this year, year 2020. So what I'm trying to say is, in cellular communication, actually each generation preparation took about or around 10 years. And given that 5G is just starting, now it's very right time to think about what should be the next generation. Okay, so at Samsung, we started kind of thinking about what the next generation or 6G should look like. And well, actually very recently, last month, we released our 6G white paper with the vision of, or the catchphrase of, the next hyper-connected experience for all, or to every corner of our life. So again, the 6G is for 10 years down the road, but we now started thinking about it. And in this white paper, we shared some of our thoughts about our vision and some of possible or candidate technologies for 6G. So for the rest of my talk, I will briefly talk about some of the contents which you can find in our white paper. So again, 6G is for year 2030. Well, actually, by the way, we think that 6G could be commercialized as early as in year 2012-8. But again, 6G will be mainly used or widely used in year 2030 and down the road. So what will be the mega trends in year 2030? So there will be a lot of mega trends which can imagine, but one thing is there will be a lot of machines. So by year 2030, 500 billion devices will be connected to the internet, and those will include vehicles, robots, drones, and home appliances, and so on. So in 6G era, we believe, there will be a lot more machines than human being, and machines could be the main users of 6G. And also there will be a lot wider variety of form factors for mobile devices, well, AR glasses, VR headsets, and even hologram devices. And the next one is, again, AI, artificial intelligence. Well, I earlier said that AI is being heavily used or becoming more and more used for even 5G. But I think AI will be even more major role for improving network performance, reducing cost, and saving energy in year 2030. And as you know, today, a lot of network equipments are being softwareized, and this kind of softwareization and open architecture will be even more big trends in year 2030. So what will be some killer services in 6G era? So we can imagine some new services via higher hyperconnectivity involving both human and things. The first one could be truly immersive XR or extended reality. So as the resolution for VR, AR, and mixed reality increases, a lot higher data rate will be required. And the next one is, again, mobile hologram. So hologram technology is not there just yet, but in 10 years down the road, we believe that hologram will be realistic then. And to support very high fidelity mobile hologram will need a lot higher capacity over the wireless link. The last one could be a digital replica or digital twins. So by replicating physical entities and interact them in the virtual world without temporal or spatial constraints, I think we can do a lot more things compared with purely virtual world or purely physical world solutions. So the point is, all these truly immersive XR or high fidelity mobile hologram and digital replica, again, depending on the resolution of the things which you would like to see or share or replicate, the data bandwidth needs will be a lot higher than what we can support with 5G. And so with 6G, we'll need a lot higher data rates compared even with 5G. And then what will be the requirements for 6G? So basically, I mentioned some of the services, but these services will require not just data rate, but it will require substantially higher computing power. And also for the interaction, it will require high or ultra low latency. So we are considering 3 different kinds of requirements. The first one is, as has been with 3G and 4G and 5G, basically we are talking about performance requirements in terms of data rate and spectral efficiency and latency and so on. So in terms of peak data rate, with 5G, I think in the earlier part of my talk, I talked about 5G's, peak data rate was defined to be 20 gigabps. We target 1,000 gigabps or 1 terabps in 6G. For user experience data rate, we're talking about 1 gigabps compared with 100 megabps of 5G. And also, let's see, for air latency, so latency over the air link, 5G targets 1 millisecond over the link, and with 6G, we are talking about 0.1 millisecond. Okay, so again, we can imagine that 6G's, this performance requirements will be a lot higher and tighter than 5G. Not just that, we also consider some of architectural requirements and trustworthiness requirements for 6G. So with 6G, as I said, we'll have a lot variety of form factors, and irrespective of the form factors of user devices, we should be able to enjoy high fidelity and high computing, heavily computing intensive services. So to achieve that, we will consider communications and computing convergence. So I will talk about split computing concept later. So basically, the computing will be performed not only at the end user device, but also in multiple network entities. And also, network AI will be more heavily used. And so what happens is, in today's 5G network, at a given network, AI technology is being used. But for 6G, can we design 6G by considering AI from the beginning? So that's our thinking of native AI. So the last requirement is about trustworthiness. So earlier I said that there are more softwareization and open source based development is becoming more and more popular. So in 6G era, even if we use open interfaces and open sources and so on, the security should be clearly or tightly supported. And also, if we think about AI, basically we know that AI works well in many places, and AI is used as solution in multiple applications. But in many cases, we don't know why AI works good and what AI does, what deep learning does and what machine learning does for providing this, good performance. So, and also, AI, in order to provide good performance, in many cases, personal information might be utilized. So, we should understand what AI utilizes for performing better. And also, even if AI is used, users' privacy should be well protected. And if, we should be able to identify if AI is malfunctioning, and also if AI is kind of utilizing in personal or user information in undesirable manner. So in that context, basically, trustworthiness should be properly provided and guaranteed. So this slide shows some of candidate technologies to realize 6G, which we are currently considering. So those include terahertz band and a novel antenna technology, duplex scheme, and so on. And I will share some of our thoughts in the following slides. So in earlier part of my talk, I said that with the generations of cellular technology, the carrier frequency moved up and up. So 4G was utilizing only sub 6 gigahertz carrier frequency, while 5G introduced millimeter wave. So for the actual commercialization, only up to 30 gigahertz is being utilized, but 5G actually defines carrier frequency usage up to 110 gigahertz. So what's next? With 6G, we imagine that even higher carrier frequency will be utilized. So that's the reason why we are talking about terahertz. So actually, terahertz means basically 1,000 gigahertz. So it's very large, very high frequency. So by moving up to this terahertz or sub-terahertz, domain, basically we can consider or we have a chance to enjoy even wider bandwidth than the higher data rate can be supported. And also by utilizing wider bandwidth, because the time granularity can be very fine, we can also utilize this kind of terahertz communication for a high precision position kind of provisioning too. But actually, if you think about this kind of very high frequency region, there are a lot of inherent technical challenges. But the thing is, in this high frequency domain, we don't have, RFIC or even discrete RF components. So in order to develop this terahertz technology, we have to develop our own RFICs and ADC, DAC, and so on. And also, as I said, the higher the frequency, the higher path loss involves. So in order to overcome severe path loss and atmospheric absorption, what we should do, that's a big question. So we might need, even more, by the way, with the introduction of 5G, we use very massive MIMO technology. So for 5G, hundreds of antennas are utilized for 5G transmission. So with 6G, we might need even more, like thousands of antennas for the transmissions. So that will require a lot of challenges. So another candidate technology which we are looking at is novel antenna technology. So as I said, with massive MIMO, which was utilized or introduced with 5G, but with 6G we might need even more, even larger number of antennas. But utilizing large number of antenna involves a lot of challenges. So is there any alternative? So this metamaterial kind of technology is kind of alternative technology which we are considering. So there can be both meta surface lens and a metamaterial antenna. So this meta surface lens is on top of existing massive MIMO. So by using massive MIMO, basically we can make beams, kind of beamforming of signal, but by adding this meta surface lens on the surface of kind of antenna array of massive MIMO, we can control beam shape and direction and even make sharper beams so that the signal strength at the receiver can be enhanced. Another thing is, as I said, by using metamaterial antenna, we can fully replace the conventional or traditional massive MIMO or kind of technology or a massive MIMO antenna arrays. Another thing is the evolution of duplex technology. So duplex technology means the transmission of uplink and downlink. So how to share an uplink and downlink. So basically base station is there and UE or user terminal is there. So downlink and uplink. So in order to support both uplink and downlink, there have been traditionally TDD and FDD. So with TDD, time sharing of uplink and downlink was occurring. With FDD, basically different set of frequency bands are allocated for uplink and downlink respectively. Now we are thinking about full duplex. So by using the same frequency band and time, uplink and downlink transmissions can occur simultaneously. So that's something like, while I'm talking, I hear from what others say, simultaneously. So apparently this involves self-interference. So while I'm receiving, my self-transmission kind of work as interference. So how to cancel self-interference while I'm receiving signal is very important, key challenge and technology. So actually this is self-interference, but if you think about kind of multi-cell environment and kind of multiple user terminal environment, while single base station is receiving while transmitting. So self-interference is one thing, but another thing is one UE's uplink signal can work as a cross-link interference to another UE in the same cell. And also this kind of cross-link interference can occur across multiple cells as well. But anyway, by using this kind of full duplex, we can apparently kind of double the capacity of the link. So we believe that this is very promising technology, and we are looking at this very carefully today. Another is evolution of network topology. So the traditional topologies, again, as shown in here, multiple base stations are deployed across a given region, and depending on the cell coverage, UEs are connected to a single cell. And typically, these base stations are connected using wireline links. But today, we are considering wireless backhaul. So kind of connecting multiple base stations using wireless backhaul is kind of emerging. So in 5G era, a technology called IAB, integrated access and backhaul, is kind of emerging. And we believe that it will be kind of play a critical role for the wider spread of millimeter wave communication in 5G. So in 6G, I think we expect a lot more. Basically, automated configuration and optimization of new network entities, and those new network entities includes not just the traditional base stations, which are connected wirelessly or through wireline links, but also new entities such as non-terrestrial network entities, satellite and HAPS, high altitude platform systems, will be considered. So these days, actually, many new satellite companies are entering this kind of cellular industry. And the goal is basically to support wireless connectivity to this smartphone, but using satellite link. So in old days, satellite links were providing kind of internet connection to unconnected areas like, kind of deep mountain areas or desert areas or oceans and so on. And also, if you think about some satellite systems like Iridium, some special purpose, very heavy smartphones could be used for the communication with satellite. But again, what happens if we can enjoy satellite service using our smartphone? So that's the big kind of challenge today. And it might happen in years down the road, but in 6G, I think that will become even more popular, and a lot of network entities such as satellite, HABs, and air taxis could play a role in this kind of new network topology. The next one is spectrum sharing. So actually, traditionally, for 4G and 5G, network operators had to kind of go through spectrum auction to get the license of the usage of spectrum. Especially when I say, usage of spectrum, typically it has been like, get the license from the government, and then the particular band is kind of used by a particular network operator in a kind of orthogonal manner. So not other, kind of operators were allowed to utilize the band at the same time. But what happens if we are allowed to share the spectrum across multiple network operators so that, spectrum can be utilized in a more kind of uh, adaptive manner. So the thing is, because the spectrum usage needs can vary across multiple, operators, if they can share the spectrum in a kind of adaptive manner, the spectrum utilization can be improved so that this kind of precious, spectrum can be more kind of efficiently utilized. So in here, again, AI ML can play a role so that, dynamic spectrum can be kind of achieved while sharing only limited amount of information is kind of shared across multiple network entities or network operators. So, I talked about, AI and native AI, and well, again, AI will play even more important role and across multiple network entities, including UE base station, core network, and application servers. And I think, as I said, in order to achieve native AI, so that is kind of designing 6G by considering AI from the design phase is very important. The last one is, I think, split computing. So I think I talked about communications and computing convergence briefly already. So independent of device capability. So in here, this AR device, which does not have heavy computing capability, achieve very low resolution but by kind of splitting computing load across AR and network entity, like edge computing at the base station, by kind of sharing the computing load, even this kind of lightweight AR device can enjoy high fidelity, AR service. So especially if you take a look at the right-hand side, depending on the end device's capability. So if the device is very capable, all the computing job can be done at the device. But if you take a look at this kind of smartwatch or AR, basically very light load computing is done at the device, on device, but the rest should be done at the network edge or at another device and so on. So, by kind of distributing this kind of computing load or by splitting the computing load across multiple network entities, I believe we can enable kind of, all different types of devices to enjoy very high fidelity service in 6G era. So let's wrap up my talk. Again, what's happening is, 5G commercialization just started and it's kind of happening now. And for 5G, AI, ML is being utilized. And we just started 6G research, but in the future, basically more wider spread of 5G and heavier usage of AI, ML, and we'll see many research and proof of concept kind of demonstration of various candidate technologies, including what I mentioned. And we expect the 6G commercialization as early as in year 2028. So thank you very much. That's it from my side. Thank you very much for your attention.
Thank you. Thank you, Dr. Choi, for the very visionary talk. And yeah, and Dr. Choi finished it on time, so we have pretty much time for the Q&A. So is there any question? If you have question, please raise your hand so that I can unmute you and you can just speak with Dr. Choi. Uh, there is a question. Let me see how to unmute.
Hello?
Young Han, right? So
Yeah.
please.
Can you hear me? Yeah. Hi, thank you for the impressive presentation. I have a question about the security of 5G or 6G. To
Okay.
achieve low latency, 6G utilized split computing that uploads workloads to distributed servers or IoT devices. However, I think such changes might also increase the attack surface. For example, a malicious attacker might want to eavesdrop the communication between IoT device and base station to achieve users' private data. So I wonder what kinds of technology are being developed to protect against such threats.
Well, frankly speaking, we are still working on it. But actually, you have a very good point. Uh, so what you said is through split computing or by involving multiple entities across network, there'll be more information exchanges, and there can be a more or higher security threat. So your question is what's the kind of um, countermeasure or what we should do in the future. So I did not mention about our security solution in detail, and but we are definitely looking at that problem. And yeah, by the way, even in 5G, because I think people and even government today are more kind of interested in security and security attack. 5G's security features are much more stronger than 4G. So 5G commercialization started last year, but 5G standardization has not finished just yet. So I don't know if you're familiar with 3GPP, but basically when you say 5G, especially 5G commercialization, the commercialization which is happening now is utilizing 3GPP release 15. By the way, release 16 has just finished, and ITUR's 5G standardization will be based on release 15 and 16. And people are working on release 17 now. So my point is 5G itself is evolving, and one very important part of 5G and also the future generations will be having higher security kind of measures. So again, I don't have enough time to talk about 4G versus 5G security features, but if you are interested, I recommend you to take a look at new features of 5G for security features. And again, for 6G, we'll take a look at 6G and kind of security and privacy problems for sure. So thanks very much.
Okay, thank you.
Any question? Please raise your hand if you have question. Uh, okay, actually, I have a question. So I have a question about you mentioned about the 6G, we use the Hira hertz kind of bandwidth. So I just remember that the current situation and problem faced by the megahertz. So it is a very promising technology, but it has some practical issues like it cannot go through the materials, and the region of this radiation is limited. So if you just push it to the even higher frequency, so will it be very practical?
So your question is, 5G introduced millimeter wave. It was kind of promising technology, but it also involves a lot of problems, and especially related with the propagation characteristics. So what happens with even higher frequency in 6G, which is terahertz, right?
Yeah. Yes.
It's a really good point. So I'd like to mention two things. So millimeter wave at 5G, um, it's being utilized, but still at very early stage. And I think it remains to be seen whether how millimeter wave of 5G will be successful, and in what domain it will be utilized. Again, I think one of the very possible kind of usage will be wireless backhauling, right? And other than that, such as kind of using, support, this access for handsets and smartphones. I know that in the US, operators provide millimeter wave based, wireless access for smartphones too. So again, the point is the millimeter wave future and the usage will remain to be seen. And then along with that, I think at this stage, we would like to understand, how promising terahertz is. And so we are doing kind of prototyping, within the company, and we'll see how it goes. But the point is, actually, this kind of high frequency has a lot of potentials, especially because of very wide bandwidth and potential to support very high speed. And again, as you mentioned, it has a lot of kind of downside too. But because of this merit, I think we'll find very interesting applications in various domains. That's what I remain, I think imagine, and that's what I hope.
Okay, thanks.
Okay.
So we will have the last question. So who will be the last one?
Can I ask a question? So it's very interesting talk. Thank you very much. So today you mostly talk about issues in, to me, wireless communication issues and access networks. Can you talk a little bit about challenges in designing core networks for 5G and 6G? Is it like too easy, or so you seem to let it out? So can you talk a little bit about it, or?
Yeah, core part, again, it's very early stage, so I cannot tell for sure, but we are definitely looking at the core side too. Basically, one thing is, well, actually, when you say core, I think you are not talking about the network topology, but the core side, like, network functions, like, UPF and so on. Is that what you're asking about? Okay, I see. One challenge which we are looking at is because of the softwareization of the network devices, such as routers and so on. We are looking at, again, software implementation of these network core functions. It happened, or it's happening already, but I talked about like hundreds of gigabps, right? Can we really implement and support such high speed using off-the-shelf servers, x86 servers? I think that's a big question, which we are looking at now. So yeah, I think, other than that, I think another thing could be, I think, convergence of transport technology and so what I'm saying is, let me put it this way. So core network is being defined by 3GPP, as you might know. So 3GPP defines from physical layer over the air, RAN side, as well as core network too. In the core network, this network function virtualization and so on, the service-based architecture was introduced and so on. But basically, 3GPP has not been care about transport technology, such as how to support this backhaul technology, or optical fiber and so on. So what I believe is, by combining or by considering this core network along with transport technology, I think we have a chance to improve the performance while minimizing or reducing the OPEX and CAPEX and so on. So again, it's very initial thought, but I think we have to think about that kind of direction.
Okay, thank you very much.
Okay, thank you.
I think this concludes this session, and we thank again to Dr. Choi. So thank you for your great talk. And
Okay, yeah.
Thank you. And
Go ahead,
we'll,
go ahead.
Thank you.
we'll have a small break, and the next session will be the industrial spotlight talks. Okay.
Okay, so thank you very much. Please enjoy the rest of the workshop. Thank you very much. Bye-bye.
Bye. Thank you.
Hello. Hello.
Hi.
So we're going to start the second session. Okay. So let's get started. I'm Kuntan from Huawei, and we are going to have the second session of today's morning. It's an industrial spotlight talk. We have three very great talks going to be presented in this session. So let's welcome the first speaker, that is Ted from Alibaba. Dennis is the chief architect of Alibaba Cloud Network Infrastructure and also the head of Alibaba High Performance Networking Group. He is responsible for the architecture and the future evolution of the Alibaba Cloud Network, including the data center, metro, backbone, and edge network. He is also the driver of the evolution of the high performance DC network in Alibaba and deploy new technologies such as RDMA, advanced network congestion control, and etc. So before joining Alibaba, Dennis was a distinguished engineer at a Cisco. So welcome, Dennis, and he's going to talking about building the predictable DC network for next 10 years. So Dennis.
Hi, can you hear me?
Yes.
Okay, let me share the slides. Can you guys see the slides?
Yeah, good.
Okay, let's get started. So good morning, good evening. My name is Dennis Kai from Alibaba. So first of all, thanks for Professor Chen to invite me to speak at Apnet 2020. This year is difficult and special for all of us. And all the sessions are remote through the cloud. So this makes my talk somehow more meaningful. So what should we do for the cloud? How the data center network evolve in the next 10 years? So that's what I'm going to talk for this session. So Alibaba is a web company. Many of you probably know us as a giant e-commerce company. So this is just one of our core business. But beyond that, we also have many others, such as electronic payment and fintech, digital media and entertainment, logistics, and many other business initiatives and innovations. So all these business and applications are running on top of the Alibaba cloud infrastructure. So as you can see, our business and applications are very diverse. In addition, we are very fast growing as well. Together with a hyperscale, this brings in tremendous challenge to our network infrastructure. So we are very actively looking for and adopting new technologies and innovations to meet our business requirements. From a business requirement point of view, the network must be highly reliable. It can iterate quickly to provide the feature velocity. In addition, it must provide high performance and low cost to make our products more compelling. So a quick overview of Alibaba Cloud global network infrastructure. So we have 22 data center regions worldwide and over 2,000 edge sites. They are connected by Alibaba Global Network and support billions of our end users. So when zoom into our data center region network, it is a high available design with multiple availability zones. The availability zones are connected through high bandwidth metro network. Within each availability zone, there could be multiple data center clusters, and each data center clusters is a hyperscale multi-tier class architecture. So a single scale out data center cluster can support a range of few thousand to close to hundreds of thousands of servers. So for today's presentation, the focus is on the data center region network, particularly a data center class network. It seems the slides and the voice have some delay. So I look at the U-tune of my cell phone. There seems there's some delay there. Anyway, so well, that's just a quick introduction. Now let's start our, our real stuff for today's talk. So I guess we all know Moore's law, right, in the semiconductor industry. And actually in the networking and the telecommunication world, there is also a law called Metcalfe's law. So Robert Metcalfe is a co-inventor for Ethernet, and he's also the co-founder for 3Com. And he formulated a law which indicates the value of any network would increase as a square of the number of the connected device. So basically what this means, the scale does matter, right? It will bring the value by the square of the node. The scale does matter also from different perspective. It means something challenge as well. So even though there's not such kind of law based on our real experience, the network complexity should also increase by, if not the square, it could be something even more than that of the connected nodes as well. So in the data center, typically we use the number of the server to indicate the scale. As a typical enterprise data center, tens of thousands of servers could be big. But for the large web company like us, we measure the server in million, right? So when your data center scale increase from hundreds of thousands to a million, what does this mean? I mean, it certainly means a big business success, right? As Metcalfe's law says. But for us as a network operation engineer, this also means somehow a nightmare. And we, and including myself, we did have such kind of nightmare experience back to a few years ago in our network. So moving forward, cloud will become a new public infrastructure, just like water, gas, power, railway systems. So more and more enterprise, government, small business, or even individuals will move the RT infrastructure to the cloud in the next 10 years. So our cloud data center will continue growing and scale to another level. So what can we do and what should we do now? So how to keep the performance, reliability, and make the network be manageable when the scale increase? This is a problem we need to solve today. So different people certainly have different opinions, but here's what I'm thinking. I want to divide the network eras or ages into 3. So the internet era, well, the main purpose of the networking is to connect people. It is a connection need. The more people you connect, the more value you create. So connection means value in that era. So I still remember not a long time ago, probably 20 years ago, it cost us 5,000 RMB just to install a telephone at home. So the connection really means the value. In the internet era, the network is made by commercial equipment, which is a closed hardware and software systems. Roughly about 10 years ago, the web applications like Google start to be really booming. So the data center which support web application become bigger and bigger. At a certain point, they run into the wall. And the disruptive innovation started from there. People start to rethinking how to build a hyperscale data centers from the physical topology, from the networking protocols, how to build a switch, and how to manage a network, and etc. So you all know right now, it's eventually coming to SDN, software-defined network, merchant silicon, white box become popular, open and disaggregation become the mainstream, network automation become a must for the mega scale data centers. So the source of the innovation in the data center space is shifting as well from the equipment vendors to the bigger web players. So that happened in the last 10 years. So what's next? So what the network will look like after 5 to 10 years? Which direction should we move towards? So fundamentally, the network innovation coming from two parts, the business and the technology. From business perspective, the cloud will become a new public infrastructure, as I just mentioned. So the scale will continue growing, even at a more accelerated rate than before. And it will scale to next level, which could be tens or hundreds of millions of servers. So how to manage such giant, large data center network? So from availability point of view, it must be super reliable, just like some other utilities, just like water faucet in your kitchen or table light in your bedroom. From the workload point of view, the artificial intelligence will dominate. So we're going to end into a big data era. So we need a high performance network to connect the data and the CPU, GPU computing power. So the business and applications bring in tremendous challenge to our network, which will require technology innovations. Fortunately, there are lots of innovations happening already, especially from the hardware chips point of view. So the chips now are programmable and have a high visibility as well. So this makes it possible for the data center network continue evolving and meet the business needs. So we will end into a new era, the era of the predictable network service, in my opinion. So in my talk, I will quickly review the network 1.0, the connected era, connection need era. Then we'll share with you what we did in Alibaba in the last 10 years, basically the network 2.0. After that, I will talk about some of our latest work, which we are doing in Alibaba, and we believe the network 3.0 is the era of the predictable network service. So I started to work for Cisco since the year 2000. Back to the early of the 2000s, as a network engineer, what we talk the most is all kinds of network protocols, right? You name it. All this like a spanning tree, fabric path, layer 2, all kinds of layer 3 routing protocols, MPLS, VPNs, all the tunneling protocols. I even do not want to mention multicast, which will make your network 10 times more complicated with multicast. Besides the protocols, the other big things is the network equipment, the routers and the switches, right? So if you are a master for some popular network device like Catalyst 6500 or Cisco CIS, you will be a superstar at that time. So network 1.0 is the age of the network equipment vendors and this is CCIEs. Things run pretty well. As a network engineer, we were all enjoying the golden age of the network 1.0. But as the network continue growing, switch and the routers scale up, it become bigger and bigger, more and more complicated. And it become much more difficult to manage. And more important, it just cannot catch up the speed of what application needs. Finally, it was broken. And then we fixed it. This is what happened in the last 10 years for the network 2.0. Network 2.0 is an era of the web scale. It is the mega scale data center which drove the disruptive network evolutions. The tier 1 web company and the cloud providers finished this round of architecture evolution in the past 10 years. Some companies like Google, they started earlier, while others may come a few years later. We at Alibaba also completes this network architecture evolution in the past few years. So I'm going to share with you some of our direct experience of the network 2.0 evolution at Alibaba. Our network 2.0 journey started from 2013. The first thing which we did is to standardize the data center network architecture for different business group and applications. After that, we adopt the hyperscale network design, get rid of all this layer 2 stuff, make layer 3 end-to-end, use BGP as a routing protocol instead of OSPF. In 2015 and 16, we did some kind of trials and for our VPC virtual network for the cloud business. We tried open flow-based network overlay solutions, and we eventually moved to a host-based overlay solutions with VXLAN. From architecture and technology point of view, eventually everything seems settled down. But we still run into a big challenge in about 2016. It is what I called earlier a nightmare. So our network had an exponential growth in that years. So around like 2015 to 16, we run into the point which we believe we need to rebuild our data center network. The main drive coming from the network operation, the manageability and the reliability. Here's what we did for our architecture rebuild. So first, we moved from the scale up hyperscale architecture to a true scale out architecture with a multi-plan. The single cluster can scale out with multi-plan from a few thousand to close to hundreds of thousands of servers. Second is about the switch. We made the switch based on a motion silicon, based on a white box hardware and in-house software. We get rid of this big chassis. From the software point of view, we did a maintenance first to reduce the software complexity. And then we add quite a lot of features for the network monitoring and the management. At the end, with the fully in-house built software systems, we are able to make our network management systems much more efficient and fully automated. So this is fully rebuilt systems from architecture to the device, including the hardware and the software, to the management systems, dramatically reduce the workload for our operation team and make our networks much more stable. And this architecture rebuild in Alibaba, we made the network shift from 1.0 to 2.0. Here's a high-level overview of the Alibaba Network 2.0 architecture, the data center network, which we call the HAIL. So HAIL stands for High Availability, Intelligence, and Low Latency. So it is a multi-tier class true scale-out architecture support mixing of 25 gig, 50 gig, and 100 gig servers. It is built from the single chip switch. The switch and optical transceivers, they're all based on the motion silicon, white box hardware, and in-house Alibaba software. So in the HAIL network, we support advanced network monitoring and operation-related features, such as this in-band network telemetries. And we also had the RDMA high performance networking feature enabled everywhere. So here's an overview for our switch. So even though Alibaba made switch a long time ago, but those are the switch which has massive deployment in our network. So one is a Fishbone, another one is called Finex. So Fishbone is our top of rack switch as built based on a 3.2T switch chip. The Finex is our leaf and spine switch is built based on 12.8T the chip. So Alibaba Network OS, which we call AliNOS, is based on open source Sonic systems. It is like a decoupling software and hardware through the SI. So it is an open platform based on Linux and x86. It is container-based. You can manage the switch just like you manage the server. So we can support warm and hot upgrade. So the high availability architecture is based on Radius DB, and the management and operation is through the gRPC. So from the feature point of view, we remove those unused features, simplify the server dual homing features, enhance the BGP convergency, and put a lot of effort on the network management side. Last but not least, it is a container-based. We support 4 virtualizations. In fact, we build a virtualized data center network. Systems use a simulation. So we can simulate a large-scale data center network for control plan verifications, for some regression testing, for some configuration verification, and so on. I would like to use this slides to conclude our network 2.0 journey at Alibaba. So there were lots of arguments or different opinions about the white box. What's the motivation behind, right? Even today, and all the friends of mine, Francisco, now he's in Juniper, actually he's quite a senior guy, still ask me the same question. So what's the business model for the white box and why? So based on my direct experience of the network 2.0 journey at Alibaba, I think white box is one of the components, but the mandatory component to make up the hyperscale data center network. It is not about the hardware or the cost. It is about the in-house software. Only if you fully control the switch software, you can integrate it with your network management systems in a very efficient way. You can flexibly split your network monitoring and some ops related operation and the workload on the backend and on your switch itself. In addition to that, only if you fully control your software on the switch and on the server and the NIC, you can have many more advanced features, such as the path control, fast failover, end-to-end monitoring, and so on. Those are very essential for your future high-performance data center network and for your much more stable network.
你们两个上两口，这个应该是6.6.2，那个
好像有些噪音啊，能不能把它 mute 一下 ？Yeah. So okay. So in short, white box switch is one of the mandatory key components of the data center network systems. But if you only look at the switch alone, without other pieces from the puzzle, there's not much value by itself. So that's my opinion. So now let's end into the network 3.0. We are entering an exciting era of the networking industry. So we expect that many things could happen in the next 10 years. So the cloud as a new infrastructure, it will move into the mega scale, right? The DC will continue to increase to the next level. So how to handle the new challenge of this network operation? So the network as a utility, so just like other utilities, the service must be super reliable. The performance must be predictable. So the technology side, compute, storage, network, they continue evolving in parallel. Switch chips continue the Moore's law. The bandwidth double every 18 months. This could continue for next 5 years at least. For storage, there's a new storage media type comes out. It's much faster and a bigger volume as well. Per gig price is going down dramatically. From the compute side, we are in the heterogeneous computing era. The GPUs, the domain-specific AI chips will become more and more popular. So even though the network storage and compute, they evolve in parallel independently, but they need to be combined together to achieve the data center scale performance. Another one is the power about the hardware chips. The switch chip, the NIC chip, they are moving to programmable. They can provide much more advanced network telemetry and instrumentations. So the data center workload is also shifting. AI lead application will dominate. We're getting into big data era will require data center scale computing power. Put all this together, the data center architecture will also need to evolve. The data center will eventually become a software-defined, reconfigurable, efficient resource pool. So let's see what we can do and what we are thinking. Okay. So overall, a cloud will become a new public infrastructure. The network as a foundation of the cloud will become a new utilities. Okay. So it must be very high available, highly reliable. So the resource pool must be able to be shared in a secure and efficient way. It must be able to provide differentiated service with guaranteed QoS, basically pay as you need. So fundamentally, it should be able to provide a predictable services. So how to achieve the network as utilities? So how to provide the predictable network services? This is not something easy, but this is the direction what we truly believe. So first, the network must be highly available from the central data center all the way to the edge, to the 5G, to the MAC, cover the different type of the customer and the use cases. The second, the network operation will enter into the new level. With the new technologies, we are going to enter into autonomous time. So make the network super reliable and be manageable. And the third, the network must be fully programmable, and with advanced network telemetry, it can close the programming, analysis, and verification loop in an automatic way. So with big data analysis. Last but not least is about the performance. The high performance network is a fundamental piece for your future data center network. So it works as a data center I/O fabric. It makes data center resource to be reconfigurable. So this is just like an overview. So now let's look into some of the details. Now moving forward, right, to the next 10 years, the cloud will become a new public infrastructure. The size of our data center will become much bigger than we call mega scale today. Eventually, it could become like a giga scale. So it could be 10 millions or 100 millions of the server. In such kind of giga scale data center, how can you do the network troubleshooting? For the packet loss, for the slow I/O, it must be different approach. It must be more intelligent than ever than what we can think today. So the answer, at least as right now, we think is big data and machine learning, artificial intelligence. We must get enough operation data from the network and do the intelligence analysis and take action fully automatically. So first, we need the data, enough data from the network, right? With the more advanced switch and the NIC chips, we get much more data than before. Not only the switch operation status, but also the user flow level informations. So here's just some examples, right? So today we can achieve the user flow based network telemetry, such as a user flow network path per hop delay, the port rate, like a buffer usage. We can also get the packet buffer snapshot, like what's the real-time buffer threshold, what's in buffer packet information, and so on. And certainly for the packet drop, we know the reasons. So why the packet drop? Because of a congestion or because of pipelines. And we also make the streaming telemetry to make the data come out of the switch much more efficient. So that's the first thing, is you need to get enough data. Now, second thing is, with this huge volume of the data, how can you handle it? You have to trim it. You have to find the useful information from it. Otherwise, you're going to generate like huge data to your network, and eventually will kill your backend systems. So this require in-networking computing. You have to do certain job in distributed way to be done by the switch itself. So at Alibaba, we did some experimental in this area back to like 2017, and we made some significant progress. So in this year, we published a white paper in the SIGCOMM, which is called Flow Event Telemetry in a Programmable Data Plan. We believe network telemetry is the foundation for the autonomous network. So when the network scale to the next level. So with the big data analysis in both distributed and centralized way, we could identify the network congestions, the failures, and take a certain action very fast and in an automatic way. So we continue the topic of the chip. So with advanced programmability and the network telemetry, we could have a verifiable closed loop control. From technology point of view, we are entering into the so-called SDN 3.0 age. SDN is the most popular topic for the network industry. So I won't spend any time here. According to the Nick McCone, who is the co-inventor for the SDN, we can divide SDN into 3 stages or 3 phases. So the phase 1 is software defined. Basically, the network owners took control of the packet, took control of the software and define the network, just like us. So we are the owner for our network. Today, our engineer writes the network OS, write the software, write the code to operate the switches, not the vendors anymore. So the phase 2 is about the programmable chip. So the network owners will take control of the packet processing. At Alibaba, we have used the programmable chip for quite a few years now. So the P4 switch has been deployed at scale in Alibaba. So we wrote our applications in P4. We control the hardware packet processing. You know, the good things about this programmable hardware chip, there's one good thing for that is even the same chip from the same vendors, it could be programming for different use cases. As a network operator like us, we don't need to worry too much anymore to share our, some of our business logic with the vendors. Now we are at the beginning of the SDN phase 3. How can we verify what we did is right or wrong? The programming is one way. We need a bi-directional. So we need a reaction. We need a result from the network and compare what we programmed to see if it's right or wrong. So in Alibaba, we did both. We had both programmable chip switches deployed, and we also enable this advanced network telemetry in the production. Plus, we did some kind of research for the formal network verifications. So we are right now marching in the SDN 3.0 phase. So now let's talk about the workload. So we are in the era of the artificial intelligence and the big data. So AI need workload will become the mainstream in the data center. The GPUs, the AI specific chips have already gained a lot of attention in the industry. But the good news is more and more people started to realize the computer chip is not enough. It needs a high performance network to scale out. I guess this is one of the main reasons why NVIDIA acquired the Mellanox. The chip itself is important, right? It will scale up for its horsepower. I mean, certainly the chip itself will going to evolving by itself. But to gain the more powerful computing horsepower, it needed to scale out. So first level scale out is through the server systems. The one server, you could add multiple GPU cards there. And this GPU card can be connected to some high bandwidth network, such as NVLink. And multiple GPU servers can be connected as well through some special network at the rack level. But eventually, it needs to scale beyond the server and the rack level to scale at the cluster level. What we call this a data center scale computing. To support data center scale computing, we need a high bandwidth, low latency network fabric. Traditional TCP will not going to work well. So the core foundation for data center scale computing is from the network, from the high bandwidth, low latency network. As many of you know, the Rocky RDMA is kind of de facto standard for high performance network used in a data center. However, RDMA technology initially coming from InfiniBand. When it applied to data center Ethernet, it brings some bigger restrictions. As many of you know, it requires lossless network. This makes RDMA cannot scale well in the DC. At Alibaba, we took the RDMA technology as the direction back in 2016. Since then, we work with both our internal and external partners to apply RDMA to many of our applications. And from our real experience, we learned and we made progress, and we made quite a few important innovations. Now we are able to have large-scale deployment for RDMA. And we are making RDMA as a baseline networking transport, just like a TCP in our data center. This has become our high-performance data center I/O to enable the data center scale computing. Specifically, I can share a few innovations which we made for RDMA deployed at large scale in Alibaba. One of the example is HPCC, the high precision congestion control. Now with this, we combine the inbound network telemetry and the congestion control together. We eventually get rid of the PFC, and we can make RDMA to be deployed much more reliable and in much more scale. Another example is about the advanced network telemetry. So this is not only for the monitoring purpose. With this information from the flow, we can have very fast failure and congestion detections. And we can do failure avoidance and quick failover. So again, this year's CIRCOM, we published this flow event telemetry papers. And we also have inside Alibaba, we have multiple teams work together, especially from network and storage team work together, did lots of improvement from the predictable path management side. So we can have very efficient ECMP, and we can have much more predictable performance. So eventually we get rid of this slow I/O. So, and we also published the paper in NSDI for this year. So far, we talk about the business and applications requirement and some of the technology innovations, including hardware chips, SDN 3.0, RDMA, and so on. So now let's put all the dots together and see how can we evolve our data center network architecture. We believe the data center network will move from today's best effort network to a predictable network. The servers will move from compute-centric to a data-centric architecture. First, the network must be high performance and able to provide not only the traditional availability SLA, but also the performance SLA, such as guaranteed bandwidth, network latency, including tail latency and the failover time. With availability and performance SLA, the network and up-level applications can be decoupled. The network will become transparent to the up-level applications. This will make application and network evolve independently in parallel. From an operation point of view, there will be a clean boundary. It will reduce the complexity of operation dramatically. Today, when application report a packet loss, we don't know if it is application level issue or something wrong in the network. Network latency is critical for data center workload, especially for the high performance artificial intelligence workload, for the storage, and also for the compute storage disaggregation architecture. With a predictable network service, network latency is part of the service SLA. Network latency SLA, especially including the tail latency, is not something easy to achieve. This needs to be done through technology and architectural level innovation, including the RDMA technology, as mentioned earlier. From an architectural point of view, it will heavily rely on the smart NIC on the server side. When combine smart NIC and the switch network, we can achieve much more advanced function than before. We can have much more advanced network congestion control. We can have flow level, queue pair level, path monitoring, and intelligence path selection or path switch over. We have much easier traffic engineering capability in the DC as well. But certainly this will rely on the capability of the smart NIC and the switch, especially on the smart NIC side. The smart NIC will move beyond what it used to be. We can call it a DPU, a data process unit. It's just another network chip, but with computing power on it. The last but not the least, we will need the data center controllers. But this is different than the open flow controller. Data center controller in this case will serve as a global optimizer. The information will be connected, need to be analyzed, and then need to be synced to the DPU on the server. And the DPU will take the real actions in distributed manner. In the Network 2.0 era, the cloud computing scale out using hyper-converged server. When everything fit into one, if you need a more storage, you buy the server. If you need a more CPU or memory, you buy a server, right? It's quite easy. In the Network 3.0, we are in the AI era and the explosive growth of the data. The hyper-converged way of scaling become very inefficient. The data center will move into disaggregation. Data center will become the software-defined, reconfigurable resource pool. Thanks to the RDMA, right, low latency network transport, we did the storage server disaggregation, which are already in a massive deployment today at Alibaba. Now, we can also apply the same concept to the computing, to the GPU. So when the cloud data centers start to move towards AI, they need to have servers that are good at accelerating the AI as well. The CPU are not well suited for that. Instead of installing GPU into every server, why not? Why not we deploy GPU with disaggregated way in anywhere in your data centers, just like as we did for storage today. So with a predictable network as a data center IO bus, this become possible. So eventually data center will become a big high performance compute. With the computing resource, storage resource, it will become a resource pool at a different level, rack level, pod level, or cluster level. The servers don't need to be fixed SKU anymore. The ratio between the CPU, GPU, or SSD can be flexible based on the applications. The SSD and the CPU can be disaggregated. The GPU and the CPU can be disaggregated as well. So the CPU, GPU, SSD can be disaggregated and deployed anywhere in the data center as business need. This is the power of the next-gen data center, which will be empowered by the predictable data center network. So as a short summary, in the past 10 years, driven by the web scale and SDN, network industry had a disruption. Looking forward for the next 10 years, we will expect another disruption in the cloud DC. Network service will evolve from the best effort towards predictable, which will make our data center as a whole to be software-defined, reconfigurable resource pool. Last but not least, if you are interested in building such predictable data center network, please join us. In Alibaba, we have an organization called High Performance Networking Group. With this group, we'll make our vision to become reality. Welcome to join us. Thank you.
Okay, thank you, Dennis, for this visionary talk. So we have a time for a very short question. If you have question, you can raise your hands or I can unmute you. Okay.
I think I passed the time a little bit.
All right. Okay, so now I have a question for you, Dennis. So you mentioned not on the RDMA network deployment in Alibaba. I think it's wonderful. But what you mentioned in the talk, you most likely to put the RDMA in the context of a fast network. But how about this semantic, the difference? Because when we talk about the TCP and the RDMA, they have very different semantics. So have you any comments on what is new semantics? What's the bring for the DC computing, or is the RDMA is a good abstraction for that, or we need additional features for improve that?
Well, that's a good question. Actually, people talk about this, or the industry actually debate about this for, I think, like a decade already, right? So when we talk about RDMA, I mean, fundamentally, that's two kind of approach. So one is based on the Rocky, which is coming from the InfiniBand. Another one is coming from TCP IWAP, right? And at a different stage, I would say it could be have different results. So if you look at the past couple of years, the server NIC vendors actually, they implement Rocky RDMA pretty well, and it got deployed, right? But for the IWAP, because the TCP state machine is quite complicated, and it is very difficult to implement in the hardware. So that's the reason, based on TCP-based IWAP, RDMA, they get some kind of deployed, but not in real large way. But that is being said, that means there's no future, okay? So actually for the TCP, we're also looking at, so what we can do with TCP, especially with the, and especially when we do some of the, a lot of web customers actually do the NIC check themselves, right? So now with this, it might open the door for TCP-based as well. So at Alibaba, we are not religion to that particular technology. So
Right. So we have dropped the Dennis and Jeff. Okay. I'm not sure if there's I see Dennis, the picture is stalled. I'm not sure if there's the problem on my side or.
Sorry, I just got disconnected for some reason. Okay. I just like summarize, right? So the Rocky RDMA has widely deployed in Alibaba. For the TCP-based evolution, we're looking at this as well.
Okay.
Yeah.
So we have maybe I have one master question. So this is going to be the last. So Junhong, are you going to?
Yeah. Okay. Thank you for your talk. I have one question. You said that disaggregated server is important in network 3.0. So I wonder that is there any policy to set and maintain optimal scale of each disaggregated server? Like microservice in cloud.
So your question is about the disaggregated server, right? So your question about the scale, about something?
Yeah, but kind of number of server or.
Okay. So I can share something with you, right? So today, for example, our storage server and the computer, they are disaggregated. They are on the different servers, right? So they could be deployed in different locations or in the same locations. It's very flexible. So for the computing side, so right now, most of these are the CPUs, but we get more and more GPUs as well, and some other AI-based ASIC. So the question is, the GPU, this computing power is required by many of our customers. So we cannot have each like a common server to have a GPU card there. So which is not scale. So actually what we did is, we believe is the GPU will move into disaggregation as well. So we could have a GPU kind of a pod or a couple of racks of GPU servers. It's only for the computing, right? And then, through the high-speed network, they can go to the other server on the CPU side. So this is what I mean. What I mean. So from the scale point of view, I mean certainly the scale is some kind of number which I think probably is not good to be shared here, right? So it certainly will go beyond the rack level. So it could be multiple rack. Yeah.
Okay. Thank you.
Okay. Great. Thanks, Dennis. Thanks for the wonderful talk. So we have a applause mark here. So please have a applause for this talk. Okay. So thanks.
Okay, thank you. Thank you.
So
Bye-bye.
we are going to welcome the second speaker in this session. The second speaker is Jitu Padia. I think Jitu, and most people will know Jitu, right? Okay, so let's have a very short introduction for him. Jitu is now a partner development lead at Microsoft Azure Networking. He is interested in all aspects of the network, computer networking and network system. His current work was focused on the data center network and the mobile networking. I think he is a reception of the ACM SIGCOMM Test of Time Award for his similar work on the TCP modeling. Now we have welcome Jitu. He's going to talk about the reliability and the performance in Azure Data Center Network. So Jitu.
Okay. Hi. Can you hear me?
Hi. Yeah.
All right. Wonderful. I'm going to share. I'm sharing screen. Let me see if I can project. All right. Okay. So I'm going to talk about reliability and performance in Azure Data Center Networking. And let me begin by first thanking Kuntan for that great introduction. I worked with many of you guys in various capacities. And the work what I'm going to talk about today is essentially the work of a very large team that belongs to Azure Networking. Kun used to be part of, I used to work with Kun one time, several other people who are at Microsoft, who are now no longer at Microsoft. It's been wonderful working with this team. So this is a very large canvas, so as to speak. Okay, so as you heard previously, from several speakers, cloud is all about scale. This is one of our large data centers. Albert likes to show this picture. We like to show this picture to everybody. It can fit two 737 planes inside, tail to tail. So this is all about scale, right? And Azure scale is enormous. We have now 80 plus Azure regions worldwide. We have over 4,500 peering locations. We have many edge sites and a huge amount of fiber that connects all of this together, right? And I'm not even going to talk about how many servers we have. Those numbers are just astronomical, right? Okay. But when you run such a large network, again, as our previous speaker pointed out, the first and foremost thing is to ensure reliable operations. Next, we try to improve performance. And after that, after the first two things are satisfied, then we talk about potentially adding new features. So if you don't take anything else from this talk and you just take these 3 bullet points away, then my work is done. Okay, so if you want to run a large public cloud, you must first ensure reliable operations. After that, you do what you can to improve performance. And after that, you think about adding new features. Okay, so this is sort of the our list of priorities. So let's talk about reliability a little bit, right? And this is a picture. I think, thank you, Harry. This is a picture you drew, and I've been using it ever since. So customers place enormous amount of trust in us, right? A number of very large world corporations trust us with their critical data. When Azure goes down, a number of things can go wrong, right? And so when customers place their operations in Azure, the first and foremost thing they demand is reliability. And reliable networks are critical for overall cloud reliability. And I'm not saying that just because I work in networking or you guys work on networking, everybody likes to say that networking is critical. But that's because networking problems can have a very high blast radius. So take an example of Microsoft's network. So we have multiple data centers in an Azure region. For example, in US East is one of our very large regions. We have several data centers. And these data centers are connected together with a regional backbone. And this typically has 32 routers, 64 routers. And by design, these routers are identical. By design, they have the exact same configuration. So if there is a systemic error in either the hardware or the software or their configurations, then what's going to happen is a bunch of them might go down all at the same time. And if you have this, what will happen is you will lose connectivity. Just when a few routers go down, you will lose connectivity between DCs. And that would be a major outage. A lot of our customers will be affected and bad things will happen. Okay. So what are all the possible causes for errors? And this is not just about Microsoft, right? We routinely hear stories about how Google has had outages, Amazon has had outages, everybody, right? If you run a large public cloud, these things are going to happen to everybody. And they happen because of software errors, they happen because of configuration errors, they happen because of hardware failures, human errors, everything. So how do we guard about that? So at the very bottom, there are always two questions that you need to ask if you want to make your network reliable, okay? So the first question you ask is my network working as I designed it to work, okay? So that's the first question. Is the network currently working as I wanted it to work? And the second question is, if we make a change, a plan change, let's say I want to add a new router, I want to change some configuration, I want to decommission the data center, something like that. If we make this change, will anything break? Okay, so those two are the fundamental questions that you need to ask as a network operator. And there are two very different questions, okay? The first one talks about how the network is working currently. The second one talks about how the network will work after a hypothetical change has been made, okay? So why is this hard? Why is it hard to answer these questions? It is hard to answer these questions because, hold on 1 second here, I might have some audio problems. Hey, Kun, can you hear me correctly? Sorry.
Yes.
Okay, sorry.
I can hear you. Yeah, good.
Okay, sorry, I was having some weird echo. So let me know if you can't hear me. Okay, all right. So why is this hard? And the reason it is very hard to answer either of these two questions is because we have a very large and very complex network. As I already pointed out, we have hundreds of thousands of routers, hundreds of DCs. But more importantly, these routers comes from multiple vendors by necessity. They have very complex routing policies. For example, in various places in the world, we have to promise to keep the data within a certain region. And there is constant churn. Even if nothing else was happening, our routers keep going up and down. We keep adding new routers. Changes have to be made to update things. So there is a constant churn. Okay, so it is difficult for any one person to fully grasp what's going on. Okay, and obviously you cannot do any kind of realistic testing. This scale is too vast, and the churn is too high. So anything that you are trying to do is always going to be something that you cannot replicate clearly in a lab. Okay, so this is a little bit like space shuttle launch. This is what I like to tell people, right? You get to launch the space shuttle once, right? It is an extremely complex machine, and complex than launching a space shuttle. Okay, so let's focus on the first question: is my network working as I designed it to be? Right? Is it behaving as I intended? Okay. So now there are a couple of questions you have to ask here, and none of them are easy. So first question is, what is intent? So I designed my network to do something, but as any of you guys who have run a large network know, the intent always gets clouded in all sorts of documents. Oftentimes what happens is somebody writes a spec in English language or some other thing, and that gets implemented using, I don't know, Cisco or Sonic policies or what have you. And somewhere there is a disconnect. The managers or the planners of the network meant one thing, the network engineer implements something slightly different, and there is a disconnect between the two. So capturing the intent, figuring out what the intent is very difficult. Okay. Then there is a question of what is reality? What are we going to verify this intent against? And how can we efficiently tell whether the intent and the reality match? Now, fortunately, remember the previous slide, intent, reality, and how to match them. So these are the three questions, okay? Fortunately, the second question is actually easier to answer. So in a network, what is reality is very clear. At every router, the forwarding information base, the FIB of the router, is ultimately what's going to route packets, okay? So it determines the behavior of each device and just longest prefix match. So once you have all the FIBs, if you have a snapshot of all the FIBs, you're done. That's your reality. So fortunately, the second question is easy. The first question, as I pointed out, is very hard, right? Because somebody wrote some specs, somebody built something, and there is a mismatch between the two. But here we are going to cheat, okay? I'm going to not go focus on our WAN network. I'm going to tell you only how we verify intent and reality in our data center network. And in data center network, again, as the previous speaker pointed out, the picture is a little bit easier, okay? So we have essentially a variant of class topology, just like everybody else. We use shortest path routing, and we want some very simple invariants, right? So we want all pairs reachability. We want to make sure that all redundant paths are available. So if you take essentially the basic simple stuff, okay, such as locality of address ranges and the topology, and we combine it with some very simple desirable properties, such as all pair store reachability, and we want traffic to follow shortest path, then based on this, we can derive a set of contracts. And these contracts are what capture our intent. So our intent is derived based on the network architecture itself. Okay, and again, this does not apply to WAN, where the topology is essentially random and is dictated often by geographical factors and fiber availability. But within DC, things are a little bit easier, right? So FIB verifier is a tool that generates contracts based on what we perceive to be the intent of the network designers. It pulls FIBs from the routers and it verifies them, and it flags errors to network engineers. And today we run this continuously. We run this in our DC, and we run this in all of our regional networks, and we have found and fixed hundreds of bugs. You would think that in a simple network like DC and our regional network, which are very well structured, very well behaved, very simple configuration, you wouldn't find bugs. Nope, we find hundreds of bugs and we have fixed them continuously. What kind of bugs have we found? We have found software bugs. We have found bugs that cause RIP-FIB inconsistency. Hardware failures, that's just a given when you run a very large network. There are always going to be hardware failures, too many operational links down, and so on and so forth. There will always be operational drift. So for example, when there is a live site or when there is a problem, network engineers will go down and maybe one thing they did is they will shut down some BGP sessions. Then somebody forgets to bring them back up, right? So this can happen. And there is always churn, right? So we have found all sorts of problems. And we are continuously fixing them. So FIB verifier is one of the tools we use to guarantee that our network is working as intended. Okay, so now let's come to the second question. The second question, if you remember, I asked was, if I make a change, will it break anything, right? And so ideally, if we could do anything, what would we do? Before we make a change, we would make a complete replica of the network. And this would include all hardware, all software, all links, everything. And we would apply the change in the replica. And if it all goes well, we would deploy it in production. But obviously, this is too expensive. Okay, so money doesn't grow on trees. If I went and told my managers, hey, I want to make a complete replica of Azure's network, they're going to laugh. There is not enough money in the world to do that, right? But the key insight that helps us here is that most of the incidents are due to bugs in tooling, software configuration, and so forth. Okay, and most of the cost of the network is in hardware. So what do we do? And so what we do is we essentially build a high fidelity replica of the network via emulation. So we take the production network, which consists of the hardware, the software, such as the OS, and then the configuration that runs on top of them. And then we create a virtual replica by essentially virtualizing the hardware, right? So we keep the same topology, we keep the same software, we keep the same configuration, and we virtualize the hardware. So this gives us a very faithful copy of the network in which we can try things out. Now, of course, this is not going to catch the hardware faults, but that's okay because some faults are going to happen. We'll at least catch all the ones that happen potentially because of software and configuration, okay? So the thing to think about here is the analogy. This is a very cheesy slide that I show, but that captures what we're trying to do here is, astronauts, when NASA sends astronauts to space, NASA spends enormous amount of money to build extremely high fidelity emulators so that every single thing that you do in space can be thoroughly practiced, right? And so by the same token, Azure engineers use Open Network Emulator to practice complex, high-risk network operations. Okay, so everything they do is practiced very thoroughly, all right? And this is our typical workflow. So the hardware network engineer describes the change. It creates an emulated replica. The change is applied to the replica, and then we use a formal verification engine based on Z3, as well as some manual testing, and that allows us to do verify whether the changes succeeded or failed. And then any changes that are safe, we apply them to the production network. Otherwise, you can just iterate and fix whatever is broken, okay? I'm going to go very quickly over how the emulated replica is created. There is a SOSP paper that we wrote about this, and that has many more details. So there's a machine, we can call it the orchestrator. It pulls a snapshot of the production, and we basically spawn a bunch of VMs in Azure. The great thing about running a public cloud is you can spawn as many VMs as you want. And these VMs, we essentially create a bunch of containers. They're linked together with a bunch of virtual links using VXLAN tunnels to create the topology we need. And there's a management network that's connected to a console used by the operators. And then we use various VMs that run on these containers to essentially create an emulated copy of the network. And to an operator that is logged in through the jump box, everything looks as if they are connected to the real production network, okay? So it's very high fidelity. We can spawn very large networks very quickly. It's very seamless to the operator, the network engineer who's testing their changes. And we spend tens of millions of core hours per year testing new deployments and changes in Azure. And this is one of the critical gates now. If you want to make any change in Azure, you have to go through the Open Network Emulator. And we have avoided, we suspect, hundreds of potential sabotages by using this tool. Okay. In fact, what we do today is slightly more sophisticated. And the reason for that is even though we are Azure and we can spawn as many VMs as we want, spawning VMs is both expensive and it is time consuming. So what we do first is a two-step process. And this is called the Network Change Validation Service, or NCVS. So the proposed change is first run through a network simulator. Okay, so low fidelity. So this is just a simulator. We call NLS, Network Logic Solver. And the change is first tested in the simulator. If the simulator in the change fails in the simulator itself, that's it. We stop. Okay, then the network engineer has to go back and check why the change didn't work. All right. And this is, you can think of this as a quick and dirty first step test. Okay, that allows you to make sure that everything is okay before you take the more expensive step of spawning the full replica and testing your change in the Open Network Emulator. And then a pass fail, the same thing as before, right? So it's a two-step process, a cheap, quick check first that allows us to weed out many problems without having to spawn all the VMs. And then if you pass, then we spawn the full replica and check the change again. That's how we go. Okay. All right. So in summary, reliability of Azure network is our top concern. And we focus on two questions. Is my network working as expected? And for that, we have fib verifier. And the second one is, if I make a change, is that change safe? So NCVS verifies that any change is safe. So for network emulation, if there are many more details for network emulation, see our paper in SOSP 2017. For fib verifier, see our paper in SIGCOMM 2019. And there is a lot more ongoing work. For example, we are potentially adding hardware routers to the emulation. We are bringing emulation as well as formal verification to many other parts of networks and the network change toolchain. And we'll hopefully write papers about it in coming years. Happy to talk about that as well, if time permits. Okay. So the next topic is performance. And we are going to replace, we are in the business of replacing TCP with RDMA. And this is a little bit bittersweet for me. I did my PhD on TCP, and now I'm in charge of replacing this with RDMA in Azure. So that's actually quite fun. Okay, so just to set standards here, right? We talked about TCP in the last talk as well. Just remember that ARPANET started using TCP on January 1st, 1983, okay? And I don't know who's on call, but I suspect that many, many people on this call were not even born in 1983, okay? And it's just people like me and Kuntan, we are old and we have been around for too long, so we know all this. But there are many other of you, young students especially, who were not even born when TCP started, okay? So TCP is older than many of you, right? And TCP is not suitable for modern DC applications. It was designed for WAN, modest throughputs, very long round trip times, and data center apps need very heavy very large throughput, very low latency. And more importantly, we are Azure, we are in public cloud. What is our business? We sell virtual machines, we sell compute power, okay? So we can't afford to waste TCP, can't afford to waste CPU figuring out TCP's complex algorithms. So we need very, very low CPU overhead, okay? So TCP is not suitable for modern DC applications. We have tried. We tried fixing it with DC TCP, many different things, but ultimately, I think TCP needs to be replaced in modern data center. Again, the point that was made by the previous speaker as well, okay? And just to answer a little bit, go into why we need to do that. If a simple application is write a block of data at a local disk, okay, at a particular, from a local disk to a remote disk, what will TCP do? It will first burn CPU to read the data, packetize it. The data will go over the network, where it will be reassembled. If the packets are lost, they'll be retransmitted. TCP's congestion control algorithm will run. Many things will happen. Okay, so TCP will waste a lot of CPU and will add very high latency due to multiple steps where CPU is involved. Okay. RDMA, on the other hand, is far simpler. The application allocates a memory buffer, lets the NIC know about it. The receiver also has a memory buffer. The receiver's NIC knows about it. And then the two NICs handle all the data transfer. CPU is not used at all. Okay, so RDMA bypasses the host OS stack. That reduces the CPU utilization on the host. It also lowers the latency. Okay, and RDMA outperforms TCP by a vast margin, as you can see on this graph. Even at low message sizes, it achieves full throughput, and it does so with almost no CPU utilization. Okay, so the latency is also much lower, obviously, because you're not paying the penalty of transfers and stuff like that. Okay, so this is all good. However, RDMA is not loss tolerant like TCP. Okay, TCP was designed for wide area internet, where packet drops were a norm, right? Performance degrades if packet loss rate is even more than 10 to the minus 4, right? So how does one make a data center network this reliable, this drop free, right? So the analogy I like to give here is RDMA like a Formula One race car, okay? And TCP is like just your old family car, okay? Formula One race car goes very fast, okay? It will do amazing things, but you really have to know how to drive it, and you really have to have very clear roads. If there is any congestion at all, this is what happens, okay? Total disaster. So you don't want to do this in a Formula One racing car. You don't want congestion in a Formula One racing car. You don't want dirt on the road. You don't want bumps on the road. Your road has to be clean, no congestion. How are we going to do that? We do that with something called priority-based flow control, right? So an upstream neighbor is told to pause by a downstream router when the queue size reaches a certain threshold. Okay, so that makes sure that there is no packet drop. So if there is congestion starts building up, the network will simply pause. You will start building up an upstream neighbor, and then we will be fine. And this, of course, works, as you know, on a per priority basis. So while the blue packets are paused, green packets can continue. What does this ensure? This ensures that there is no congestion-based packet loss. Unfortunately, PFC can cause many problems when deployed at scale. Okay, one of the most famous things it can cause is a circular buffer dependency that can cause a deadlock. Okay, so our solution to this is to essentially minimize the number of PFCs that we have to generate. For this, we invented DCQCN. It's essentially a congestion control protocol that is implemented entirely in the NIC. So the sender NIC is called response reaction point. Okay, the switch is called the congestion point, and the receiver NIC is called the notification point. Okay, so the switch marks packets based on congestion, marks ECNs, and the receiver essentially sends back feedback, and the response point responds to this CNPs by reducing rate. So this is built into Mellanox NICs. It's very low weight, unlike the full TCP. By the way, this is a clear contrast here with IWARP. It's a very simple algorithm. It reduces PFCs by a factor of well over 1,000. Okay, and we have tuned it all the way from 5 meters to 100 kilometers. Okay, so in Azure we use RDMA not just within data center but also between data centers. So we have tuned DCQCN from just 5 meters, which is within a cluster or within a rack, all the way to 100 kilometers. That's what most of past several months we've been working on. Okay, and there are numerous other enhancements that we have done. We have tuned router buffers. We really understand how our ASICs work. We have constant monitoring to remove bad links. We have been tuning NIC transmit and receive pipelines. We have PFC watchdogs. And then we have developed RDMA eStats. We are working on streaming telemetry to collect data on how our network is working. Each of these things is worth a paper in itself. I'm happy to talk about some of these things in more detail if you want. Just wanted to keep the talk at a very high level here. Okay. The key takeaway here is today, majority of Azure traffic is now on RDMA. Okay. Not just inside DCs, but also between DCs. We have seen significant latency improvements and significant CPU savings. Okay, and we have already written a couple of different papers on that. In SIGCOMM 2015, we described DCQCN. 2016, we described some of our RDMA deployment challenges. We have written numerous papers in ConeXT and Hotnets on deadlocks and so forth. Cone has been involved in some of these papers. So again, happy to talk more, but this is the message to take away. Majority of Azure traffic is now RDMA. And of course, the future is all about SmartNIC, right? So far, we have been working primarily with Mellanox NICs. Going forward, we'll have our own. And now we are thinking of many different things that we're going to do. We don't necessarily always have to worry about PFC. There is potential to work RDMA in a lossy environment. many other things are possible, and we're always looking for improvements there. Okay. So with that, I'll conclude my talk. Thank you, and I'm happy to take questions.
Okay, thank you, Jitu. Thank you for a wonderful talk. So we have about 10 minutes. So Jitu, you just give the talk. Okay. So if any questions here?
Yeah.
If you have a question, you can just click the raise your hand, so I can mute you. Okay, so Jitu, maybe I start with one question. Yeah. Actually, you said we deployed RDMA and now moving to the next stage of Smart Lake. So can you brief a little bit on what the new features and or new applications of this Smart Lake? How do you think about this in-networking computing paradigms in the data center?
So we are definitely thinking about in-network computing, but from the SmartNIC side, the thing that excites me the most is it gives us a chance to collect much better telemetry than we can collect today, right? Some of the RDMA telemetry that is shipped today is kind of bolted on, right? With SmartNIC, RDMA will be a first-class citizen, will get much better telemetry. It also allows us to think about moving away a little bit from DCQCN to more sort of proprietary congestion control protocols. There is a bunch of work that has recently come out of Stanford and so forth that is very exciting in this regard, and we are looking forward to that. One of the things we have discovered, by the way, and this is again, perhaps this is a characteristic of our traffic, is that the traffic is very bursty. Okay, RDMA traffic is very bursty. Part of it, the reason is that there is no slow start. You start at full line, right? And a lot of flows finish very quickly, right? And typically, if you look at all the congestion control research, right, people focus only on long flows, right? So one of the things that we are working on now is a congestion control algorithm that is specifically designed for bursty traffic. And this is not just a congestion control algorithm. You also have to think about how you're going to tune your switch buffer to deal with this, right? Because ultimately the queue is going to build up on switch buffer, and if you want to prevent pause frames from going back, both the end host and the switch have to act together. So there is some very exciting work that we are doing. Hopefully we'll write about it soon on how everybody can work together and handle bursty flows much better. So the next step, of course, is lot of the new workloads, the AI workloads that are coming up, they have very different characteristics than the classic the classic disk read-write workloads that RDMA we have tuned for so far, right? And I think maybe CX will talk about it in his talk a little bit more, but those workloads have very unique characteristics, and there we have to see what we can do. So there are all kinds of interesting challenges that are coming up there as well.
Okay. So next question, Chen Chen. Oh, how can I?
Hello. Hello,
okay.
Can you hear me?
I can hear you. Yeah.
Okay, great. So very nice talk. So I have a question related to your work related to the verification. So you do the verification using network emulation. So it is okay, very efficient to find whether any configuration would be functioning correctly. But how can you verify whether the performance would be affected?
That's a superb question, and the answer is we are currently lacking in this area. So we do two things. One is that we are building some of these capabilities in the simulation, right? Now, in an emulated network, you can't always quite check performance because your emulated routers are not going to forward traffic at the same rate. They're going to have very different latencies and so forth. So one way is to trust the network engineer to do a little bit more sophisticated analysis, but that sometimes doesn't quite work. So what we do instead is we try to do this analysis in the simulated network where we have much more leeway towards doing this. And the second thing that we are looking at now is to add at least a few additional hardware components to an emulated network and check to see if we can do some performance studies there. But this remains one of the more unexplored areas. And in fact, you asked this question, I don't know whether you've seen examples of this, but we have seen problems like this in Microsoft, where there are no configuration errors as such. Everything looks fine. But when you put this in practice, the performance is not what you want. And then you discover these problems, unfortunately, only in practice. And so this happens sometimes. And I would love to have a solution that is as clean as verification is for checking purely reachability. Unfortunately, we don't have that yet. And so this is clearly an exciting area of both research as well as industrial practice.
Okay. So, Apnet, you are going to be her next question.
Yes. So I have a question about the emulator. So the assumption for emulator is the router vendors should release the image. In that case, the emulator can guarantee the high the high accuracy, right, for the emulation. Yes. So yes. My question is, if we know some vendors may not release the image, or maybe just to release a micro version of their image. So in that case, whether I'm just wondering whether Microsoft meet that case, or if you never meet that case, but other company wants to reproduce the emulator, however meet that case, do you have any thought about that?
So yes, so all of that is correct. This is indeed a problem. When we buy a router, we have made it a requirement that the vendor supply an image that meets certain criteria, and we are in the process of writing down formally what it means. Because obviously, whatever image the vendor gives, it's not going to, for example, it's not going to have the same data plane performance. That's just a given, right? So we have to define what it means. It has to support the same number of interfaces. It has to support all the routing plane functionality we need. So we are in the process of writing this down very carefully. Now, how do we enforce this? Some of this is simply because we are a large customer and we can tell our vendors what we want. Now, of course, this goes only so far, right? We have some old routers for which our vendors simply cannot virtualize, because these were produced using operating systems that are not as virtualizable as a newer Linux-based operating system, right? And there, unfortunately, we don't have much of a choice. What we sometimes do is replace it with a newer image, and this is obviously lower fidelity. So that's a continuous battle that we fight. The ultimate goal, of course, going forward, as you guys know, is we plan to run as many of a large fraction of our network on Sonic. And Sonic is obviously our own homegrown OS, open source. And the Sonic pipeline is such that it always produces a fully compatible, fully functional virtual image when it produces a hardware image. So hopefully this problem will then slowly go over time. But for now, it is a problem, and we manage it the best we can.
Thank you. Okay, so Chen Xiong, you're going to ask the next question.
Yeah, so hey, Jidu.
Hey, how are you? Good to see you.
Yeah, good to see you. So you mentioned that basically you now can do DC to DC RDMA, right? That's really great news. I think everyone in the industry should be exciting to hear that. Can you just tell us a little bit that do you still count on the PFC to do that? That does it mean that actually you now don't count on the 3 meters is a limitation of PFC?
Yeah. So yes, we are doing long haul PFC, and we are using. Remember that this is essentially a tier 2 level where we have deep buffer switches, and we are encountering obviously some problems. The extra buffer is DRAM; it's off chip, doesn't have essentially the same performance as on chip buffers. So all those issues are there. But at the same time, the customer, the underlying applications itself make sure that the amount of traffic that goes over tier 2 is not as high, right? Because what we primarily use RDMA for in Microsoft today is essentially disk traffic. And while we don't always do co-location, we try very hard to make sure that your disks are not in some other random data center, right? So combination of two factors. Yes, we have deep buffer switches. Yes, we have some problems, and we have tuned DCQCN to the best of our abilities. But we also bank on the fact that the traffic volumes that cross tier 2 are comparatively lower than the volume that stay within the data center. So the combination of that all these factors together makes it work well. But this is an experiment in progress. As I'm saying this, maybe tomorrow we'll discover some problem. This is work in progress very much. And this is absolutely cutting edge. I'm not minimizing the difficulty of doing this.
Okay, cool.
Okay, great. Thanks you again for the wonderful talk. I think it's time is going to be late in your time, right? Okay.
Yeah.
So
thank you.
Yeah. Thank you.
Thank you, Kun. Okay. Thank you. Bye.
So let's welcome the next speaker, Chen Xiongguo. I think most people also familiar with Chen Xiong. He is a director of ByteDance's AI lab now. Before he joined ByteDance, he was a principal researcher at Microsoft Research, and also a principal dev manager in Asia. He recently working on data networking and also machine learning systems. I think he was the pioneer in data center networking, and did a lot of work on all aspects in the networking, in data center networking. He is going to talk about accelerating distributed CNN trading with ByteDS. So welcome, Chen Xiong, your time.
Okay, thanks, Quinn. So let me share my screen. Yeah, can you guys see my screen now?
Yes.
Okay, can you see the full screen?
I think you need to switch the screen.
No, I'm doing the two screens. Let me just using one.
So you just click the display setting and.
Is it working? Or it's
no. The display setting. You go to the menu. There's going to be a display setting there.
Let me just unplug that one.
No. Okay.
How about this time?
Okay. It works. Yeah. Good.
Okay. Yeah, so let me get started. So this talk is about the accelerating distributed deep neural network training. It's ByteDS. I'm Chen Xiongguo. It's a pleasure to be here. So this is the outline of the talk. So basically, first I will talk about some DNN background, and then I'll be focusing on the three technologies that we have introduced in ByteDS. And so those three technologies are basically RDMA for accelerating the DNN training communication, batch scheduler for better overlapping of computing and communication, and summation service, which is a new way of partitioning the how we do the parameter update. Finally, I will do a brief summary. So this basically is a figure to show, starting from when the transistor got invented, how my bias pick of several of the most important systems, communication and computing systems, right? So as we can see, there's a kind of clear interaction among application systems and hardware. So we system builders take inspirations from the requirements of applications, and also it's kind of limited or constrained by what, or enabled by what hardware can provide. Right. So this is the x-axis actually is the timeline, right? And those are kind of systems and build around the timeline. And I think now is the time for building the machine learning systems enabled by the specific ASICs and GPU and very fast networking fabric, right? And also it's kind of inspired by the machine learning enabled applications. So this figure shows the G-flops per dollar, and also the number of flops per clock cycle can carry out. As you can see, the the cost per G-flops actually is degrading, and the number of calculations can be carried out in one CPU cycle is also increasing. So roughly on the same slot. So which means that using the same amount of money, you can buy, say, tens of thousands times CPU computing cycle in about 10 years. So this is great, right? And the trend is still continue. And but currently this is a kind of machine learning now. It becomes very important. But currently we got a problem, right? So the left side is the number of flops per CPU clock, right? It increases around several hundred times in 10 years, right? But on the right side is the model size, right? So it basically in 5 years the model size actually increased 10,000 times. The ResNet 50 got 25 mega parameters. The latest GPT-3 got 175 billion parameters. So this is it's huge. So apparently we have a problem, right? So what really those DL models look like? So here we give some examples. They look quite different. The left side is AnexNet. The right side is the BERT large model. but they are really quite similar in that they are all those kind of called deep neural networks. So it's basically they are building layer by layer. So each layer has a kind of a different or similar operators. So those operators typically are big matrix calculations using float point. So here we see some details of those DL models. Right, so it's here you can see that basically the number of flops carried out by each model actually is kind of huge, right? It's typically it's tens or even hundreds of G flops just carry out one forwarding calculation. And the time needed to exchange the parameter, right? Spans from 8 milliseconds to 60 milliseconds. So that's just for one round, right? So and on the ideal communication condition, which means that you simply use all those 100 gig links at the full speed, which typically it's not possible when you are using, for example, TCP, right? And those training actually shuffles a lot of data, right? Based to converge. Typically, tens to hundreds of terabytes. Depends on whether you are using IP16 or IP32. That's quite a lot of data to be shuffled. So the training process is actually it's kind of quite a mechanical, iterative process, and the model needs more and more computational power. And as I have said, we need a very good network to shuffle a huge amount of data. So let's just look at one, iteration, see how it works. So it's typically called a mini batch. So in a mini batch, so what we do is that basically we prepare a bunch of data called a batch of data, right? And then we feed that data into the neural network, and the neural network will carry out a forward calculation, or it's called a forward propagation, right? Along from near 0 to near, for example, in this case is near n-1, right? This is the forwarding. So the forwarding part actually calculated a loss, from the input. Okay, then we'll do the backward. So the backward is using the reverse order, starting from the last layer n-1. Then, from the last layer to the first layer, gradually we calculate the loss, the gradient of the loss, along the way. This is the backward propagation. So the backward propagation algorithm actually is the core algorithm of DNA training. So after the backward propagation, we got the gradient of the parameters. Then we do the in this case, we show is that we do a gradient update using, for example, push to the parameter server. Then the parameter server will aggregate the parameters, the gradients from all the workers, and then do a parameter update running optimizer. Then the updated parameters will be distributed to the workers. So that's essentially how it works. So there are 3 parts, forward propagation, backward propagation, then parameter update. Then this mini batch training is repeated, using all the data. So once all the data is used, then this is called epoch, right? Then the epoch is repeated again. So until the model is got converged. So this is roughly, if you are using just a single GPU or a single training machine, so this is how it works. Of course, this is if I choosing using a single machine, it will be very slow, right? So what you do is that you use distributed training. In this, here we mainly talk about this data parallelism model to increase the training speed. So now two types of distributed framework for the training. One is called parameter server on the left side. On the right side is the wall reduce. So they look quite different, but actually they are not that different. So it's a basic, what they do is essentially it's the same. It's the workers reading the data and calculate the gradients, and then the workers exchange the gradients and do the update of the parameters. So in the parameter server uses additional server to store the parameter, to store the gradient and carry out the parameter update. And using wall reduce, there's no such thing as a parameter server. It's every node is the same. It's a kind of it's more homogeneous. But we'll see that our technique, what I'm talking about, will actually be applied to all of them. The technologies that I will be talking about, with 3 of them. So the first one is RDMA. So G2 actually already paved a perfect background for RDMA. So I don't think that I need to repeat that. So essentially, RDMA is kind of a uploading technology and it can be used to accelerate computer communication without introducing additional overhead to the CPUs as the TCP does, right? So that's so that's the main part of RDMA, right? So yes, of course, RDMA can reduce the CPU overhead to almost 0, and to reduce the the communication latency to almost to very close to several microseconds, right? So if there's no contention or congestion, right? So this is kind of the key benefit. right? So so here I'm mainly focusing on how we use RDMA to accelerate the the distributed DNN training. Right, the vanilla RDMA implementation actually means that okay, you just replace each TCP connection with RDMA connection, right? So that looks very simple, but it's also quite naive, right? If you do that, the performance you got actually is not quite good. As we can see, basically for large models, even using vanilla RDMA actually can outperform TCP. For example, the vanilla RDMA implementation actually can outperform TCP when the model is VGG, right? But for rational inception, actually, vanilla RDMA actually is worse than TCP. So then what do we do? So we actually introduced several technologies or techniques to improve that upon that, right? The first is actually try to leverage the characteristics of DNN training. As we can see, right, the DNN training is a kind of a iterative and repetitive process, right? So when they need to shuffle data to exchange the tensor, the gradients, it's a kind of fixed pattern. So which means that you can always reuse the buffers of the previous iteration, right? So this is what we do, right? So we, as you know, right, RDMA needs to do the memory registration, but because this is a very repetitive process, right? You don't need to register every time when you need to send a buffer, you need to register at memory. So you don't need to do that. You just need to register once and use it, and then use that buffer again and again and again, right? So that's actually save your memory registration time. All right, that's and that will be much faster because the memory registration can take, in the worst case, can take a milliseconds. And the second one is that okay, when, for example, when you're using RDMA write, you need to let the peer know that which address that you will let the peer to write to, right? So that this is you need to do this notification. Again, you can leverage the repetitive property of this DMA training. You just need to notify the peer once, then that peer knows that okay, last time I can still use this address and token, and it's safe to do that. So this receives one RTT from the notification, right? So this is the second one. The third one is that okay, for TCP, typically you need to do the memory copy, from user's buffer to kernel, and sometimes you need to several times of this kind of copy, and it takes quite a lot of time. So we took the effort of making the zero copy RDMA data parse. So this is I think basically this is actually it's quite a lot of engineering work of doing that. The first one is that okay, we run into quite several slow receiver symptom. The slow symptom is the case that when the RDMA NIC it's got internal congested, it will not be able to deal with the incoming traffic, and so it will send a pulse out to the upstream switch to slow down. So this typically is very bad because typically we don't want to see the PFC. A lot of PFC pulse frames, right? Because it will cause a lot of damages, as G2 mentioned in the previous talk. So we actually identified several of these things that can cause can cause this slow receiver symptom. The first one is actually interesting. So we once used this RDMA loopback traffic. For internal RPC, we found that actually because this internal traffic actually needs to go through the PCIe to the NIC, and then from the NIC back to the server memory. Actually, then it competes with the incoming RX traffic. So it causes the internal incast. So the best way is that to avoid that, because this is not really good, because they compete with the PCIe bandwidth. So it's what we do is that we just need to do not use RDMA loop back traffic, right? So you can just use, for example, share memory to do that. Right? This is the first thing that we try to avoid. The second is that for RDMA communication, it's better to use page-aligned buffers. If you are not using page-aligned buffers, you will got a problem, and your pipeline will got severely slowed down. So we just observe that this is the case, but and we believe that this is something to do with how the NIC works, but we don't know the full details. And the last one is that we found is that the RX and the TX cannot be fully duplex, right? So it's typically, if you have something that need to the sending and receiving, the reading and writing at the same time, sometimes you got a problem. And also, for the when we are sending out a walkie, it's better that you have one scattered gather element per RDMA, right? Or so and if you have multiple SGEs, and you got slow down the pipeline. So again, this is what we have observed. We still don't know the full details on why is that, but we just figure out a way to work around. So this is all about what we did in RDMA. So the second is a piece of work is we call the batch scheduler. So batch scheduler is also something that we did try to leverage how the DNN training works. So here we show a graph that basically shows how one iteration for the DNN training. So here this graph we show it's the back propagation of the previous iteration and the forwarding part of the next iteration. As I've said before, is that basically the backward start from the last layer and forward start from the first layer. So this is a kind of a reversed order, right? So and so when we for example, in this case, once we finish the BM-1, we will push the gradient, then we'll pull the gradients again, right? And the parameters we got for BM-1 will be used by F1-1. So this is basically the dependency graph, right? So the dependency here is just shown by the arrows, right? So it's quite easy to understand. Apparently, if you look at this figure, you'll immediately realize that okay, the communication order actually is wrong, right? Because you will push, for example, the last layer of parameter first, right? But this last layer of parameter will be used, very late. But on the contrary, the first layer of parameter will be used first, but it will be communicate the last one to this kind of communication, right? So yeah, this actually shows that basically an example, right? How the push, pull, and also the forward and backward and forward actually works, right? And so basically, priority scheduling actually will make things much easier. It's the right way to do it, but the natural way to do it actually is FIFO. It's easy, but it causes this priority inversion problem. Okay, well, so what do we do? So what we do actually is quite simple and intuitive, right? In order to achieve this priority scheduling, So we partition the tensors into small pieces, right? Because these small pieces of tensor partitioning give us the chance to do preemption, the transmission preemption, right? So it's basically, compare with the FIFO and also the way we do the priority scheduling plus the tensor partitioning. So in this case, we can see 44% speed up, right? This is quite significant. And actually, there is more than that. So we have shown that basically the tensor partitioning actually is a quite good strategy, and it actually reduces the NP hard problem to a very easy problem, right? So if you're so for example, if you don't do tensor partitioning, but you still want to do the priority scheduling, so what you are dealing with is actually a hard problem. It's hard, and also it's very hard to balance that basically to make things to get the best optimization for that. So tensor partitioning actually was first introduced in P3 and TikTok into 6ML papers. So here we actually show that using the tensor partitioning and priority scheduling, so we can achieve the communication optimality on certain kind of assumptions. So I will do not cover the details here, but if you guys have interest on that, you can refer to our SLSP paper in 2019. Batch scheduler actually does more than the tensor partitioning and scheduling. So we provided one unified scheduler for all the training frameworks, including TensorFlow, PyTorch, and MaxNet. Right. So this actually is quite good. Is that we try to provide a generic scheduler. So no matter which ML framework and the communication method we use, and this looks very easy because, for example, if you look at how the DN training works, right? So all the frameworks should support the same, same graph, right? Graph computing, right? How can that be difficult? But in reality, it's really very, very challenging to do that. It's because all those kind of different frameworks have different communication mechanisms. And for example, the TensorFlow actually is a kind of a declarative engine, and PyTorch is kind of imperative. And also both TensorFlow and PyTorch got this global barrier between iterations, which actually eliminate all the benefits of overlapping the computing and the communication. I will leave the details to the paper. The last one I'll be talking about is the piece of work we call the summation service. So the summation service is a service on how we do the parameter update. So this is it is actually a very generic service, but I will use parameter server as an example to illustrate that. So in parameter server, the optimizer is in place on servers, right? So this actually leads to two problems. The first is that the parameter server actually is not a very generic implementation. And the optimizer update on server requires the framework specific implementation. And which means that, okay, so even if you have a very good, for example, MaxNet parameter server, it cannot be used by any TensorFlow worker, because it's simply they are using different frameworks, right? So this is not possible. The second is that the parameter servers typically are CPU based, and we found that basically using CPU based servers and the optimizer update cannot match the the 100 gig network bandwidth. This is because the CPU is the bottleneck to run the optimizer, right? So and the optimizer it's kind of very the computation intensive. It needs to run the parameter update algorithm and update all those kind of parameters. The parameters, as I said, it can be tens of megabytes to even several hundreds of megabytes to several gig to even bigger, right? So as I said before, GPT-2 got GPT-3, GPT-2 got 7.5 gig billion parameters, and GPT-3 is got even bigger, 100 times bigger. So here comes our observation. What we have found is that we can divide this optimizer update into two parts. We use the CPU servers for gradient summation, and using GPU for a parameter update. So this is because the CPUs, even if they are not fast enough to run our optimizers, the CPU actually is very good at doing the data summation. So this is because the summation of modern CPUs can be optimized using the OVX instructions. So yeah, so this basically this is a key idea of what we do. And here is some explanation, the difference between a parameter server versus what we do in BadPS using summation service, right? So it's essentially this is basically this is how we partition the calculation, right? So the server only the servers only sum up gradients, and this calculation is a kind of framework independent. It's generic. Now, because what it does is actually very simple, right? They give a bunch of gradients, and the summation server just sum them up, right? So that's intuitively very simple. And the heavy optimizer update is now performed by GPU, and GPU, of course, is good at doing that, right? So to me, this is a kind of perfect, computation partitioning strategy, right? So now I'll introduce some, experiment result. So we have a, RDMA Rocket V2 network. It's for bisection bandwidth. We built this network several years ago. It provides full 100 gig to the server with full bisection bandwidth. And for the servers, they are the GPU cards are V100, so each server has 8 of them, and and the benchmarks we are using here are those quite famous. The DL models, ResNet, BERT, Transformer, GPT-2, right? And the metrics we care here is, of course, because BadPS actually does not change the training. So for example, the convergence, this kind of thing does not change at all. So the metric here we use is simply the training speed. That means that, for example, how many images that you can process, how many language tokens that you can process. And well, this is an experiment that we use 256 GPU cards, and compare with without the BadPS. So this training can take quite a long time. In this case, is more than 2 weeks. And BadPS actually can reduce the training time significantly, right? And this case is a video classification, and the model is ResNet, and it's essentially it's an image classification. So essentially, you take a video you do the sampling and turn that into the images, and then feed the image into the model. And again, you can see, the BAT-PS almost achieve perfect scaling and much better than the baseline. So the critical is that actually the ResNet actually is a very good model for communication optimization, because the ResNet model is more computation heavy, right? Which means that the bottleneck, most of the time, the bottleneck actually is on the calculation or on the computing side, not the communication side. So, but even for this model, basically BAT-PS is doing much better. And this is this is quite a busy slide to show the scalability, right, of BAT-PS along the line of different different of models, right? For example, we compare with ResNet with using TensorFlow, MXNet, and also running PyTorch using a GAN model, and also Transformer, BERT-NURGE, PyTorch, GPT-2, etc. So the thing is that by using BAT-PS, we can see in all the cases it's performing much better than the private solutions. Right? In some cases, it even achieves this kind of linear scaling. Right? Okay, so let me try to summarize. So in BAT-PS, so basically we try to accelerate the DN training using 3 techniques, right? It's using RDMA for communication acceleration, right? By offloading the CPU from carrying out the transport layer protocols, right? In batch scheduler, we try to optimize the computer communication overlapping, so to build a better pipeline, right? So once you are doing the try to overlap the computing and communication ideally, right? So that's so once you do that, and you kind of will increase your pipeline efficiency dramatically. The third part is the summation service. Is a way to do better computation partitioning, right? So this way, if you do the partitioning right, you can reduce your total computation time, right? In our case, is that we just let the parameter servers to carry out the very simple gradient summation, and to leave the more heavy lifting parameter update to the GPUs. So as I said, there are quite a lot of opportunities in machine learning systems. Right? So I believe that in the near future, we will need to build this distributed parallel HPC computers. So it's similar to the previous HPC computers, but it's kind of tailored for the machine learning traffic model. And we probably will need to do the scale out, scale up. But no matter what you do, the most important thing is actually reduce cost. So the current model of using machine learning actually is very expensive, right? So you can build your networks with more and more parameters, but the cost, but the damage it causes is that you will need to use much deeper neural networks to do the serving. Typically, does not work out. Because computing is not free. So I think this actually is the single most important thing that we need to address later. Right? Basically, as the models are going bigger, how to train them fast enough, and most importantly, how to serve them cheap enough. I think that this is quite the right time and to work on is the machine learning system. And as you can see, the system that the model that we are building is quite preliminary, compared with the real world intelligence. Right? So it's something that I think it's need more people to work on. So with that, I will stop here, and yeah, this is some advertisement. Yeah.
Okay, great. Thanks, Xiong, for the wonderful talk. And we have time for several questions. If there are any questions here, please raise your hand. Okay, you too. Let me find.
Hold on.
Okay.
Can you hear me? Okay,
yeah,
good.
we can hear you. Yeah.
Okay, Chungchun, very, very good talk. Very interesting. Really liked all the technical details. So I have a high-level question, though. Since you are building this system from ground up, right? You potentially had the option of evaluating the cost-benefit trade-off of using RDMA versus something like DPDK from get-go. So do you feel that you should have done that? Why didn't you do it? Why not go with DPDK? Why go with RDMA? Because unlike public Azure, right? Yes, you're trying to save CPUs, that's for sure. But as you said, your main target here is GPUs, and you could have potentially made do with DPDK, or that was never an option. Any insights on that?
Yes, to me, it's never option. So because there are several things, right? So it's every GPU server does have at least 2 sockets of CPUs, which means that typically we still have maybe have near 100 cores, CPU cores. But those cores are not idle or free. So typically for DN training, we need to do data pre-processing. And also for a lot of times that we use this spare CPU cores for parameter server, right? And so those are the things that the CPU cores can do. So this is the first argument, is they are not free. The second is that they are not. The second is that I didn't do the experiment. That I believe that it's not sustainable, right? So using so typically for 100 gig you still need to burn several cores, and also if you compare I believe that RDMA can still beat the DPDK in terms of latency and throughput. Especially next stage we'll move to 200 gig. And if you look at how the NVIDIA builds their SuperPort, that's basically eight 200 gig NICs. Right, so I don't know how if without RDMA, how DPD can handle that. Yeah.
Okay. Thank you. That was great. Thank you.
Yeah, I think at one point for the DPDK is actually we lack a transport, maybe quite a reliable transport for DPDK. Maybe that's also issue.
I believe someone is building some TCP on top of DPDK.
Right, sure. But there is still TCP. It have a very deep stack, so it's still have the problem that you mentioned.
Yeah.
Okay. I think there's another hand raised, but I didn't say it. If you want, okay. Chen Yang.
Yeah.
Sorry. I mute you, but I try to. Yeah. Please, I press it now. Yeah.
Okay, thanks for your talk. I'm quite interested in the RDMA evaluation. We have a simple question about if they are both inflow and outflow work in simultaneously, and I think the performance degrees. So could you explain more about why? I'm sorry, I'm kind of catch up with the reason. Could you explain more about it?
Hi, Yang. I didn't hear you well. So can you repeat your question? And also, can you let me know which slides you are talking about?
Okay, so in the RDMA evaluation, the duplex performance.
Oh, let me
Okay.
see. Let me evaluation. Duplex. You mean this one?
Yes. So the problem 3 is I still do not understand why it happened, but we facing this problem in our experiment.
Which problem is problem 2 or problem
3?
I think the problem 3.
Yeah.
He is pitching why X and TX are not duplex in current RDMA.
Yeah, so that's our guess. Is we didn't got confirmation from well, I need to say the leak we are using is Mellanox. From Mellanox, we also don't know the reason.
Okay.
Yeah, maybe we'll have a Mellanox guy here. But anyway, yeah.
Okay,
I guess it's a general got the effect of it.
Yeah, I guess
Okay,
there's some complexity within the pipeline which prevent them doing this. And that's just my guess.
Thank you.
Okay. So Wang Shuang?
Okay, can you hear me now?
Yeah,
Yeah.
I can hear.
Thanks, Dr. Gore, for the nice talk. I have one question about BetPS. BetPS chooses parameter server architecture because, as the document in GitHub said, the PS communication pattern is better than ring or reduce. But as far as I know, ring or reduce is widely used in many companies. Because people find parameter server, the performance of parameter server architecture is worse than ring or reduce. So what do you think causes a gap between the theory and the practice? Thank you.
Yes, this is I think this is a really great question. So it's, that's also our observation. So the world is state art. If someone wants to break a record, typically they use word reduce, especially some kind of from NCCL plus, for example, HORO. So in in all the cases, the word reduce is used. I think there are several reasons. The first is basically Reduce got several quite good implementation, especially Nico, right, and Horo, right. So and why PS did not catch up? I think PS is catching up, right? If you look at that PS, it's it actually it's a kind of a lot of engineering work. I don't think that it's quite a lot of magic here. It's just starting from the theory, we are convinced that you will do things if we do things right. Actually, parameter server can be 2 times faster in terms of communication compared with word reduce. So this also is there's no magic in the theory. It's because the PS uses more bandwidth and provided by the parameter server. And also, I think now one additional reason so why PS did not do well is because previously without this tensor partitioning, the communication of pull and push they cannot be overlapped. So so the only time that actually when you be able to do the to do the pull is that the push has been done. So which means that even if you are doing the using the parameter server, if you are just doing this unidirectional communication without the full pipelining, right? The best you can do is just you can get from like something like using word reduce, right? So I think those are just several of my shorts. I'm just wondering whether that's enough to answer your questions.
Okay, I got it. Thank you.
Okay,
No.
thank you. So I guess we're just on time.
Yeah.
Chen Xiu, are you in Seattle or in somewhere in China?
Oh yeah, I'm in Seattle. Yeah.
Okay,
Yes.
okay, thank you. So it's going to be late your time. Yeah. And
Nice.
so yeah, thank you for your talk again. So with that, we conclude this session. I think it is also the last session in the morning. So the after morning going to start at 1 o'clock p.m. Thank you, everybody. So let's meet in afternoon.
Yeah, thanks, Quinn, for hosting the talks. Yeah, thank you. Thank you, everyone.
Thank you.
Bye.
Thank you, everybody.
Okay. Hello everyone. Can you hear me?
Dear King, are you mute yourself? I can't hear your voice.
Okay. How you cannot hear me? I'm not muted. One sec. How? Okay. Can someone raise hand if you can hear me? Okay, good. So Marius can hear me. Thank you. Okay, so welcome to the Apnet. Thank you very much for attending. So I'll be chairing this session, and the first speaker of the session is Marius. And Marius was a PhD student at EPF, where working with Edward Bognion, and then he just defended his thesis and will be joining MSR Cambridge as a postdoc. His research focuses on data center systems, specifically on microsecond timescale remote procedure cores. And he's interested in improving the tail latency of network systems by rethinking both operating systems, schedulers, and networking transport protocols. And Marius interned at MSR, Google, and CERN, and he's also an IBM PhD fellow, and he's going to be applying for academic jobs at the end of the year. So without further ado, Marius, let's get started. So Marius, can you share your screen?
Yeah, let me try to do that.
Okay.
Okay, so can you see my screen?
Yes, I can see your screen.
Great. So hello everyone. Thank you very much for the introduction, Gun. And today I'm going to talk to you about tail tolerance systems and how to systematically approach tail tolerance as a design principle. This is work done with my advisor, Ed Bugnion at TPFL. In this talk, we will focus on latency critical data center applications. So we only consider applications that run inside a single data center. And in such a setup, latency is a very critical metric, but also a very challenging problem for the following reasons. The first one has to do with the economic aspect of latency. So there is a very strong economic aspect of latency, and users are expected to stay engaged more in a system that is responsive as opposed to a laggy one. So latency translates to revenue stream. For example, James Hamilton in his article about the cost of latency mentions that a 100 millisecond delay in Amazon dropped sales by 1%. The other interesting thing about data center systems is that nowadays we're talking about microsecond scale computing. So the infrastructure that we have inside the data center can deliver packets or even serve applications in microsecond scales. And the problem is that existing systems and networking infrastructure and networking protocols were not specifically designed for these time scales. So systems have to adapt to this new time scale. And the last part that makes the problem much more challenging has to do with the way existing data center applications are structured and deployed. And this is the large fan out and fan in communication patterns that these applications follow. As you can see here in this figure, I show you the microservice communication pattern for Amazon and Netflix. And the idea here is that the initial client request is broken down to several sub requests that are served by different parts of the infrastructure. And the latency of the initial request is determined by the slowest sub request. So in this case scenario, we have the so-called tail at scale problem. Despite these challenges, we need to design and build low latency systems that can also provide tail latency guarantees. And let's try to understand the latter statement. To do so, we need to understand how system behaves in terms of latency. And for us, the RPC latency, so the latency of a system that serves incoming request, is broken down to the communication delays, so the delays to send and get back the reply,
the queuing time on the server side, and the service time of the actual request. And if we abstract away the communication and the system overheads, queuing theory gives us the latency profile of a system across different loads. So in this figure, you can see a latency versus load graph. So on the y-axis, you can have the latency at a certain latency percentile, and on the x-axis, it's the achieved load. And we see here that systems follow this hockey stick curve. So as the load increases, latency also increases. And people working on latency critical systems know this behavior, and they have been trying to move this curve in order to achieve better results. One approach to move this curve is to try and push it more to the right. And to do so, we need to reduce the system overhead. So a typical example of such approaches is data plane operating systems and systems such as X, where they manage to reduce the system overheads and achieve much better throughput in terms of compared to vanilla operating systems such as Linux. Another approach to achieve better results is by moving this curve lower. And this means that we can achieve better latency results, but this time because of better scheduling. And another example of such a system is Zigos. So Zigos achieves better results compared to X because it makes better scheduling decisions. The problem, though, that all of these systems approach latency as a plain metric that they report when they evaluate the systems. And let's try to understand what I mean. A typical way of comparing two systems is picking a specific load level, for example, at 80 or 90% load, and then comparing the tail latency at this load level. So here, obviously, the orange curve is better than the blue one because for the same load level, achieves better latency. However, in most cases, the deployment scenario is different. Data center operators define a certain latency SLO, for example, 500 microseconds at the 99th percentile latency, and they expect the system to behave within this SLO. Obviously, this SLO cuts the latency curves of different systems at different loads, but this has to do with the efficiency of the implementation of the equivalent systems. Our claim, though, is that since the systems are expected to perform within the SLO, we shouldn't focus on what happens beyond this SLO, but instead focus on predictability. So a tail tolerant system is one that predictably performs within the service level objective that has been defined by the data center operator. In this talk, we introduce SVEN, that stands for SLO Violation Eliminator. So SVEN is a system that performs SLO-aware RPC admission control, and it does so in an application-agnostic manner. Also, SVEN leverages the advancements of in-network compute and programmable switches to perform this task in the network. And also SVEN is orthogonal to any scheduling decision that the system might already have in place. So for the rest of the talk, I will present SVEN's design principles and some of internals about its implementation. Then we will see how SVEN performs in action during our evaluation. And finally, I'm going to close with some open questions regarding SVEN, but also tail tolerant systems in general. The basic idea behind SVEN is trading throughput for latency predictability. So as we saw in the figure before, we'd rather have a system that does not serve the maximum throughput that it could potentially serve, but instead consistently perform within the SLO. And the way to do so is to drop requests that they are likely to violate this SLO. And this means that when the client sends a request and this request goes through, it's highly likely that the request will come back in time. And for the requests that are dropped, then clients receive an early notification, which is an application of the end-to-end argument, because clients know that this request is dropped because it was about to violate this SLO, and they have different choices regarding this request. One choice is to ignore it, and because they can navigate this latency versus completeness trade-off. Think, for example, an application such as web search. And in these cases, a faster response is much better than 100% complete response. So better never than late. The other choice that clients have is to retry the same request to another server, expecting that the this request will come back within the SLO. So when designing Sven, we set the following design requirements. The first one is we wanted an application that is, we wanted a solution that is application agnostic. So we didn't want to configure Sven specifically for different applications, but we wanted this to perform in a completely application agnostic manner. The second one was that we wanted to have a zero added overhead on the server side. And the last one was that we wanted to have a proactive design. So avoid canceling requests that have already started being processed on the server side. So now I'm going to describe how we fulfilled those requirements one by one. And the first one is the application agnostic aspect. So we decided to implement Sven inside the transport layer. So we looked at the stack and we decided to put Sven at the layer below the application. To do so, we need a transfer protocol that exposes the RPC semantics, because as we said, we want to do RPC admission control. So we used RTP2. RTP2 is a transfer protocol for data center RPCs presented on ATC in ATC 2019. And RTP2 stands for Request Response Pair Protocol. RTP2 exposes those request response pair abstraction to the endpoint at the network and breaks the traditional point-to-point RPC semantics. So RTP2 allows a client to get back a reply from a server that is different than the one it initially contacted. And also, RTP2 is designed specifically for in-network policy enforcement. So now I'm going to walk you through a packet exchange for a multi-packet request and a multi-packet reply on top of RTP2, because it's important to understand this mechanism since Sven depends on it. So in this figure, we have a bunch of clients that want to communicate with a bunch of servers. And in between, we have a middle box that implements some policy. You can think of this middle box to be either on hardware or software, and implementing any kind of policies such as load balancing or firewalling or application level steering, etc. So initially, the clients send the first packet of the request to the middle box. And this packet can either contain the entire request if it fits in a single packet, or it contains only the first part of the request. Then the middle box picks one of the servers based on the policy it implements, in this particular case, S1. And then the server notifies the client that it's ready to serve this request. The client sends the rest of the request directly to the server, bypassing this middle box. And the server now serves this request. Once the request is over, the server replies back directly to the client, again bypassing the middle box. Also, RTP2 uses application-specific feedback messages from the servers to the middle box that are sent from the server to the middle box at the end of each request. And we're going to see how we leverage these messages in Sven. So RTP2 provides the right abstraction for Sven since it exposes these request and response pairs. But not only that. Since RTP2 is designed for network policy enforcement, we can implement Sven as an RTP2 policy and use programmable switches for that. So the servers won't be modified or loaded with more functionality, and Sven will run entirely in the network. So Sven's functionality depends on a middle box that implements this SLO RPC admission control. And this middle box has two responsibilities. The first one is to estimate the RPC latency distribution, and based on this distribution, to reject requests that are likely to violate the latency SLO. We split these responsibilities between the control plane and the data plane. The data plane is in charge of performing the latency measurements and dropping the actual requests. And the control plane is in charge of setting the drop rate. We implemented such a middle box on a Tofino programmable switch, and we ran experiments with this. Now let's try to see what the data plane, how the data plane is structured. And the first task of the data plane is to estimate the latency of the latency of the RPCs that is observed by the clients. And to understand how this is done, I'll bring back the RTP2 packet exchange. So the data plane takes a timestamp for the rec0 and the feedback packets that it receives. And the difference between these timestamps for the same RPC is a good proxy for the RPC latency observed by the clients. Obviously, we cannot keep the absolute latency values in the data plane due to space constraints, so we can easily implement a simple latency histogram in the data plane. The other task is the actual RPC admission control. So the data plane probabilistically drops incoming requests based on a drop rate that is set by the control plane. Once the request is dropped, the data plane sends back an early reject to the client to notify that this request was actually dropped. Now let's take a look at the control plane. The job of the control plane is to set the target drop rate. The only input that it takes is first the target latency SLO set by the data center operator and the current latency estimation from the data plane. It runs periodically and it updates the data plane with the target drop rate. So if the latency SLO is about to be violated, the drop rate should be increased. Otherwise, it should be decreased. We implemented a very, very simplistic proof of concept control plane that uses an additive increase, additive decrease loop. And we did that in Python. And this control plane runs in the Tofino control plane. So this design also satisfies the proactive nature that we set as a design goal at the beginning, because by dropping a request in the network, we don't need to implement server-side cancellations, and servers do not waste any resources for requests that are eventually dropped. The other part of the proactive design is that by returning early rejects back to the clients can navigate this latency versus completeness throughput that I mentioned before, or they can retry the request somewhere else. So now let's try to put everything together. In this figure, we have the bunch of clients that want to communicate with the RPC service that runs inside the server. And in between, we have the Sven middle box. So the clients first send the reg0 packets to the Sven middle box. And once the Sven mailbox receives this packet, first gets the timestamp because it's the first thing we want to do once we receive a packet. And then the mailbox decides whether it should drop this request or forward this based on a probability P. So the Sven mailbox generates a random number and decides whether it should drop or not this request. If the request is dropped, then the mailbox replies back a rejection to the client. Otherwise, it forwards the packet to the server. The server serves this request and replies back to the client. And once this is done, the server sends back a feedback message to the middlebox. The middlebox again first gets a timestamp, and then it associates this feedback message with the timestamp that it got for the initial reg0 packet, and computes the latency and updates the latency statistics. Also, periodically, the control plane reads these latency statistics and computes the drop rate and sets this probability to drop a packet in the data plane. So we built and deployed Sven in our cluster, and during the evaluation, we asked the following question. Can Sven identify the load that violates this SLO and keep throughput below that point across different service times? To do so, we ran a synthetic micro benchmarks with different service time distributions. Specifically, we consider 3 service time distributions, a fixed distribution, an exponential distribution, and a bimodal distribution. And we apply a step load pattern to see how Sven behaves during load changes, and even in cases when the overload is beyond the system capacity. But first, let's try to understand what we expect to see. So in this figure, you can see the latency versus throughput curves for the 3 distributions that I mentioned before. And we ran this experiment on a single machine with 16 cores, and the average service time is 10 microseconds. So the maximum throughput we can get in this experiment is 1.6 million requests per second. We also set an SLO of 300 microseconds at the 99th percentile latency. You can see this SLO with the red curve. So what we see here is that the SLO is violated at different load levels across service time distributions. As you can see, the gray curve that shows the load that violates the SLO is at different levels across these different curves. So here we expect that the Sven will identify and keep throughput below this load level accordingly for its service time distribution. We run now this experiment. We run the load step experiment for the same service time distributions. And now I plot the throughput versus time experiment. And in this curve, in this figure, you can see the offered throughput. So the orange line is the offer load. So the orange line is the offer load that we add to the system. Now I added two gray lines, and the dark gray line corresponds to the system capacity, which is the same across different service time distributions, and it's at 1.6 million requests per second. The light gray line corresponds to the throughput that violates the latency SLO at 300 microseconds, and it's the load level that we saw before in the previous graph. So we see that this SLO is violated at these different load levels. Now I plot the achieved throughput when we run this system with Sven. And as you can see, Sven identifies the load that violates the SLO and control throughputs and maintain throughputs at this load level. As you can see, throughput is kept at different levels across different service time distributions. Now the question is what happens with latency? And in this figure now I plot the latency as a function of time for the same experiments. As you can see, Sven reduces the SLO violations even in cases when the offer load is beyond the system capacity. So keep in mind that for this part of the curve, for a system without Sven, the latency would be super high because the system operates beyond its capacity. The other system is that the other thing we observe is that we still have SLO violations, and these are due to the simplicity of the control loop that we designed. But the conclusion here is that despite the simplicity of our proof of concept, Sven can turn any RPC service to a tail-tolerant one. Before I finish my talk, I would like to pose some open questions regarding Sven's designs and the tail tolerance in general. And the first question has to do with the implementation of the control plane. So as you saw, we implemented a very simplistic control plane with this additive increase, additive decrease algorithm, but ideas for a more robust control plane might come from control theory, for example, something like a PID controller, or we could also leverage machine learning and online learning to identify the target load. The other question has to do with the fact that Sven drops requests. And some clients might not want that or might not be able to handle this. So could we, instead of dropping those requests, use Sven to first degrade them and only drop if absolutely necessary? So a degraded request receives a reply of lower quality, but it's faster to compute. The question here is, how can we do this in an application agnostic manner? And what does this mean for different applications? It could make sense for something like websites, for example, but not for a key value store. Finally, Sven, despite being a step towards systematic tail tolerance, it does not provide strict guarantees. As you can see, we still had SLO violations. So the question here is, how can we provide even stricter guarantees similarly to the fault tolerance line of research? So to conclude, I presented Sven, which is a system that can be used to deploy tail-tolerant RPC services by exercising SLO-aware RPC admission control. Sven is implemented as an RTP2 in-network policy, thus it remains application agnostic, and uses in-network compute and programmable switches to avoid server modifications. Sven is the first step towards systematic tail tolerance, and we expect to see more systems like that in the future that consider tail tolerance as a design principle rather than a metric to report once the system is implemented. With this, I would like to conclude, and I'm happy to take your questions. Thank you.
Thank you, Marius. Could you please use the raise hand feature if you would like to ask questions? Okay, I don't see any raised hands. So I have a question myself. So looking at your evaluation, so it looks like the latency actually goes quite far beyond SLO. And I think if you actually implement it such that if you throttle the request to exactly below the SLO line, like magically, then it would never actually go beyond the SLO, right? So
Yeah.
does it mostly coming from the fact that you do feedback control of some sort that has a delay to actually adjust the probability? Is that the right way to think about it?
Yeah, so both points were actually right. So in our experiments, we set the threshold in the control plane exactly at the SLO. We could set a value that is lower so that we react faster. But then this has to do with the quality of the control plane. So setting the difference is something that is not very straightforward and comes through experimentation. Also, the control plane that we designed uses those SLO violations in order to react. So as I said, it's an additive decrease, increase, additive decrease. And once it observes these SLO violations, then it starts increasing the drop rate. So having something that it's more aggressive than just additive increase, additive decrease will probably reduce these SLO violations. And this is why we have it as one of our open questions. The good thing also about this control plane is that doesn't have to be super fast. So we run our loops in a 100 millisecond period, and also we run this in Python. So this, despite our simplicity, this gives us some slack to leverage even more complicated control loops. As I said, as you saw, I mentioned machine learning. So we think that probably we have enough time to use some basic machine learning in order to, instead of just reacting to and increasing or decreasing the drop rate, just setting the drop rate specifically based on what we observe and what the traffic is at its point in time.
Okay, thank you. So I think we are slightly over time, so let me move on to the next speaker. Thank you very much, Marius.
Thank you very much.
Yeah.
Let me stop sharing my screen.
Yes, please. So next talk is from Kefan Chen. He's a PhD student at Tsinghua University, Computer Science Department. And his research interests include network protocol stacks and data-driven networking. Unfortunately for him, he has a networking issue, so I'm gonna play recorded video of his talk for this. So, let me share my screen. So, can you hear the audio from this? No.
Oh, King, I think you may need to set up the video.
So does audio going in or
use another audience channel.
Use another audio. Okay, can you elaborate more on what you mean by that?
Uh, you can first you see a button at the left at the bottom left, start video. Then you can see video setting.
Here.
Video setting. I think you can share your screen. Yeah, it's here. And choose another microphone. Same assistant. I don't know whether it can work, but same assistant.
So you so when I play this, you don't hear any audio. Is that correct?
The voice is very low. I think the audience can't hear it clearly.
Okay, let me try to fix that. Is it better now? Let me.
Online services such as EDC, game, work, etc. is created by content provider and hosted in cloud, eventually delivered to user through internet. As for cloud service provider such as Tencent, providing high performance
Hi, King. I think it's not work very well.
Is there a different way for me to actually play this?
Can you send the file just the video file just to the chat channel?
You mean the video file?
You can send the file to the chat, and I can try to.
Oh, one sec. I think I know how to do it.
Check first. Click the check.
Can you hear now?
High resolution and congestion control. This is key role in transport performance.
Can you hear the sound now?
But the voice is very low. I think it's not clear.
I think this is the video effect is very low volume.
Hello everyone, I'm Ke Fan Chen from Tsinghua University, China.
Oh, it's okay now.
Data center user congestion control. Nowadays, online services such as video streaming, online game, work, etc. is created by content provider and hosted in cloud, eventually delivered to user through internet. As for cloud service providers such as Tencent, providing high-performance delivery for this content is crucial. That is, they pursue high throughput and low delay. For example, they want to minimize page load time, provide a video with high resolution, and congestion control. plays a key role in transport performance because it decides sending rate. In the data center to user paradigm, there are lots of heterogeneity. When the online content is sent from data center, it will travel through wide area network and local access network, finally to user end device. For wide area network, internet service provider has their own different network properties and traffic engineering policies. Besides, there are also dynamic cost traffic. For access network, user could use lots of such as Ethernet, Wi-Fi, 4G. From the perspective of cloud service provider, these complex factors cause heterogeneity perceived from servers in data center. Therefore, one server in data center faces worst heterogeneous user connections and is reflected in two aspects, diversity and dynamic. Although dozens of congestion control algorithms (CCA) are proposed, in practice, a single algorithm is usually configured for all connections in a server, but one specific CCA cannot excel in diverse scenarios. The reason is that traditional end-to-end CCA make assumptions about network and infer the bottleneck from the local observables, but this is not always accurate. Observed the shortcoming of traditional CCA, there has been a surge of efforts to utilize machine learning techniques to adapt congestion control to heterogeneity, but they have practical issues. They can be characterized in two camps: model training approaches and online learning approaches. Model training approaches generate a control policy for a given artificial network specified by simulation or network trees and train a control model offline. The online learning approaches make no assumption about the network and adjust its sending rate based only on online reward to maximize a utility of combined performance metrics such as PCC, and they will have practical issues. For the model training approaches, it is hard to predefine the client's network parameters or get the trees in advance because the client and host is not fixed. Secondly, the effectiveness of trained algorithm is heavily depending on the training dataset. Lastly, the overheads of them are usually higher. As for the learning approaches, the main defect is they usually slowly reach the available resource due to its length read control from scratch for each connection. In the figure, shows a throughput of two CCA, one online learning approaches, PCC, and the other is Rustwood, a traditional algorithm designed for wireless network, and it is a Wi-Fi scenario. You can see that PCC reaches the resource share way too slow. And existing methods, as we have stated before, go to extremes. For model learning, for model training approaches, it goes to the extreme of specificity, such that you have to define the training dataset accurately for it to train. And for online learning approaches, it goes to the extreme of generality. It makes less assumption and treats the network as a black box. Generate a policy by trying and learning. So, what about a middle road, which is selecting CCA according to the network characteristics of each connection? During the figure, we can collect network feedback data for each connection and characterize it. Based on it, select a matched CCA. And it is a middle road in the sense that it reveals the human wisdom in the traditional CCA and utilize the pattern recognition power of machine learning to find the scenario and CCA mapping. Next, we talk about why selecting CCA. Firstly, hand-crafted CCA achieve the desired goals and perform well in normal scenarios. The typical network scenarios have been well studied, and corresponding CCA are proposed. Meanwhile, machine learning CCA cannot magically surpass all handcrafted CCA in all performance metrics. The figure shows real-world CCA test results. It tells that handcrafted CCA achieve the expected performance, such as cubic BBR achieve high throughput and Vegas achieve low delay. And some machine learning methods such as COPA and PCC perform similarly as Vegas. Lastly, finding the mapping of given connection to suited CCA is feasible in data center because unlike traditional congestion control, which use only a single connection's feedback data, server in data center have a global view across connections. And we found out in our dataset, real-world dataset, that network characteristics of connections in a server share similar features, and these features and accumulated historical data provide a dataset for CCA selecting. We introduced RING, a framework for server-side congestion control. It has two main functions: collecting data for characterizing connection and switching CCA to adapt to heterogeneity. Figure shows a high-level structure of RING, including two key modules, selector and agent. They exchange information through a pair of pipes. Agent resides in network protocol stack and is responsible for collecting data and switch CCA. The selector maps the collected data to matched CCA. The agent collects network feedback data and exposes it to selector by outward pipe. Selector maps the data to suited CCA and sends CCA switch notification to agent. Then the agent can launch an algorithm switch in network protocol stack. We will talk about each component with more details. The agent has two main functions, data collection and algorithm switch. That collection function is instrumented in the ACK processing procedure. The algorithm switching is realized by two steps, replacing CCA on the fly, and ensuring the smoothness of CCA transition. Note that it is non-trivial because different CCA can maintain different variables. Thus, state translation is needed. We will talk about how to address this challenge. First, about replacing CCA on the fly, it can be done by replacing the reference to the algorithm. It is usually a function point, and we have to restructure the transport call. We have to restructure the transport protocol to be modularized, and CCA is need to be implemented as pluggable module. For ensuring the smoothness of CCA transition, the key is to translate the variables between the previous and selected CCA. And there are two kinds of variables are crucial to performance, the sending rate and observed variables. Because sending rate directly decides the performance, and the sending rate is computed based on the observed variables. We take two key steps to achieve it. First is to inherit the previous algorithm sending rate, and then we initialize the new algorithm's observed variables to the default value. This is because we found out that the observed variables of algorithms are usually updated frequently, and therefore this is most variables of algorithms are updated per ACK, and multiple ACKs are received in one RTT, which can generate adequate samples to update the observed variables. Now talk about selector. Its main function is to map collected data to match CCA, and this is the focus of future work. We briefly describe the key ideas. For some special cases, we first check whether this connection is a physics-typical network scenario. If so, we can use a rule-based selection designed by a human and choosing a specialized CCA. But for general cases, we intend to apply data-driven method to gauge the mapping. We call it learning-based selection. And the mapping is learned from the real dataset collected in our production server. We implement RIN in Linux by modifying the kernel and add a kernel module and write the user level library. The user space implementation includes a user interface, which is a set of API to manipulate the kernel module. And we implement a selector with a rule-based selection policy. It It is used to differentiating Wi-Fi from wired connection and to demonstrate the usage of this API. Next, we answer 3 questions. Can we achieve smooth and online algorithm switching? And we improve performance by using Ring. Finally, whether the overheads introduced by Ring are moderate. We build a testbed to emulate heterogeneous network. We emulate wide network by setting a middle box machine as the network bottleneck and set the bottleneck parameters by Linux TC. As for the wireless network, we use a local university public Wi-Fi. First, algorithm switching. We regulate the link to such parameters, and we switch algorithm using Ring and switch from cubic to BBR and Westwood, and these 3 algorithms covers the major types, which is the read-based, window-based, or delay-based, loss-based. And the figure shows that the smooth and online algorithm switching can be conducted by Ring. Next, we create 3 network scenarios: Wi-Fi and wired network with small and large bottleneck buffer. And we use 3 client machines to access all 4 servers. The 4 servers use different congestion policy. We collected data from 4 servers and found out that Ring virtually outperform others in the heterogeneous network setting. Finally, we explore the overheads. We set up 1 server machine and 1 client machine. They are connected directly. We compare, and the client machine uses a HTTP benchmark tool to download files and nearly saturate the NIC. We compare Ring with Netlink to demonstrate the efficiency of Ring. Netlink is a commonly used tool for transferring information between kernel and user space. We profile CPU cost and found out that the overheads introduced by Ring are modest, while Netlink's cost is non-negligible. Conclusion: we introduce Ring that aims to improve performance by exploiting the heterogeneity of client's network. It has 2 functions: collecting data for characterized connection and switching CCA smoothly. Preliminary evaluation confirms the feasibility of Ring, and our future work will focus on designing learning-based CCA selection policies using the real-world dataset collected from our production servers. Thank you, and I'm ready to take questions.
Right. Thank you. So because of the time, I think we'll skip the Q&A and move on to the next speaker. So the next speaker is Xiaorui Wu. He's a final year PhD student at City University of Hong Kong, working with Henry Su. And his research interested in distributed deep learning systems, and received a bachelor degree from University of Electronic Science and Technology of China. Are you?
Hello, can you hear me? I'm here.
Yes, I can hear you. Can you start the presentation?
Okay. Hello, can you hear me?
Yes, I can hear you. Please get started. We are short on time, so please try to make sure you finish in 20 minutes. Thank you.
Hello. Sorry, hi, hear me? Hello, can you hear me?
Yes, we can hear you. Can you get
I
started?
can. Okay, can I start now? Yeah. Sorry, can you hear me?
Xiaorui, can you hear me?
Yeah.
We can hear you, so please start.
Okay. Hello, everyone. My name is Xiaorui Wu. Today, I will talk about ARENA. ARENA is a system to accelerating DNA inference with efficient online scheduling. This is a joint work with City University of Hong Kong and the Pengcheng Lab. Deep neural networks empowers state-of-the-art results across a range of applications, including traffic monitoring, surveillance, AI assistant, garbage classification, or other AI-based applications. DNA inference is the core of the AI-based applications. Let's first look at what happens in the DNA online service pipelines. It can be abstracted as 4 stages. First, the clients submit queries to the applications. Second, the applications conduct some pre-process and the queries, and then the queries are analyzed by the DNA models. Finally, the prediction result is processed and sent back to the clients. The DNN-based inference is the most computation cost in these pipelines. In this work, we focus on how to serve online workloads efficiently with distributed DNA inference. So how is the DNA inference serving architecture? It is similar to traditional distributed serving architecture, but there are 2 different points. First, all of the tasks are replaced with DNA inference tasks. Second, because the DNA inference tasks are computation intensive, backend will adopt specific accelerator, such like GPU or TPU. In this paper, we focus on GPU as the backend computing device. Clients submit the queries and the applications collect the queries and then sends them to the front end. The back end processes the queries with DNN models and returns the prediction results to the applications. However, what's the difference if we consider the process from the client perspective and the cluster perspective separately? Clients just know they submit queries to the applications and don't care how the applications to process the queries. In the contrast, the cluster treats the applications as a client. They don't know the true clients. As a result, cluster aims to improve the throughput of cluster and reduce the total mixbound, but clients only care when they can get their response. Now we have an example to explain it. So if we have two tasks, task A and task B submitted at the same time, task A contains 2 queries and task B contains 3 queries. And there are 2 orders to execute the tasks. What's the difference from the cluster and client perspective? For the cluster, the total cost to execute task A and task B is stable, which will not be influenced by the execution orders. Now we talk about the different results from the client perspective. In first order, we execute the task A first and then execute task B. Three red clients need to wait a long time for finished task A and task B. The latency is multiple times than the task B's execution latency. In the contrast, if we execute the task B first and then execute task A, 3 red clients only wait the execution latency and 2 blue clients only wait a small part of execution latency of task B as the waiting time. For second order, the client experience is obviously better than it in first order. It's a different client experience which can directly influence the reviews of the applications. Most existing DNN serving systems only consider the execution time from the cluster perspective, such like the TensorFlow serving clip or Nexus. They focus on offline scheduling policy to improve the throughput of the cluster. They don't consider the client experience. They know the predictable workloads in advance and rely on offline scheduling policy. If there is unpredictable workloads, they only consider FIFO as the online service scheduling policy. In this paper, we propose Arena, an efficient DNN online inference scheduling system. Arena aims to minimize the average job completion time and improve the client experience. The average job completion time is directly related to the client experience. So during the computation of average job completion time, we use the number of clients instead of number of tasks, which can directly reflect the client experience. Now we propose 3 dynamic scheduling policies for online service from 2 levels. First is task level. The preemption scheduling policies can provide limited resource for the task with the highest benefit and the average job completion time. And stacking scheduling can run multiple tasks concurrently to improve the throughput and reduce the job completion time. We also exploit the model level. The batching scheduling can batch examples across different tasks which use the same model. We use some examples to illustrate our scheduling policies. First is preemption scheduling. There are multiple conditions to execute preemption scheduling policies. The ongoing task occupies the limited resource. There is no sufficient resource for a new coming task, but the new coming tasks contains a large number of queries. So if we want to apply the preemption scheduling policies, we need to compute the job completion time, and the current job and the future job completion time should be smaller than the FIFO's scheduling. And both tasks can satisfy the latency service level objectives. There are two models, the model A and model B. The model A's batch size is smaller than model B, but the execution latency is longer than the model B. So let us consider the two inference applications, one using model A and one using model B. We assume that 8 queries of model A arrives at the very beginning, and 256 queries of model B arrive 1 millisecond after that. FIFO schedulers will run A's queries first, then B's queries, leading to an average job completion time of 83 across all queries. Since queries of model B only takes 10 milliseconds to finish, if we allow preemption where B's queries get executed as soon as they arrive, the overall average job completion time now jumps to 12 milliseconds. Note that throughput is slightly lowered with preemption, since the mix span increased from 85 milliseconds to the 86 milliseconds. However, we should, in order to implement the preemption scheduling policies, we should serve two challenges. First is how to enable preemption, and second is how to process the immediate results, because we need to stop an ongoing task. There are some activations we should process. The next policy is stacking scheduling. Stacking scheduling is suitable for the situation that the GPU resource cannot be fully utilized by a single task. So we want to pack two tasks together to run at the same GPU. The requirement for the concurrent task is that the total resource requirement should meet the GPU resource limitation. In the table, we add two new features, that average GPU utilization and the peak memory requirement and its corresponding time step. So through two features, we can compute the total GPU resource the concurrent task needed during their execution. In this example, we assume that Model C submits 10 queries at time 0, and Model D submits 100 queries in 160 milliseconds. If we don't know the detailed data trace, we only schedule the task C and task D in sequence, and we first execute task C and then execute task D. The average job complete time becomes 63. However, now we know the detailed data trace. We know that peak memory requirement of task C and task D doesn't exceed the GPU memory capacity. So we can apply the stacking scheduling policy on task C and task D. The new scheduling result with stacking is is shown in the figure, that where the average job completion time drops to 27 milliseconds. However, we should also consider the question that the interference among concurrent tasks, which may cause both tasks becomes a little longer, little slower than before. The final policy is batch scheduling. Batch process is a key techniques to improve the utilization of GPU resource. In a reasonable range, large batch size only marginally inflates the execution time. Most existing machine learning frameworks adopt the batch process to improve the throughput. The basic requirement for the batching scheduling is that ongoing task and new task should use the same model, and we should check the large batch size doesn't cause obvious latency growth and the GPU resource is sufficient for new large batch execution. In the table, we find that when the batch size are 8 and 16, their execution latency is similar. The gap is only 10 milliseconds. Let us consider a scenario where 8 queries for model A arrive at time 0 and 8 queries for the same model arrive 1 millisecond afterwards. The current FIFO scheduler will simply execute these 2 batches sequentially as shown in figure. The second batch experiences a job completion time of 149 milliseconds, and the average job completion time is 112 milliseconds. So now if we apply the batching scheduling, we can use 2 8 batches compared to a new 16 examples batch and execute the large batch. The large batch result shows that the average job completion time can be reduced to 86 milliseconds for all 16 queries. So in order to implement our dynamic scheduling policies, we should fix multiple challenges. First is how to enable preemption. Second is how to process immediate results. Finally, we should also consider the interference among concurrent GPU models. First, how to enable preemption. Our existing service frameworks do not support preemption. They haven't considered stop and ongoing inference tasks. We proposed multiple possible solutions. First is, in general, inference tasks is assigned to a thread to execute, so we can kill or cancel the thread. But this solution is now may cause GPU memory leakage. And the same as the second solution, that if we want to use multiple process to execute the inference task and kill the multiple process, the problem is that the GPU driver is not safe across the multiple process. Finally, we plan to modify or rewrite the computing graph. So we designed an exact OP which can receive an external signal and exact the computing from the computing graph safely. As illustrated in the figure, we assume that blue blocks as the layers in computing graph, so we can insert the exact OP between 2 layers. If we send a preemption signal, the exact OP can receive the signal and exact from the nearest layers. The second challenge is the process the immediate results. If we apply the preemption, and there are some activations generated by the previous layers. So we should process the immediate results. There are two possible solutions. First is we can swap in and swap out the immediate results. When we want to re-execute the task, we can use the immediate results to save the computing resource. And the second solution is we just discard the immediate results and recompute the total computing graph when we want to execute the task. In our current implementation, we adopt the solution 2 based on 2 reasons. First is recomputing cost is light, which can be ignored. Some previous works also proves this process. We set them in our paper. Second is that a solution 1 need to modify the runtime frameworks, and sometimes the I/O operation cost is heavy. The last challenge is how to process the interference among concurrent GPU models. The interference may cause both two tasks becomes slower than before. So we propose the 2 solutions. First is we only stack long-running tasks and short-running tasks in our stacking scheduling. Even both tasks becomes a little slower than before, but the average job completion time can still benefit from the stacking. The second solution is that providing concurrent running tasks. All applications will register models into the cluster in advance, so we can providing all models offline to choose the models with little interference. And then we put them in a list. If we want to apply stacking scheduling process, we can choose the models from the list. The prototype of Arena is still under implementation. To evaluate the performance of our dynamic scheduling policies, we conduct a real data trace simulation. Our data trace is collected from our test bed. We simulate 4 applications with varied workloads. The result shows that Arena can still improve job completion time by 1.3 to 2.5 times over TensorFlow serving scheduling policies. To conclude this talk, Arena serves multiple applications with efficient online scheduling at the low job completion time. It includes 3 dynamic scheduling policies. In order to implement 3 dynamic scheduling policies, Arena enables preemption to support preemption scheduling and batching scheduling policies, and analyzes the interference across models and frameworks. Finally, Arena uses job completion time as a target to schedule online inference workloads, which can directly improve the client experience. Okay, thank you.
Thank you, Xiaorui. Given the interest time, maybe we'll take one short question if there's any. Please raise hand if you have any questions. In the meantime, the Shin-chan, our next speaker, can you start your screen share? Okay, so I have a question from the Zoom chat. So the question is, how does Arena schedule batching, stacking, preemption? Is there a trade-off between interference latency and batching performance?
Sorry, can you repeat it? The signal is not.
Yes, so you can also see it in the chat. So the question is, how does IRENA schedule batching, stacking, preemption? Is there a trade-off between interference latency and batching performance?
Yes, we use the batching scheduler before the requirement. The basic requirement is that all the tasks, if we use the scheduling process, we should make sure they should first meet the latency requirement, and then is the job completion time.
Okay. Thank you, Xiaorui.
Okay, thank you.
Okay, Xin Chen. So next speaker is Xin Chen. He is a second-year PhD student from Hong Kong University of Science and Technology in Computer Science and Engineering Department. His research is in the intersection of machine learning and networking systems. Without further ado, Xin Chen, please get started.
Yes. Can you hear me now? Yeah.
Yes, I can hear you.
Okay. Thank you, Kim, for the introduction. Good afternoon, everyone. I'm Xin-Chen Wan from SynLab HKST. Today, I present our work, RAT, Resilient or Reduced Tree for Distributed Machine Learning. It's a new parameter exchange scheme with topology awareness to accelerate distributed machine learning training process. In recent years, we have seen machine learning empower state-of-the-art results across multiple applications such as image classification, speech recognition, and game playing. Most growing applications of AI embraces the use of machine learning and have yet achieved great performance. For instance, in image classification scenario, deep learning jobs can reach around 3% top 5 error rate beyond humans. However, the machine learning training can take up long training time and require a large amount of data for training. For instance, to train a widely used model, ResNet50, upon a single TPU, can use up 10 hours until model converges. And for NLP model BERT, the time can expand to 81 hours with the use of 16 TPUs. And for the huge amount of dataset part, the famous image classification dataset, ImageNet, has over 15 million images, while Q&A dataset scored contains over 100,000 QA pairs. Such huge datasets have a special GPU memory requirements. To overcome the above challenges, distributed machine learning is usually adopted and implemented. There have been multiple parallel training paradigms for distributed machine learning, and we focus our discussions in data parallelism. In such paradigm, each worker manages its local model and trains independently on a portion of the dataset, which is also named as a data shard. The training process is done in an iterative way, and each iteration contains two phases. The first phase is the compute-intensive local model training phase that involves a forward pass to generate predictions with the mini-batch input, and a backward pass to derive local gradients with respect to the loss between predictions and the given labels. The second phase is the communication-intensive parameter gradient exchange phase, where mean gradients are calculated across all locally calculated gradients. The updated parameters are sent back to each worker, and then the worker starts the next iteration with the updated version. Several papers have pointed out that the second communication phase is becoming a severe bottleneck across the training process. And they also quantify that the communication may take up to 90% of the overall job completion time, as the amount of iterations for training can usually be up to hundreds to thousands. A better way to determine how parameters or gradients are exchanged among servers are worthy of exploring. And this logical exchange scheme is also known as the parameter exchange scheme. At each parameter exchange phase, a particular exchange scheme that describes the logical parameter exchange process among servers in each iteration is implemented. Here we categorize popular parameter exchange schemes for DML jobs as follows. The classical parameter server scheme, the collective or reduce schemes that include ring or reduce, k-nominal tree, butterfly mixing, and recursive halving and doubling, and some topology-aware or reduce schemes such as BlueConnect, parameter hub, heaps, and p-link. Here we also note that the PS and ring are the representative parameter exchange schemes that we're exploring. Next, we'll introduce each of them in detail. PS employs a direct communication pattern, where parameters are synchronized directly between workers and PS. After computing and generating local gradient updates, workers push them directly to PS and pull the updated parameters back as soon as PS finish the aggregation. Though PS is direct yet effective, we reveal that it's ill-suited to network oversubscription. A PS traffic pattern is shown in this figure. Here we observe that the cross-rack link will always suffer 16/7 times workload compared to each inter-rack link. More generally, given R racks, each with WR workers with an oversubscription ratio of 0, the average job completion time will be as worse as the equation shows. It indicates that the problem will get more severe for large jobs with more racks. Besides, we also emphasize that the server placement in each rack won't alleviate this problem, because the inter-rack traffic won't change given a cluster size. And the key factor is the direct communication pattern, which is adopted by PS. Compared to the direct communication pattern of PS, Ring typically adopts a chain-based communication pattern, and it introduces a minimal cross-rack traffic, as the ring or reduced traffic figure shows. In such scheme, all nodes form a ring topology, and each node transmits gradients in exactly the same circular direction. It has two phases, scatter, reduce, and all gather. For example, in this figure, the scatter reduce phase processes after each worker generates their own gradient updates, and they each receive a chunk of gradients from its right-hand side, aggregates it with its local copy, and send it to its left peer. After n-1 iteration, each worker has precisely one chunk that involves all workers' updates. Then in the all-gather phase, each worker simply copies the received chunk with n-1 iterations and finally complete the communication phase. Compared to PS, ring or reduce aggregates the parameters or gradients in each hop and thus minimizes the inter-rack traffic. However, here we reveal that ring also introduces too many dependencies and is thus vulnerable to congestion or failures. As the case shown in figure, N nodes are involved in implementing all reduce operations, and we assume node 1 cannot send data temporarily, which may result from multiple reasons such as the link fails, or it is congested and priority is given to other traffic, or node 1 is a straggler and is not yet ready to send, etc. In this case, node 2 can only send 1/n of the data to node 3 via one of its chains, because n-1 chains are blocked due to node 1. In turn, node 3 can only send 2/n of the data to node 4, and so on. Such dependency causes a cascading effect to all the downstream nodes, leading to a 50% cutoff on network utilization when n is large. We refer to such phenomenon as chain blocking. Later in our experiments, we also revealed that the chain blocking phenomenon is quite not common in ring scheme. In contrast, PS does not suffer from this problem, as the direct communication introduces minimal dependency. Other all-reduced schemes like k-nominal tree and recursive halving and doubling can be viewed as a mixture of PS and ring. They have predetermined exchange patterns that are agnostic to network topologies and suffer from similar problems like extra traffic for inter-rack communication or long dependencies to some extent. And some recent all-reduced schemes execute gradient aggregations by wearing the hierarchical network topology, but they each have limitations in extra cross-domain traffic and long dependency chain. Besides, some special data center network topologies or hardware requirements are also needed for such schemes. For instance, BlueConnect breaks up one ring into multiple small rings, but as it's a variant of ring-based scheme, it inherits the vulnerability of ring and requires symmetric topology to reduce the straggler effect. HIPS requires server-centric topology to embrace RDMA, and parameter hub requires each server to be equipped with multiple NICs for the purpose of relieving incast congestion. P-link requires no knowledge of topology. However, it is restricted to the two-level hierarchical topology. On the whole, we give an overall comparison table with the two metrics that we derived from PS and ring, which is the minimum cross-domain traffic and the number of the total dependent steps. For this table, we can easily find out that existing parameter exchange schemes face either or both of the two limitations, and thus are not adaptive to network oversubscription and not resilient to congestion or failures. The above-mentioned limitations motivate us of the desired properties of parameter exchange schemes. The first is the minimum traffic across oversubscribed regions that help us avoid the in-network bottlenecks. And the second is the short dependency chain that help us better resilience to traffic congestion and failures. And here we present our solution, RAT, resilient or reduced tree, as the new parameter exchange scheme with the awareness of topology that satisfies the two desired properties. Moreover, due to the simple structure of RAT and easy for implementation, we also demonstrate that RAT is easy to enable affordable computation and enforcement overhead. Now we introduce the design of RAT. Given a physical network topology, we build the logical RAT for a DML job following a simple layer structure, resembling the physical topology while accounting for oversubscribed regions. A node plays one or more of the following roles. The first is the leaf role. Leaf node senses local gradients and receives the global update. Each worker in the job corresponds to a leaf. And the second role is the aggregator, where for each oversubscribed region in the topology, RAT introduces a corresponding aggregation layer to minimize cross-region traffic. In the reduced phase, an aggregator aggregates the gradient updates from leaves and low-level aggregators within the region and send the aggregated updates to the high-level aggregator or root. In the broadcast phase, the communication reverses. And the third role is the root. It is responsible for aggregating all the gradients, calculating the global update, and send it back in the reverse direction. Here we also show an example of two racks network topology and one RAT that is built based on the topology. Here, node 1 and 8 are the aggregators at each racks, and 1 is also the root of the RAT tree. The parameter exchange algorithm is closely related to the role of the node. RAT partitions the whole nodes into different groups and hierarchically aggregates gradients based on the topological characteristics. Still, we set the two racks with 8 nodes as an example, and the RAT traffic is described on the left. Here, aggregator 1 and 8 aggregates the updates within each rack, and afterwards, aggregator 8 sends the aggregated updates to root 1, and then the broadcast process operates in a reverse direction. More generally, for a specific parameter exchange process, we construct n RATs given the network topology, where n is the size of the cluster. For example, we establish 8 RATs here, and each RAT conveys equally 1/8 traffic volume. For each RAT, roles are assigned according to the oversubscribed regions, and traffic is transmitted based on the architecture of RAT. After the introduction of the RAT design, now we revisit the design properties and show that RAT satisfies all of them. Firstly, RAT treats the cross-domain traffic in a similar way as ring. It aggregates the parameters or gradients at each hop to guarantee the minimal interact traffic during aggregation. Secondly, RAT has the dependency chain with the length of 2 times L plus 1, where L is the number of the oversubscription layers. Since a data center cluster typically has few oversubscription layers, like 1 or 2, this chain is usually much smaller than alternative schemes except PS. Last but not least, RAT has a simple structure which only introduced 3 rows and a simple yet effective design with topology awareness. This simple structure makes it possible to enable timely computation and enforcement overhead during the practical implementation. We have evaluated RAD using NS3 simulations with both oversubscribed network and network with failure scenarios. And here we show our preliminary simulation results. In the oversubscribed scenario, we use a conventional spine leaf topology with 2 spine switches and 4 leaf switches. We set the number of workers per rack as variant, and the oversubscription ratio changes accordingly from 2:1 to 32:1. As shown in the figure, RAD achieves an average of 25 times better than PS. This is because PS introduces a large amount of inter-rack traffic and results in the bottleneck at cross-rack link. Ring minimizes inter-rack traffic and is expected to perform as well as RAD. However, from the figure, we surprisingly observe a minor throughput degradation in Ring implementation in many cases. Through analysis, we think Ring's long dependency chain may introduce some extra delay at each hop. The delay at each hop slows down the total chaining process. And for the network with failure scenario, we run ML traffic on 64 servers in a 40 gigabits per second network with no oversubscription introduced. We simulate the network congestion of failures at nodes or links by pausing some nodes sending data. That is, we randomly select K nodes temporarily stop sending data and periodically change the K nodes every D time. The results shown illustrate that RAD achieves 5.7 times better performance than Ring. This is because when one node is blocked, other nodes can still take the available bandwidth to proceed if in PS or RAD mode. While for Ring, the progress of its downstream nodes is heavily blocked due to chain blocking. Besides, RAD achieves comparable performance against PS in this scenario because RAD only introduces a minimal number of additional dependencies upon PS. For more detailed evaluation setups, please refer to our paper. And for the future work of RAD, firstly, a more concrete testbed implementation is ongoing and is expected to be integrated to some mainstream DL frameworks like TensorFlow and PyTorch. And secondly, as current workloads are equally distributed in each RAD across the cluster, a much general case that a different size of workload in each RAD remains to be explored. To sum up, in this presentation, we revealed that the optimization of parameter exchange schemes has a great potential to accelerate the process of DML. However, existing schemes may have limitations in introducing extra cross-region traffic or have long dependency chains. And then we introduced RAD as a topology-aware scheme that utilizes the characteristics of 2 or 3 layer tree-based decision topology, which is already prevalent in current decisions, and thus have few oversubscribed layers. Through analysis, we demonstrate that RAD achieves 3 desired parameter exchange scheme properties, which are the minimum cross-region traffic, short dependency chain, and simple architecture. And that's the end of my presentation today, and I'm happy to answer questions.
Thank you, Xinchen. So if you have any questions, please raise your hand feature or type the question into the chat window. So I have one question. So I don't actually know much about model training, but one thing that I read or heard somewhere is that the common technique people use to avoid bottlenecks during the synchronization is using the stale values. Can you kind of explain about like if you actually when you're to use those stale values to optimize system, does this kind of solution still actually provide sufficient good benefits or not? Do you have a sense on?
And I'm sorry, I'm a little confused about the terminology. What is I didn't catch that words.
Oh, okay, the stale value. So to avoid synchronization across all the workers, so some of the workers are to keep training using the stale value.
Yes.
Right. Yeah. So can you do you have a sense on like how would it work when you combine your solution with those kind of techniques?
I think your point is that whether we need to use the synchronization phase or some a stair synchronization parallelism such as SSP or ASP. That is right. Okay. Firstly, our solution is orthogonal to those solutions. However, in our implementation, we assume that we use the BSP. That is, we synchronize the parameters in each iteration. And for the SSP and ASP, of course, we can as well implement them in it. But however, in practice, the SSP and ASP are not good for model training as they may not give the reproducibility to the model training, and it will lead to some degradation to the final accuracy and thus affect the model performance. Yes.
Thank you. Does anyone have questions? Okay. Thank you, Shin-Chen. So this is the last talk for the data center networking session. Thank you everyone for attending.
Thank you, Kim.
So let's take a break.
Hello, can you hear me?
I can hear.
Okay. Yeah, I'm Qin Huang. Yeah, I'm hosting the last session in this APNet. And okay, I see that the first speaker, Dr. Ennan Zhai, has in the room. And now let me introduce Dr. Ennan Zhai first. Okay, and Dr. Ennan Zhai is currently a staff engineer at Alibaba Group. His research focuses on building secure and reliable networking systems, and especially his work takes advance of an interdisciplinary approach, integrating areas including verification, programming language, database, and security. And before joining Alibaba, he was a research scientist and lecturer at Yale University. And he also got his PhD in 2015. And okay, now let's welcome Dr. Ennan Zhai to present his work.
Hi, Chen, can you hear me?
Yeah, I can hear you. And you can share your screen now.
Good. So can you see my talk slide? You can see my screen, right?
Yeah, I can see your screen.
Okay, great. So are you all start now or just wait for maybe two minutes?
Okay, and we can wait for 2 minutes and let's start at 3 p.m.
Okay, good. Yeah, how's everything going?
Yeah, it's good now. Yeah. So
Yeah.
how about you?
I think I'm fine. So work from home for about 5 months so far. Yeah, we never know what time we can, go back to the company.
Yeah. I think maybe working from home will be common in the future.
Yes, maybe. Yeah, in that case, I think a lot of companies do not need to, rent any office rooms anymore. Yeah, but we never know. Yeah, I think, yeah.
This is similar in university. Yeah, our department has notified us that we need to be prepared to host online course next in the next year.
I see. Yeah, great. Yeah, I think good. Yeah, I think Zoom performs very well for our conference this year.
Yes.
Okay. Yeah, I think maybe it's time for me to present. So can I start, Chen?
Oh, okay. We may start now.
Okay. So thank you very much for Chen's introduction. So hello everyone. Today I'm going to talk about Lyra, a cross-platform language and compiler for data plane programming on heterogeneous ASICs. This is a joint work between Alibaba Group, Tsinghua University, Harvard University, and Nanjing University. Oh, I may need to turn off this one. So in recent years, programmable network devices have gained a significant traction in the networking community because of their high performance and high flexibility. People have shown benefits offered by flexibility of programmable network devices, such as consensus protocols, load balancing, and congestion controls. At the same time, the mainstream ASIC vendors are releasing their programmable ASICs. For example, Broadcom releases Trident 4 and Jericho 2 ASICs, which can be programmed in NPL language. Barefoot and Cisco also published the Tofino and Silicon One that support P4 programming. However, despite the bloom of programmable switches, the foundation of network programming on data plane is still at an early stage. Programmers are still using chip-specific languages and manually take care of a lot of details with hardware architectures and network environment. This brings back to the era when the programmers coding the software on CPU using the assembly language. Let me show an example to illustrate why current data plane programming is hard. This is a network sequencer which is a critical component for the linearizability in the consensus protocols, such as Paxos. More specifically, the network sequencer adds the sequence header to select the packets and drop others to keep the ordering. For example, the sequencer adds the sequence header, a combination of a switch ID and a timestamp, into the packet header on the given packet based on its source IP. For other packets, the switch drops them. The replica servers can then order these packets based on their IDs. We can observe this sequencer has two components, the filter table and the routing table. In general, there are three problems in the current data plan programming. The first problem is the portability. Programmers still use low-level and chip-specific languages to write the programs on the ASICs. Suppose we have a Tofino switch, and the programmer wants to use the P414 to implement the sequencer in this switch. This is the P4 code to add the sequence header into the packet. What the programmer actually really wants to do is just these two operations. It's easy to know the chip-specific languages like P4 are still complex to express the programmer's intent. Even worse, different ASIC vendors provide different library APIs for their own specific ASICs. The programmer has to learn these APIs and takes care of the hardware constraints for different ASIC architectures to make sure the programs compile successfully. Furthermore, different ASICs support different programming languages. For example, the Trident 4 and Jericho 2 ASICs support MPO, while Barefoot Tofino ASICs support P4. So it's really hard to port one program written for one specific chip to another one. The second problem is the extensibility. Current programming languages focus on the programming individual ASICs. It's hard to write the program running on multiple switches. Suppose we have two switches that can hold 1,000 entries respectively. The routing table of the switch requires 500 entries, and the filter table requires 300 entries. In this case, we can easily fit both of the tables into one switch. Due to the business reason, the number of filter table entries increases to 800. The Tor switch does not have enough space, so the programmer has to put the filter table into the aggregation switch, write the programs on both aggregation switches and the Tor switch, and make sure they work together. When the number of the filter table entries increases to 1,300, the filter table cannot fit into either of the switches. So the programmer not only needs to split the filter table into two tables, but also needs to consider how to pass the information between two switches. Otherwise, the filter table on the Tor switch cannot know whether the first table is hit or not. The third problem is the composition issue, that how can we optimize the programs to make sure they can fit in a single basic. Suppose a practical deployment of a programmable data plan has two programs. If the programmer wants to add an ARP table with 300 entries to the Tor switch, we need to rearrange the table allocation. Adding another program, one switch perhaps results in the rearrangement of other programs on the switch. We can see that any of the above cases requires a huge amount of efforts to program the data plan. We summarize the three problems. We believe the foundation reason for the above three problems is the lack of high-level data plan programming language. Again, this indicates that the low-level chip-specific language is the same as the assembly language that is specific to the CPU architecture. Like Dr. Brian said, the C language lets you get close to the machine without getting tied up to the machine. So now it's the time to propose the high-level data plan programming language. So in this work, we propose Lyra, a high-level data plan programming language and a compiler. Lyra offers an one big pipeline abstraction. The programmers only need to express their intent through Lyra language. The Lyra compiler can generate the chip-specific programs for switches in the target network. The compiler introduces three techniques to address the above-mentioned three challenges. First, LoRa builds one language synthesizer for each low-level data plan language, so that the program can be ported between switches. Second, LoRa introduces topology-aware code allocation to deploy the program across multiple switches correctly. Finally, LoRa uses chip-specific constraint encoding to make sure one or more programs can fit into the switch. The first question I want to answer is what type of abstraction we should propose for our target scenario. Traditionally, there are two network programming models. The first model is per switch model. This model is too fine-grained and exposes too many details. The second model is one big switch model, which looks the entire network as a big switch. This model is too coarse-grained. We cannot specify where to allocate the programs, such as deploying a table to all the Tor switches. So we propose one big pipeline model that provides a good balance, can give us the enough flexibility to the programmer. The one big pipeline model achieves the portability because it hides the detail of the chip-specific information. Using one big pipeline abstraction, the programmer only needs to specify the sequencer program logic and fine-grained scope rather than worrying about the extensibility and the composition. Let me show you how to write the LoRa program. This is a sequencer program written in LoRa language. We have three sections. First, we need to define the header and parser. In the one big pipeline model, we only need to define a set of parsers. Second, the pipeline section. In our example, there is only one algorithm. So the pipeline SEQ has only one element called the sequencer. And the algorithm sequencer calls two functions, add sequence and the routing function. The main logic of a sequencer is implemented in the add sequence function. In this function, we can observe that the filter table is implemented through an external variable called a filter. And the size of the filter defines the number of table entries. Currently, we have 300 entries. So when the programmer wants to increase the number of entries, she only needs to change the size of the external variable, and the LoRa can take care of anything else. With the LoRa program, let me show you how the LoRa compiler works. The compiler has two components, front end and back end. Let me first show the front end. This is a LoRa program we write for the sequencer. The front end is responsible for translating the LoRa program into the intermediate representation. The front end expands the LoRa statements, replace the branch conditions into a predicate, which indicates when the statements under the predicate are performed. Finally, the front end analyzes the dependency between the statements. We can observe that the first statement depends on the two statements above it. Now let's look at the design of the backend. So the backend has three major components: language synthesizer, chip-specific constraint encoder, and extensibility module. First, the language synthesizer translates the intermediate representation into structured low-level languages. The chip-specific constraint encode checks whether the program can fit into the switch. Finally, the extensibility module guarantees the program can correctly deploy in the given scope. Let me first show you how we address the portability problem. LoRa should be able to handle both P4 and NPL languages, but we have different programming patterns. For example, P4 is a table-oriented language. On the other hand, NPL is a procedure-oriented language. In this talk, I'm only focused on the P4 language. Please see our paper for more details about the NPL. A P4 program is a composition of tables. Different packets may hit different tables in the program. Each P4 table has match and action fields. In this example, action 1 and 2 are mutually exclusive, like if and else. Each action may have one or multiple statements. These statements have no dependency. Now let me show you how to compile a LoRa program into the P4 program. We introduce a data structure called a predicate block. A predicate block is a group of statements that have the same predicate. and have no dependency between each other. This is the intermediate representation we get from the front end. Let's see how to construct the predicate block. We check the first statement and create a new predicate block with the predicate IPv4.source IP in filter. Next, we check the second statement and third statement because they do not have any dependencies, so we put them into the same predicate block. However, the fourth statement depends on the third one and the second one. In this case, we create another new predicate block. For the last statement, since the predicate is different, we also need to create a new predicate block. So after this step, we get 3 different predicate blocks. Now we need to analyze the relationships between predicate blocks. The first relation is the dependency relation. This happens when one statement in the predicate block depends on one statement in another predicate block. So we can see the second blue predicate block depends on the first one. The second type is mutually exclusive. This happens when the predicate of the 2 predicate blocks can never happen at the same time. In our case, the red one and the first blue predicate block are mutually exclusive. So now let's see how can we use predicate block to generate the P4 code. If 2 predicate blocks are mutually exclusive, then we can merge them and build a table called filter table 1. Given the input of the external variables lookup, we can automatically generate the match fields, which is the source IP. Similarly, we can convert the second blue predicate block into a new table called the filter table 2. The filter table 2 has no match action and has no match field. Because the 2 blue predicate blocks share the same predicate, so the second table is only executed when the action 1 of the filter table 1 is executed. Until now, we can get the synthesized P4 code. Now let's check the second step in the backend of our compiler, which is the encoding chip-specific resources. Using RMT architecture as an example, the RMT switch has 32 stages in the ingress pipeline and requires if one table with the variables written by another table, the first table should be deployed in the stage later than the second one. Because we have 2 tables, we can introduce 2 variables, sFilter1 and sFilter2, that indicate the stage each table is deployed in. We can encode this constraint that sFilter1 should be smaller than sFilter2 because filter table 2 depends on the filter table 1. We should also add the constraint that both variables should be deployed in one of the 32 stages. The SMT solver can quickly return the answer that sFilter1 is 0 and sFilter2 is 1, which means the 2 tables should be deployed in the first and second stage. We also encode other constraints, such as SRAM, TCAN memory, the number of tables per stage. So please see our paper for more details about this. We also propose an approach to handle the extensibility that makes sure the program is correctly deployed in our topology. Due to limited time, please see our paper for more details about the extensibility design. So far, we have introduced all the components in the Lyra compiler design. By using Lyra, the programmer can only focus on high-level intent description, and the Lyra compiler finishes the rest of things. Evaluation. We write the Lyra programs for many P4 applications, such as netcache, netchain, and even the switch.p4. The table shows the comparison design details. We can see the writing a Lyra program requires much less code than the P4 program because Lyra uses a high-level language and the one big pipeline model. Lyra can significantly reduce the resource usage compared by the manually written P4 code. For example, we can see the netcache program. Lyra just use 12 tables, but original program use the 96 tables. Why? P4 code generated by Lyra can save the resources. This is an example. Here's a code for netcache. We can see the two tables with no match field in the manually written P4 code. And they are performed under the mutually exclusive predicates. In this case, Laravel compiler can merge the two tables into one table because the two actions only need one same match. So in conclusion, Laravel is the first high-level data plane programming language and compiler that achieves portability, extensibility, and composition. The programs generated by Laravel use fewer hardware resources than the human-written programs. So this is the end of my talk. Thank you very much. I'm happy to take any questions.
Okay, thanks for the nice talk. And do you have any questions from the audience? Okay, so if there's no questions from the audience, I may have a question. So my question is that you mentioned that you have a big pipeline model abstraction for Lila. So as we know, can you hear me?
Yes.
Okay, and as we know, there's another abstraction. It's called one big switch. So what's the difference between one big switch and one big pipeline?
Oh, that's a great question. So actually, yeah, we have mentioned one big switch, but yeah, I can repeat that. So the one big switch is a coarse-grained model. In that case, we look the entire network as the one big switch. However, sometimes we want to specify some fine-grained scope. Say I want to put one table on the Tor switch, and I want to put the load balancer on aggregation switch. In that case, I should specify some fine-grained scope. However, if I use the one big switch abstraction, we cannot do that because one big switch abstraction just look the entire network as the big, one big switch. So it prevent me from deploying the tables in the fine-grained scope. So that's also the reason we want to propose a new abstraction, which is the one big pipeline abstraction. And in this abstraction, we could propose a fine-grained scope for different programs.
Okay,
hopefully I answer your question.
Okay, and there's another question from the audience. The question is that if there is a new ASIC that is released with its specific low-level language, so what engineering efforts are needed to support the new ASIC and the new low-level language?
Great question. Yeah, so for the compiler, we can only handle the ASICs and languages we have known. That means we cannot handle the languages and ASICs we don't know. So the engineer efforts we should put for the new ASICs is to feed all the information in our provided templates. So we provide some templates for the constraints, the language model, and hopefully the templates can save a lot of efforts from the adding the new language and adding the new ASICs. But I think they need some efforts. But I think fortunately, the efforts should be done by the programmer developers rather than the users of compilers. So in that case, we can add the new constraints for the constraints for the new architectures and the languages maybe within 1 or 2 days. I'm not sure, but we have tried that before. So this is what I can answer, but it totally depends on the huge difference between the existing language and the new language, or the huge difference between whether it's a huge difference between the current ASIC constraint and the new constraint.
Okay, thank you. Okay, now let's thank the speaker Anna again. And we can move on to the second talk. Okay, the speaker of the second talk is Dr. Shuihai Hu. Shuihai, can you hear me? Oh, okay. Yeah, I can see your screen now. Hi, Shuhai, I cannot hear you.
Can you hear me?
Oh, I can hear you now.
Okay.
Okay.
Let me share my slides.
Okay. I will introduce you when you're sharing your slides. Okay. The second speaker, Dr. Shuihai, who is currently the chief scientist at Cluster, and he received his PhD degree in computer science from HKUST in 2019. And before that, he received his bachelor's degree in computer science from USTC in 2013. And Shuihai's interests are mainly about data center networks and machine learning systems. Okay, let's welcome Shuihai.
Thanks for a great introduction. Hello everyone, I'm Shuihai Hu from Cluster and HKUST. Today, I would like to talk about our work areas, which proposes a new building block to augment proactive transport. Before I start, I would like to share one thing about this paper. So a workshop version of this paper was accepted by Apnet 3 years ago. So actually this paper may be the first silicon paper that comes from Apnet. Okay, so let's start now. In recent years, as you may know, the link speed of production data center networks grow very fast, from 1G to 10G to 100G, with 200G on the horizons. Given this trend, congestion control in data center networks have become much more challenging. With link speed increased by 10 to 100 times, today's data center networks have much higher bandwidth delay product and more burstiness, and the flows now finish in much fewer RTTs, leaving the transport very little time to react to congestion. Today's congestion control are mainly achieved using reactive protocols. Reactive algorithms such as TCP and DHCP react only after congestion already happens. Reactive solutions have long-standing problems, including switch queue buildups, serial loss under incast, and very slow conversion speed. With higher link speed, all these problems now become worse. Proactive congestion control solutions, or PCC, have drawn greater attention in recent years. Compared with traditional reactive solutions, proactive solutions have several advantages, including near zero queuing, zero packet loss, and faster convergence. Unlike reactive solutions, the key idea of PCC is to proactively schedule network transfer using credit, based on the availability of network resources. The idea of PCC can be realized in several ways. For example, FastPass employs a centralized arbiter to enforce a tighter control over network transfer. PDQ and TFC leverages switches to explicitly allocate link bandwidth among the passing flows. ExpressPass, NDP, and Homer use receiver-driven, credit-based approaches to explicitly schedule the arrival of data packets destined for different receivers. While being promising, all existing PCC solutions require one HRTT to prepare the schedule. In high-speed networks, we find that the cost of delaying all flows by one HRTT can be very expensive. Our observation is that at a high link speed, a large portion of flows could complete in the first RTT. In this figure, we show the fraction of flows that could have been finished within the first RTT under different link speeds. Although our measurement methodology is idealized, the results suggest a very clear trend that the rise of high-speed data center networks makes the first RTT much more important. As we can see, at a 100G link speed, 30 to 80% of flows could have been finished within the first RTT. However, existing solutions cannot well handle the one HRTT problem. They mainly fall in two categories. One line of work chooses to pay the cost of the one HRTT. For example, in ExpressPass, the sender will send a credit request to the receiver on the arrival of a new flow.
On receiving the credit request, the receiver will send the credits to the sender. The sender will then send the data to the receiver after it receives credit. So in this process, all flows are delayed by at least 1 RTT. At high speed, the cost of wasting first RTT can be expensive. To demonstrate this, we measure the FTTs of 0 to 100 kilobytes small flows with 100G link speed. Flows are generated according to cache follow workload. As we can see, compared with idealized solution, 80% of small flows take 1 extra RTT to complete when under express path. A second line of work that new flows blindly send the traffic in the first RTT, such that the 1 extra RTT can be removed. For example, in Homer, on the arrival of a new flow, the sender will send a BDP of unscheduled data packets. This unscheduled traffic, however, may cause large queue build-ups and severe packet loss. As a result, good properties of PCC will be violated. To demonstrate this problem, we study the flow performance of 0 to 100 kilobytes small flows on the Homer and idealized solution. Flows are also generated according to the cache follow workload. As we can see, compared with idealized solution, the tail FCT on the Homer is extremely long. This is because some scheduled packets get lost due to buffer overflow and trigger flow timeouts. The results indicate that blind burst can cause serious performance downgrade for PCC. To this end, it's natural to ask such a question. Can we eliminate the 1 RTT extra delay while preserving all the good properties of PCC? Our answer to this question is yes. Now we will talk about the design of ERS. This is a design overview. As we can see, ERS mainly contains 3 components: rate control, selective dropping, and loss recovery. ERS adopts a minimal rate control at the end hosts. All flows start at a line rate in the first RTT. This can maximize the chance for new flows to fully utilize spare bandwidth. In the network, to safeguard scheduled packets and preserve all the good properties of PCC, ERS introduces a novel selective dropping mechanism as the switch. More details will be introduced later. And given ERS has safeguarded the scheduled packets, loss recovery is needed only for the first RTT unscheduled packets. In our design, we leverage the well-protected PCC as a safe and efficient means for recovering lost unscheduled packets. In the next, I will introduce the selective dropping mechanism in details. At the end host, this mechanism performs packet tagging. Unscheduled and scheduled packets will be tagged with different tags. In the network, switches perform selective dropping to protect scheduled packets over unscheduled packets. So what is selective dropping? As we can see, selective dropping is a switch buffer management scheme. It configures a dropping threshold at the switch egress queues. When queue occupancy reaches the preset dropping threshold, the incoming packets carrying high priority tag will get dropped. In contrast, packets carrying low priority, the incoming packets carrying low priority tag will get dropped. In contrast, packets carrying high priority tag can still enter the queue and get served. In the next, I will explain why this works. So when network is underutilized, unscheduled packets will enter the switch queues. As a result, spare bandwidth is utilized and there is no 1 RTT extra delay. But when network is fully utilized, unscheduled packets are selectively dropped. As a result, scheduled packets are not affected and all the good properties of PCC are well preserved. While the selective dropping mechanism is appealing, the key question is how to implement it with existing commodity switches. We leverage ECN, a built-in function of commodity switches for the implementation. So what is ECN? ECN is a well-known switch mechanism which performs congestion notification while marking a specific field in the IP header. In the IP header, there's a 2-bit field called the ECN field. This field has 4 code points in total. As shown in the table, 00 means a flow is not ECN capable. 01 or 10 means a flow is ECN capable. And 11 indicates that a flow has encountered congestion in the network. In our past test-bed experiments with ECN, we made an interesting observation. Let's assume the Q occupancy reaches the ECN marking threshold. Our finding is that if a packet is ECN capable, it will enter the queue and get ECN marked. But if a packet is not ECN capable, it will be dropped by the switch. So based on this observation, we can implement the selective dropping mechanism by reinterpreting the ECN marking function. At the end host, we tag scheduled packets as ECN capable and unscheduled packets as ECN incapable. At the switch, we simply set the ECN marking threshold equal to the selective dropping threshold we want to configure. With the above simple configuration, we can implement the selective dropping mechanism using already existing commodity switches. Priority queuing is an alternative solution to the selective dropping mechanism, as shown in the figure. By having scheduled packets enter high priority queue and unscheduled packets enter low priority queue, we can also ensure unscheduled packets only utilize the spare bandwidth for the first RTT transfers. However, priority queuing has mainly 2 drawbacks. First, it will require 1 additional queue for each service class, such that the number of supported service classes will be reduced by half. Second, due to the queuing delay in the low priority queue, there can be packet reordering problem. We have a simple example to illustrate this. As shown in the figure, a sender sends 3 unscheduled packets followed by 3 scheduled packets. In the network, scheduled packets will be served with high priority. So as a result, there's a chance that scheduled packets with a larger sequence number will arrive at the receiver prior to the unscheduled packets with smaller sequence number, which results in the packet reordering problem. Now we talk about how we recover the lost unscheduled packets. With the selective dropping mechanism, scheduled packets are protected from congestion loss, so we don't need to design a mechanism to recover scheduled packets. However, unscheduled packets could still suffer from congestion loss under heavy load. To handle this, we designed a faster recovery scheme for the unscheduled packets. The first step is to detect loss quickly. To do that, we enable per packet act for each unscheduled packet. In addition, we also designed a tail loss probing mechanism for quickly detecting the tail loss of unscheduled packets at the end of first RTT. The second step is to retransmit lost unscheduled packet quickly. Our idea is to reuse the preserved PCC to guarantee retransmission. This is done by retransmitting lost unscheduled packets only with scheduled packets. This is the evaluation setup. For our test-bed evaluation, we implement an errors prototype with DPDK. We built a small testbed using 8 servers connected to 1 Mellanox 10G switch. As for our simulations, we conduct experiments using 3 simulators, including IS2, Apnet++, and HTC. We use 100G multi-tier span-leaf DCN topologies and generate flows according to realistic production workloads. First, we evaluated whether errors can assist express paths to remove the 1 RTT extra delay without hurting the good properties of PCC. These 3 figures shows the flow completion times of 0 to 100 kilobytes more flows across the 3 workloads, including web server, cache follow, and web search. As we can see, with errors, a large portion of small flows complete within the first RTT. This indicates that errors can assist its path to significantly speed up small flows by removing the 1 RTT extra delay. Second, we evaluate how errors can assist the Homer to preserve the good properties of PCC without posing new flows in the first RTT. These 3 figures show the FCTs of small flows on the Homer with and without errors across 3 workloads. As we can see, without errors, flows suffer from very large tail FCTs due to packet loss caused by first RTT burst. But with errors, there is no packet loss and the tail FCT is reduced from more than 100 milliseconds to be less than 800 microseconds. This indicates that errors can assist the Homer to eliminate large queues and the loss of scheduled packets, thus significantly improve the tail FCTs. Third, we also evaluate whether errors can assist NDP to achieve similar performance without support for expensive customized switches. The 2 figures on the left show the FCT of small flows on the NDP with and without errors across 2 workloads. The 2 figures on the right show the average and the maximum queue length on the burst schemes using web server workload. As we can see, regarding all the measured metrics, burst schemes achieve very similar performance. The results indicate that errors can assist NDP to achieve similar performance without using expensive customized switches. At last, let me do a brief recap of errors. Errors is motivated by the problem that proactive transports require 1 extra RTT for scheduling packet transmission. To solve this problem, we designed errors, a general building block for augmenting existing PCC schemes. With errors, 3 important goals are achieved, including eliminate 1 RTT extra delay for new flows, preserve all the good properties of PCC, and work with commodity switch hardware. This is the end of my talk, and thank you so much for your attention. And I'm pleased to take questions.
Okay, thank you for the nice talk. And is there any questions from the audience? Okay. Zhang Qi has a question, and you may
okay.
You may
can
raise
you hear
the
me?
question now. Okay.
Yeah,
I can hear you.
Okay, thank you for your presentation. And I have a problem that is, you have mentioned the reordering problem, and I wonder how does the EOLS get rid of the reordering problem?
Thanks for a good question. This problem is about the reordering problem. Yeah. Let me go back here. Priority queuing will have the packet reordering problem, but for errors, actually, it will not have the packet reordering problem. This is because we only use a single queue in the design of errors, as shown here, and we don't change the transmission order of the packets. Yeah.
Okay, that's because we have only 1 queue, right?
Yeah. If you have congestion or if the queue occupancy exceeds the dropping threshold, we simply drop the unscheduled packets. Yeah.
Okay, and about the loss recovery, right? Can you turn to the loss recovery page?
Yeah.
And I just don't quite understand the the last line. What does that mean to reuse the scheduled packets to retrieve?
Because here in the design of errors, the scheduled packets are well protected. Yeah, so scheduled packets will not get dropped due to congestion. So, and if an unscheduled packet get lost, the sender will retransmit this unscheduled packet using scheduled packets, whose transmission is guaranteed by the PCC scheme. So you only need to retransmit once for each lost unscheduled packet. Yeah.
Okay, thank you.
Okay, I see Li Tong also has a question. And Li Tong, you may ask your question now.
Okay. Very nice talk and a detailed talk. But I still miss some small details about the rules in your solution. For example, the sender, the receiver, and the switch. So what is the rules of this of the sender and the receiver and the switches? And also, is your solution transparent to the other solution, for example, HOMA or NDP or other solutions? Is it transparent?
Yeah, it's transparent. So actually, you can refer to the implementation section of our paper. We have a lot of discussions about how to integrate our solution with existing PCC solutions. Yeah.
Okay, I see. So what you did is only on the switch? Or
No, we actually we need a cooperation between the end host and the switch. At the end host, actually, we do a very simple rate control. We simply let the new flows start at a line rate. And we also need to do packet tagging. Yeah. Such that the switch can do a selective dropping based on the tagging, which done before at the end host. Yeah.
So you mean here the end host is the sender, is it?
Yeah, end host is the sender. Yeah.
Okay, I see. Thank you.
Okay, since time is limited, so we have no further questions now. And let's thank the speaker Shuihai again. And now let's move on to the third talk. And the speaker of the third talk is Zhiqiang He.
Okay, let me stop.
Okay. And Zhiqiang is now a PhD student at USTC, so he's very young in this session. And his research interests include RDMA, network virtualization, and cloud computing. And his advisor is Professor Bei Hua at USTC. Now, let's welcome Zhiqiang. Hi, Zhiqiang, can you turn on your microphone? Okay.
Oh, can you hear me?
I can hear you now.
Okay. Thanks for the Professor Chun Huang for the introduction. Well, my name is Zhiqiang He. A first-year PhD student from the University of Science and Technology of China. My talk today is about a new RDMA network virtualization solution suitable for VPC. This is joint work with researchers at Huawei and Professor Zhili Zhang from the University of Minnesota. And Dongyang Wang and I are both first authors, and Binzhang Fu is the corresponding author. And I performed this work during an internship at Huawei. In the public cloud, VPC is used to let users define a virtual network for their virtual machines. Nowadays, VPC needs a high performance virtual network because more and more network performance sensitive applications are deployed into the VPC, such as large scale machine learning systems, HPC applications, and so on. At the same time, RDMA is currently an important technology for building high performance networking in a data center. For now, the RDMA network can provide about 200 gigabits per second or higher throughput, and a 2 micro round trip latency under one switch. So bring RDMA into VPC is worthy work. For the traditional TCP/IP network, VPC uses packet-based network virtualization to provide a virtual network for each user. Let's first give a demo to show how it works. Suppose we have 4 virtual machines on 2 host servers. With VPC, we can join them into one virtual network and assign them with any IP addresses as we like. To allow the virtual machines for communicating with each other with the configured virtual IP addresses, VPC introduces a virtual switch on each host server to adjust and route the packets. Suppose virtual machine A wants to send some data to virtual machine D. It just writes both the data and virtual machine D's IP address to a network packet. Then the packet will be injected into the virtual switch on the host. However, for now, the packet cannot be routed on the host network because the host network cannot understand the virtual IP address. So the virtual switch will encapsulate the packet with the host destination IP address. And then the packets can be successfully delivered to the destination host. And the destination host server simply trims off the extra host header and deliver this packet to the virtual machine D. However, packet-based virtualization cannot be directly applied to the RDMA network. Let's show the problem by compare the packet processing between the TCP network and the RDMA network. In a virtualized environment, before injected into the network, packets will go through the virtual machine, the host server, and the ARNIC. Typically, both virtual machine and the host are software-based, and the NIC is hardware-based. In the TCP IP network, the network stack is in guest OS kernel. Data sent from the application will first be handled by the network stack, and the packets will then injected into the host. So we can use a virtual switch on the host to perform packet-based network virtualization. However, things looks different in the RDMA network. Compared to the traditional TCP IP network, RDMA offloads the network stack to the hardware called ARNIC. Data sent from the application are directly DMA'd to the ARNIC. Then the network packets are encapsulated in the ARNIC. So we can see that the RDMA bypasses the host software and thereby the virtual switch. So we cannot directly use the virtual switch to realize network virtualization for RDMA. So where and how to realize RDMA network virtualization? To find out where to realize network virtualization, let's first take a look at the RDMA communication workflow in detail. Suppose the client application on the left virtual machine wants to send some data to the server application on the right virtual machine. Both of them should go through 3 stages. First, they should set up QP with the peer's IP address. Well, a QP is the same concept as the socket endpoint in the TCP IP network. With the QP, client and server can then call the send and receive separately to perform data transmission. Once the data finishing the data transmission, the application will enter the cleanup stage to destroy the QP and other resources. For more details, let us zoom out the left side and push the right side onto the right corner. And we involve RDMA driver on the host and RDMA stack on the ARNIC to show what just happened in each stage in detail. The QP setup stage will create a context called QPC in the RDMA driver and write the peer application's IP address into it. Then the QPC will be cached on the ARNIC and used by the RDMA stack for packet processing. Once the QP is created and the QPC is configured, the application now can send data. The data sent from the application will be directly DMA'd to the ARNIC. Then the RDMA stack on the ARNIC will encapsulate the data with the destination IP address. Last, the packets will be injected into the network. As we can see, QPC is the key for the RDMA stack to encapsulate the network packets. So the basic idea is that we can virtualize the RDMA network by controlling the QPCs. For example, we can replace the virtual IP address to the host IP address for network virtualization. And since all the QPCs are maintained on the RDMA driver, we can perform QPC controlling in pure software. Following the basic idea, we propose MassQ for RDMA network virtualization. Now we'll give a C at MassQ's architecture. To control all the QPCs, MassQ introduced software on the host. And any requests potentially operating the QPCs will first be forwarded to the MassQ software and then delivered to the ARNIC for further processing if needed. And for requests only referring the QPCs for data transmission, MassQ just leave them untouched. These requests still bypass host software, so the performance of RDMA communication still remains. With this architecture, MassQ can provide two good features. First, with the MassQ software, it has the capability to realize network feature required by the VPC. Second, since any data transmission bypasses the host software, the performance of the RDMA communication still remains. However, to build a well-functional RDMA architecture, RDMA for the VPC based on the above architecture, we have three challenges to solve. First is how to provide a ROCE device in a virtual machine. This is important for supporting the applications who access the RDMA device using an IP address. Second and the third is how to realize network virtualization and the application of security rules in MassQ's software. In the following, I will introduce MassQ's design kit mechanism to solve the three challenges, and the design details can refer to our paper. Well, first is how does MassQ provide a ROCE device in a virtual machine? A standard ROCE device consists of two interfaces, including an Ethernet interface and an RDMA interface. For best capability, the two interfaces should be both appear in the virtual machine. To this end, MassQ used the generic Ethernet interface virtualization method to provide the Ethernet interface, and used the hybrid I/O virtualization method to provide the virtual RDMA interface. The problem is that the two interfaces are separated, so vBond is proposed to bind the two interfaces to provide a ROCE device so that the application can access the RDMA network using an IP address. We now give a C at MassQ's design on network virtualization. The core idea of network virtualization is to replace the virtual IP address in the QPC to the host IP address. To show how it works, let us first add an IP address for each host server for where the virtual machine lives. In the QP setup stage, the MassQ software replaced the virtual destination IP address with the host destination IP address, and then writes it into the QPC. After the QPC is cached, data sent from the application will be encapsulated with the host IP address by the RDMA stack. Then the packets will be injected into the host network and will be routed to the target virtual machine. To this point, network virtualization is achieved. We now give a C at MassQ's mechanism to prevent any bad guys from injecting traffic into the network. First, for each QP setup request, MassQ software will check the request whether they are allowed by the security rule. If the request is illegal, the MassQ software will reject it. And what if a security rule is updated to mark the QP is illegal during data transmission? For this condition, MassQ software explores the QP state in the QPC to shut down the QP. By changing the state of the QP to error, any subsequent data sent from the application will be dropped by the ARNIC. So we believe that by combining the two-level checks, bad guys won't have a chance to inject the traffic into the network. Now for the evaluation. In this part, we want to show that whether MassQ can provide competitive performance. We compare our solution with three other RDMA networking. Host RDMA and SRIOV are involved as the baseline. And the free flow is the newest software-based solution for RDMA network virtualization. All the candidates are evaluated in the same test bed consisting of 2 servers directly connected by Rocky NICs. And each server is equipped with 2 powerful Intel CPUs and big enough memory. And we run virtual machines using Camel and containers for free flow using Docker, because free flow's prototype can only support containers. And we first use the perf test to measure the latency for sending or writing a 2-byte message. The result showed that MassQ can achieve the same latency as SRIOV. MassQ's latency is a little worse than host RDMA, because MassQ's default mode will use the RNIC virtual function to enforce queues. So we found that the RDMA performance over virtual function is worse than that over the physical function. So if queues is not needed, MassQ can directly map the queue piece to the physical function. Our experiment showed that MassQ can achieve almost the same latency as the host RDMA by mapping the queue piece to the physical function. We also use perf test to measure the throughput with different message sizes. The result showed that MassQ can achieve the same throughput as bare metal RDMA for all message sizes. For messages less than 8 kilobytes, MassQ performs better than free flow. And we also choose 3 typical application benchmarks to test MassQ's performance. We included the Graph 500 benchmark for the HPC scenario and the key value stone for the web system scenario, and the Spark RDMA for the big data scenario. The results show that MassQ performs well in all different applications. And in the key value stone benchmark, MassQ achieved 10 times better throughput than free flow. Well, finally, does MassQ introduce any overhead? MassQ takes a slightly longer time in the QP setup stage. Well, in our test case, the overhead is about 11% longer compared to SRIOV. Actually, for most applications, the QP setup stage is not on the critical section of the application's overall performance. So actually, the overhead can be negligible. And now for the conclusion. We conclude by summarize the contributions of this work. MassQ first proposed to virtualize the RDMA network in the QP setup phase. And it further proposed 3 practical mechanisms to realize features, including Rocky device abstraction, network virtualization, and applying security rules. These features are required by the VPC. And a prototype of MassQ is implemented and evaluated against the big data and HPC applications. The experiment results show that MassQ can deployed in virtualized environment with negligible overhead. Here are some future work worth to explore. First, the containers are also widely used in public cloud, so we can use MassQ's method to bring RDMA into containers. And RDMA-capable virtual machine migration is also a very important feature in VPC. So support the live migration of RDMA-capable virtual machines is also worth work. Thank you. Questions welcome.
Okay, thanks for the nice talk. And is there any question from the audience? You may raise your hand or input. Okay. There is a question. And okay, you may ask now. Zhang Menghao.
Very nice talk. I have a question. What's the difference between your solution with hardware-based solutions?
Hardware-based, you mean offloading the virtualization logic to the hardware?
Yeah.
Well, we definitely can offload the virtualization logic to the hardware. like Smart NIC. And however, hardware-based solution depend on special hardware to realize network virtualization, while MassQ is a software solution. So MassQ can be applied with almost all kinds of routing NICs. And hardware-based solution potentially has scalability issue. And this is also discussed in our paper. You can refer to our paper for more details. Oh, that's the answer.
Okay, and there is another question from Jia Chenjun, and Chenjun, you may ask now.
Okay, can you hear me?
Oh, yes.
Okay, let's talk. I have a problem about, and you just said that you just replace the IP address. So when the packets reach the destination host server, how can they are routed to the right virtual machine? Thank you.
Good question. In addition to IP address, RDMA uses QP number to distinguish different QPs. So after the data packet reaches the host server, MassQ further uses the QP number to deliver the data packet to the QP belonging to the target virtual machine. Oh, that's the answer.
Okay, if there's no more questions, let's move on to the next speaker, and thanks Zhiqiang again. Okay, and Zhiqiang, you can close your screen sharing now. Okay. Okay, our next speaker is Yunfei Ma from Alibaba. Okay. Yunfei Ma is now a senior engineer in Alibaba, and before joining Alibaba, he was a postdoc at MIT Media Lab. And his research interests include wireless networking systems, AIoT, and multimedia transport protocols. And he got his PhD from Cornell University and bachelor's degree from USTC. And he has published more than 10 papers in top conferences, including CCOM, Mobicom, and NSDI. Okay, let's welcome Yunfei.
Okay, so can you hear me?
I can hear you.
Okay, and thanks so much for the introduction. Hello, everyone. My name is Yunfei Ma. I'm currently a research engineer in the Alibaba Group Network Research Team. And today in this talk, I'm going to introduce NFC Plus, Alibaba's next generation RFID technology for large-scale logistic application. Okay, let's start. So the reason why we want to focus on logistic application is because today's major internet companies such as are transforming traditional e-commerce into what is called a new model or online to offline model. And over the past few years, we have witnessed the great success of many companies following this transformation all over the world, such as Walmart, Amazon, eBay, and of course, Alibaba. And we know that the booming of O2O is just about to start. Now let's take a look at the chart showed here. And we can see that today's online sale is just 10 to 20% of the whole online and offline combined together. There is still a lot for the online to catch in the offline space. And so we can see a $1 trillion opportunity as the O2O trend continue to grow rapidly to close this gap. And more importantly, this year, the COVID-19 pandemic may completely change the lifestyle of people on Earth. Now, many people like me totally rely on O2O grocery and food delivery for living. So we expect these changes to further accelerate the growth of O2O services offered by major internet companies. And as one of the largest O2O companies in the world, Alibaba Group hosts many subsidiaries such as Cainiao, Hema, and Ele.me, which covers a variety of O2O services from not only in logistics, but also in new retail such as food and grocery delivery. And now in this talk, what I'm going to tell you is a core challenge people face in this ever-growing O2O service That is how to do efficient object identification at large scale. Now let me explain to you why we need object identification. So take Cainiao logistic network as an example. So the product you purchase online have to be delivered as soon as possible through a logistic network to arrive at customer hands. And in this scenario, we need to identify the package in almost every logistic operation in order to route the package to its destination. And today, you can usually see a label like this attached to a package delivered to you, which is for this purpose. However, the problem is that the flow of today's logistic network is becoming extremely large. And for example, the total delivered package number of Cainiao in the year of 2019 is 30 billion. And the number is expected to grow to be 150 billion in the year 2025. To meet the demanding scale and efficiency challenges, we can no longer rely on traditional barcode and QR code, which becomes extremely slow, labor-intensive, and error-prone. And to solve this problem, UHF RFID has been widely acclaimed to be the vital enabler for automatic object identification. But there is a big problem in reality. And the problem is that although UHF RFID has been there for more than 30 years, and after numerous trials in the real-world deployment, the UHF RFID only finds its use in very specific application scenario, such as apparel retailers. And so what is the problem? And the problem is about accuracy. And after talking with many vendors and logistics service providers, and we find that the main issue of UHF RFID today is on the reading accuracy. Consider this example. A worker is using a trolley to bring 20 labeled packages out of a warehouse. And the trolley will first pass the checking zone to make sure that everything he got is correct. And by using RFID, a worker will not need to scan the label manually. And instead, the reader in the checking zone can do the detection automatically. But there can be three kinds of results. The first one is that all of the 20 tags are detected, which is great. But life isn't always perfect. And sometimes there will be 19 tags detected, which means misreading happens. And sometimes there will be 21 tags detected, which means cross-reading happens. And both results may lead to package loss and introduce significant verification cost. And this problem really hurdles today's RFID deployment. And to understand the problem, we need to take a closer look. First, the reason of misreading is that the UHF signal is affected a lot by blockage. So when an object is placed between a reader and a tag, and the signal traversing it will be attenuated a lot by the blockage, and especially when the object contains liquid and metallic content. And nearly everything in our daily life will cause an attenuation to the RF signal, which leads to the misreading problem. And the second problem is the cross-reading. As shown here, when wireless signal propagates, it will be reflected by indoor environments, and the signal reflected might be combined constructively at even some remote locations. As shown in this plot, the signal strengths can be pretty large, even at a long range, which results in cross-reading tags even far away from the checking zone. And this phenomenon gives rise to the cross-reading problem. And because of the mis and cross-reading, the accuracy of today's UHF RFID is only around 90%. But what the vendors, logistics service provider really expect is an accuracy above 99.9%. And this 9.9% difference may lead to billions of dollars lost for handling misdelivered packages. And many vendors even discard RFID setup after deployment because they do not see any benefit with such a low accuracy. And therefore, the thing we want to emphasize in this talk is that in the real-world deployment, the median error or even 90th percentile error make no sense. It is the tail error that matters most, and we need to really focus on to reduce the tail error. So from the above analysis, we find that the main issue is really on the physical properties of the communication signal we use. And any algorithm-based techniques will not solve the fundamental issue introduced by the physical property because it is inherently determined by the frequency. Therefore, we choose to change our mind from struggling with the UHF electromagnetic wave and re-architect today's RFID system. So in our research, what we find is that the NFC at the frequency 13.59 megahertz with magnetic signal may offer much better physical properties. First, unlike the UHF signal, the material impact to magnetic signal is very small. And by fixing the location of the reader and tag, we can measure the impact by calculating the signal difference. So we take bottled water, canned Coke, and boxed milk as an example, and the object influence to NFC signal is much, much smaller compared to that of the UHF RFID. Moreover, for a carrier frequency at 13.59 megahertz, the wavelength is about 22 meters, which means that the reading operation will be located in the near field region. And the waveform in this case will be pure magnetic, which means that there will be no multipass effect. And additionally, the signal strength will also drop much faster compared to the UHF RFID far field signal. And this will effectively prevent radios from leaking. And as a result, the NFC reading will be perfectly limited to a range and will not cause cross-reading problem. Because of these properties, it seems that NFC is a good solution compared to RFID, UHF RFID. However, it also has its own limitations, which is the reason why today it is not adopted. And there are two main issues with NFC, range and orientation. First, because the magnetic signal attenuates much faster, the typical reading range of NFC is really short. For example, the commonly used portable NFC module only covers several centimeters. And even the longest NFC today will only cover 90 centimeters in the most favorable conditions. And secondly, the magnetic signal is a closed loop field. The orientation of the tag will influence the strength a lot. For example, when the tag is perpendicular to the field, the tag signal is maximized. But if the tag is parallel to the field, the tag cannot be read. And because of these two issues, the NFC technology today is limited only to proximity applications. And to fundamentally overcome these barriers, we propose NFC Plus. NFC Plus is a system that solves these two issues simultaneously. NFC Plus is the first system to enable NFC in logistic application. And it is also extend the NFC communication range from several centimeters up to 3 meters. The NFC Plus is fully compatible with ISO protocols and can work with today's commercial NXP chip. It is also very accurate with accuracy above 99.9%. And we realize NFC Plus through multiple innovation thrusts, including resonance engineering, a new self-interference cancellation in the transceiver, MIMO beamforming algorithm, and mag repeater. But in this talk, for the interest of time, I will only cover the very basics of resonance engineering, but I do encourage you to read our paper for more technical details. In order to boost the range, let's first take a look at the architecture of traditional NFC system. An NFC system consists of a reader with a TX coil acting as an antenna, and the tag will also have a coil connecting to its chip. And they are designed following the principle of inductive magnetic coupling, as shown here. The reader will generate magnetic fields which pass through the tag coil, and then the tag and reader will be coupled with each other. Therefore, from the traditional point of view, the coils of the reader and tag will form a loosely coupled transformer, and this model can describe the behavior of the circuit components. But the problem is that it also lumps all the influence of range, coil parameters, and coil orientations into the single coupling factor, which is sometimes difficult to decompose. And in our design, we're looking in a modern communication view so that we can implement the advanced communication techniques to NFC. And because of the low coupling between the reader and the tag, we can neglect the tag influence to the reader and then separately analyze the magnetic signal generated by the tag and the signal received by the tag. More specifically, our analysis procedure follows 3 steps. The first step is to calculate the current on the reader coil, and then using the calculated current to analyze the generated magnetic field. And finally, based on the magnetic field, the signal received by the tag can be calculated based on the Faraday law of induction. And following this analysis procedure, we can decouple the influence of reader circuit, range, and tag orientation, and then solve the range and orientation issues independently. And a core technique we use repetitively in our design is called resonance engineering. Resonance describes the phenomenon of increased amplitude that occurs when the frequency of a periodic force is applied. And resonation can happen by adding a shunt capacitor to the reader's coil. The circuit will form an RLC resonator, and the energy stored in the capacitor and inductor will transfer into each other periodically. And this periodic force will boost the current on the reader coil, which will be Q times that from the power source. And the Q here is called the quality factor. And after calculating the magnetic field strength in the second step, and we can see that the signal strength is proportional to Q, then a larger Q means a longer range. But there is a fundamental trade-off between resonance and bandwidth. A larger Q will shrink the bandwidth and cause problems in the receiver. As shown here, the reader will generate a signal at a carrier frequency of 30.59 MHz. Then the tag will do double sideband modulation with a small subcarrier. And when the TX and RX are sharing the same reader coil in the traditional architecture, resonating at 13.59 MHz, a larger Q will suppress the tag signal by filtering effect, and this will reduce the reading range. But in fact, the required bandwidth is mainly occupied by the subcarrier gapping or spacing. For TX or RX to communicate, the bandwidth is smaller than 100 kHz. So there will be a large room for larger Q if we separate the TX and RX coil. And let the TX coil resonate at 13.59 MHz and RX coil resonate at 14.01 or 13.11 MHz. And with this separation design, the Q value can be boosted more than 20 times compared to the traditional NFC architecture. And based on this resonance engineering principle, we have built our customized reader, and the hardware design contains a multiple channel TX module, a non-self-jamming receiver, and STM32 ARM processor for the control. And the coil of the reader is implemented as a gamma loop, and the tag we use in our evaluation is the commercial NXP ISO NFC tag chip. And on the software side, we implemented the ISO compatible protocol in C++, which contains multiple access and anti-collision functions, and it also offers a reading rate up to 50 tags per second. We first evaluated the range performance. The distance between the tag and the reader are changed to find the longest range of commercial readers. So the iPhone or the Samsung Galaxy phone can only read tags around 1 centimeter away, and the open source NFC platform Proximark can read tags at a distance of no more than 15 centimeters. As a result, they are mainly used as a tool for proximity application. And to our knowledge, the RD5101 reaches the longest reading range of NFC reader in the market, which can read tags up to 90 centimeters away in the most favorable conditions. And in our setup, the TX coil and the RX coil are placed 3 meters apart, and the tags move in between. And by utilizing the techniques proposed in NFC Plus, our system can cover the whole range of 3 meters. We then conduct a simple experiment to illustrate the effectiveness of NFC Plus magnetic beamforming compared to traditional NFC and UHF. And the tag will be placed in front of the reader rotated by 180 degrees. And the measured signal loss is shown here. And we can see that both the UHF RFID tag and NFC experience more than 30 dB signal strength loss when its antenna is perpendicular to the reader antenna. While in NFC Plus, with the help of MacMIMO, the result shown is that even in the worst case, the NFC Plus only experience around 3 dB signal strength degradation. Here we show a real-time demo and show how the system works. And in the region, we deploy 2 TX coils and 2 RX coils covering a checking zone. The 16 NFC tags attached to most RF unfriendly merchandise, such as bottled water, canned Coke, and boxed milk. And the merchandise are placed on a trolley with random orientation. And the trolley is pushed through the checking zone, and all the UIDs of the tags are read. And notice here, there are no misreading and cross-reading. And in our evaluation, we did over 10,000 tags read to evaluate the tail error performance. Here is what we observe. We observe that the NFC Plus will miss only 0.03% of the tags passing through the checking zone, much better than compared to the commercial RD5101 NFC system, which misses 40%. When it comes to UHF, if all tags are placed in the line of sight from the reader, the UHF RFID system missed about 1.54% of the merchandise. And when the merchandise are placed with random orientation in UHF, the misreading rate of the UHF system jumps to 23% due to its low reliability under blockage. When doing the cross-reading experiment, we also place plenty of tags randomly out of the checking zone from the result in the second figure, and we can see that neither NFC Plus nor commercial NFC read any tag outside. But in contrast, the UHF RFID system experienced a 42% cross-reading rate. The poor cross-reading rate performance is an inevitable sacrifice when the UHF system needs to increase its output power to reduce misreading. Now let's conclude. In summary, the NFC Plus is the only system that we know that can cover long range with arbitrary tag orientation, achieving over 99.9% accuracy. And we also want to give 2 take-home messages. One is that the tail error is really crucial in real deployment, and researchers also need to keep an eye on this. And the second message is that we want to bring the magnetic communication back to researchers' focus because we find that the physical property of magnetic signal is extremely superior in many large-scale IoT applications. And with that, I would like to thank you for your attention. And now I'm happy to take questions.
Okay, thanks for the nice talk. And is there any questions from the audience? Okay, if there's no question, and I have a brief question, and can you change to page 17?
Okay, sure, no problem.
Yeah.
Okay, let me do this. Page 17, right?
Right. Yeah.
Okay.
Okay. In this high level, design, and I see that you have 4 innovations, and you achieve 5 design goals. So may I ask, since I'm not an expert in this area, so I'm wondering, so among the 4 innovations, what are the most critical for improving the communication range to 3 meters?
Oh, okay, that's a good question. So actually both 4 innovations are important to our design. But if you ask me what is the most important one, I would like to say it's the resonance engineering. Because as I also mentioned in the talk, it's the resonance engineering technique that allows us to fundamentally break the range limit. But after the resonance engineering, there's still plenty of work you need to do in order to achieve the goal. For example, with the resonant engineering, self-interference cancellation becomes very critical. If you do not have a very careful self-cancellation, the system cannot work. And also because we need multiple antenna to cover the orientation, and with a strong resonance, implementing a multi-antenna system is extremely difficult. So we also need a couple of techniques to let the system work with high Q.
Okay. Thanks.
Yeah, but the most basic technique we use here is the resonance engineering.
Okay. Okay. If there's no other questions, we can move on to the next speaker. And thank Yunfei again. The next speaker, Dr. Li Tong, is a senior researcher at Huawei now. And Li Tong received his bachelor's degree from Wuhan University and his PhD degree from Tsinghua University. And his research interests include transport protocol measurement design and implementation in both wired and wireless networks. And I remember that he published 2 SICOM papers in the past 3 years. Okay, let's welcome Li Tong again. Hi, Li Tong, can you turn on your microphone? I cannot hear you.
So,
okay, I can hear you now.
Okay, thank you for the introduction. So today I'm going to introduce TAC, Improving Wireless Transport Performance by Taming Acknowledgements. This work is done with the Tsinghua University and the Stanford University. So high throughput transport over WLAN becomes a demanding requirement with the emergence of applications such as UHD wireless projection, VR-AR-based interactive gaming, and so on. Particularly, the average throughput requirement is 100 megabits per second of an 8K video, whose peak throughput requirement might reach 200 megabits per second. For UHD VR-based application, the throughput even reached 500 megabits per second. It is reported that the average WLAN connection speed in 2018 was 30 megabits per second and will be more than triple by 2023, which, however, is still far from being satisfactory for UHD video-based applications. So most modern WLANs are based on the IEEE 802.11 standards. It is well studied that medium access overhead in WLAN can significantly reduce TCP throughput. This is because TCP ACKs cause internal interference on the same connection. When frames are operated in the MAC layer, the time period, including the interframe space and the random backoff period, is the extra overhead between the completion of the last frame and the starting of the next frame. Since the extra overhead for sending each packet is independent with packet size, ACKs cause almost a similar medium access overhead despite the much smaller size. As a result, the internal interference between data packets and the ACKs is non-negligible. To explain this internal interference more clearly, we have conducted emulations over wireless links. Basically, TCP sends an ACK for every 1 or 2 packets, which is frequent. As shown in the left figure, the throughput on the ACK path is relatively low, although the amount of the number of ACKs is very large, but the throughput is very low. But we can see, however, in the right figure, the throughput decreases significantly with the increase of the ACK frequency. So in wireless networks, we can see reducing ACK frequency has a positive effect on the transport performance due to the reduced contentions. But however, unfortunately, simply reducing the ACK frequency hurts TCP performance, which is called negative effect. This negative effect is because that TCP's transport control depends on frequent ACKs, and the packet cloaking algorithms are impacted when the ACK frequency is reduced excessively. So to summarize, reducing ACK frequency has both positive effect and a negative effect. So in this case, acknowledgements should be tamed. This paper aims to seek the optimal ACK frequency with corresponding improvements in transport mechanism to avoid the negative effect. And here are the takeaways. First, legacy TCP's delayed ACK cannot ensure minimal ACK frequency. It is far from being optimal. Second, our way of avoiding negative effect is not only tag, but also a tag-based acknowledgement mechanism. Third, a transport protocol applying an approximately minimized ACK frequency works better than expected. Let's start from the first one. So ACK frequency can be denoted by F with the unit of hertz. That is the number of ACKs per second, which can be reduced in two fundamental ways: byte counting ACK and periodic ACK. Byte counting ACK reduces ACK frequency by sending an ACK for every 2 or more incoming full-sized packets. The frequency is proportional to data throughput bandwidth. We can also reduce the ACK frequency by sending an ACK for every time interval. This is called periodic ACK. This is two fundamental ways to reduce the ACK frequency. In the other hand, the legacy TCP also adopt the delayed ACK. Delayed ACK actually it is using the byte counting ACK and also the periodic ACK, in which the data receiver may delay sending an ACK for every air full-sized incoming packets or by a given time interval. As recommended in the IFCs, air is limited up to 2, and alpha is tens to hundreds of milliseconds, and varies in different Linux distributions. When data throughput is high, the ACK frequency still might be large. On the other hand, when data throughput is low, the ACK frequency is always as high as that in the case of a high throughput, which wastes resources. This reveals that the frequency of TCP's delayed ACK is not bounded or not minimized under bandwidth change. In other words, TCP's delayed ACK is far from being optimal. So we propose tag, a new acknowledgement whose frequency is decided by BDP, the bandwidth and the delay product. The frequency of tag is the minimal value between byte counting ACK and the periodic ACK. Specifically, tag applies periodic ACK when BDP is large, and falls back to byte counting ACK when BDP is small. In this case, when data throughput is high, the ACK frequency is bounded. On the other hand, when data throughput is low, the ACK frequency is reduced proportionally. First, we estimate tag's positive effect over various wireless links. We built a UDP-based tool to assure that there is no negative effect. The sender keeps sending large UDP packets, and the receiver has implemented various ACK thinning technologies, including tag. When the trigger condition is met, the receiver sends one small UDP packet as an ACK. The result is that more number of ACKs are reduced in the case of a faster physical rate. For example, tag has the same frequency as TCP's delayed ACK over 802.11b links with a small RTT. However, for the 802.11ac links, the frequency of tag has dropped 2 orders of magnitude when RTT is 10 milliseconds, and 3 orders of magnitude when RTT is 80 milliseconds. Ideally, links with faster physical rates increase throughput improvement. TAG approaches the transport upper bound with a minimized ACK frequency. To conclude, our first takeaway is that TCP's delayed ACK is far from being optimal. This is because TCP adopts a max function other than a min function. However, our work in this paper has demonstrated that a min function is also able to achieve good transport performance. The key is to avoid TAG's negative effect. Then we give the second takeaway. Instead of simply applying TAG, a carefully designed TAG-based acknowledgement mechanism is the way to avoid TAG's negative effect. Here we list several major issues to handle in terms of loss recovery, round-trip timing, and send rate control, including congestion control and flow control. Next, we will give some case studies to better understand these issues. First, it is well known that head-of-line blocking incurs high delay of packet resampling and thus leads to transport performance decline. In the case of a legacy TCP, when packet 3 is lost, then the loss of a packet 3 will block the head of line with 8 subsequent packets in this case. And on the other hand, since TAG might be excessively delayed, applying TAG will further enlarge this delay incurred by head of line blocking. So we also give a case study. In this case, the loss of a packet 3 might block the head of line with 97 subsequent packets. So when loss occurs during the TAG interval, the excessive TAG delay disturbs loss detection, resulting in costly retransmission timeouts. TAG loss further aggravates this problem. So in terms of a round-trip timing, the initial RTT can be computed during handshakes. After that, the sender calculates an RTT sample upon receiving a TAG. The problem here is that multi-pile data packets might be received during the TAG interval. Generating only one RTT sample among multi-pile packets is likely to result in biases. For example, a larger minimal RTT estimate or a smaller maximum RTT estimate. In general, the higher the throughput, the larger the biases. Third, for congestion control, a burst of packets can be sent in response to a single delayed ACK. Since TAG might be excessively delayed, the burst send pattern may cause larger buffer requirement, higher loss rate, and a longer queuing delay if not carefully handled. Last, for send window update, TCP ACKs report the announcement window in the TCP header for flow control. Reducing ACK frequency might also lead to feedback lags and bandwidth underutilization. For example, assume TAG is sent every 50 milliseconds. TAG 1 notifies a 0 window due to the receive buffer runs out. Upon receiving this TAG, the sender stops sending data. In the case that the receiver buffer is released 5 milliseconds after sending TAG 1, due to the loss recovery, the sender continues to be blocked for another 45 milliseconds until TAG 2 is sent. So in this case, they waste opportunity of sending data. TAG loss further aggravates these issues. So to solve these issues, we propose a full TAG-based acknowledgement mechanism. There are some notable features for this mechanism which are important for reasoning about the differences from legacy TCP. First, apart from the ACK type of a TAG, we also introduced the ACK type of a IACK to assure timely feedback upon instant events. IACK and TAG are complementary. IACK assures timely signaling, while TAG acts as the last resort mechanism in the case of ACK loss. Second, when the loss rate on the ACK path has reached a critical level, tag should carry more information such as continuous range of lost packets or received packets. This is a little bit similar to Quick. With more types of ACKs and the more necessary information carried in ACKs, the tag-based acknowledgement mechanism, therefore, is able to send less number of ACKs, but are exactly what are required by transport. We further give the protocol design of the tag-based acknowledgement mechanism, in which the advancements in loss recovery, round-trip timing, and send rate control are the key reasons that TCP's dependence on frequent ACKs has decreased. Take the minimal RTT estimation as an example. The legacy way of sender-side RTT sampling is either inaccurate or expensive. In this paper, we sample the one-way delay at the receiver, and the tag carries the timestamps and the ACK delay for a packet who achieves the minimal one-way delay. The sender then generates the minimal RTT sample according to this tag. Because tag only carries the necessary information, the tag-based protocol design not only reduces overhead, but also ensures accuracy. For other advancements in tag-based protocol, we adopt a receiver-based loss detection, in which the packet number, the IAC, and the tag play different roles. Packet number is also similar to Quick, and the packet number enables receiver-based loss detection. IAC speeds up loss recovery, and the tag assures loss recovery robustness. In order to control the amount of send data, tag-based congestion control also should integrate with spacing instead of burst send pattern. Also, an IAC updating the announcement window should be sent without delay when the receive buffer runs out. I strongly recommend the readers to refer to the paper for more details about these technologies. To summarize, applying tag significantly reduces ACK frequency and improves performance ideally. However, simply applying tag probably falls short. What we really want for WLAN is a full tag-based acknowledgement mechanism that overcomes the hurdles for applying tag, using an approximately minimized ACK frequency to support efficient transport. We have conducted experiments on both wired and wireless links. The results show our third takeaway. A transport protocol applying an approximately minimized ACK frequency works better than expected. So we implemented TCP tag, a TCP implementation that applies tag and deploys the advancements as specified above. We co-designed the receiver-based BBR as a tag-based congestion controller. Here is the result. TCP tag achieves significant advantages over legacy TCP in WLAN scenarios due to less contention between data packets and ACKs. Specifically, TCP tag reduces over 90% of ACKs and also obtains an improvement of 28% on goodput. We further find TCP tag performs equally well as high-speed TCP variants in wide area network scenarios. This is attributed to the advancements of the tag-based protocol design in loss recovery, round-trip timing, and send rate control. This reveals that an approximately minimized ACK frequency works better than expected. Okay, I would like to conclude today's talk by summarizing the takeaways. First, TCP's delayed ACK is far from being optimal. Instead, tag adopts a mean fraction to assure the minimized ACK frequency in the context of network dynamics. Second, our way of avoiding tag's negative effect is a tag-based acknowledgement mechanism in which we define more types of ACKs and carry more necessary information in X, and then we are able to send less number of X. Third, an approximately minimized ACK frequency works better than expected. So tag-based protocol provides a good replacement of legacy TCP in WLAN and also works well in WAN scenarios. Moreover, tag and its corresponding improvements in transport mechanism can also be adopted into other stacks such as QUIC to compensate for scenarios where the acknowledgement overhead is non-negligible. This work is also being discussed in the IETF working groups. Please get in touch and we will be happy to discuss with you. That's all for my report. Thank you very much.
Okay, thanks for the nice talk. And is there any questions from the audience? You may raise your hand or type in the question. Okay, if there's no question, I have a question. Okay, Yunfei has a question, and Yunfei, you first.
Okay, I have one question to ask. So I understand that in the wireless scenario, right, by applying tag, you basically reduce the contention for the wireless resource, and that's how you get the increased throughput.
Yes.
But can you give more explanation on why in like WAN scenario, why you also see a lot of benefit from by applying tag?
This is a very good question, and actually we can see here, this is the WAN scenario results. Actually, we adopt the we integrate the TCP tag to a Stanford test bed in the WAN scenario, and we can see actually it works better than a lot of other solutions. It is because actually we are using the TCP BBR as a congestion controller, and this platform is a pantheon for all the congestion controllers. So if we can see that BBR and the TCP BBR, they works for here. The TCP BBR is a little bit worse than the TCP tag. It is because the TCP BBR, they are using a smaller buffer, sending buffer and the receiving buffer in the host. And actually TCP tag, because TCP tag, we increase our sending buffer and the receive buffer. So for this result, we have a little bit better result than the TCP BBR. But actually, for most of our other figures, I didn't put the figures into these slides. Most of the figures shows that TCP tag and the TCP BBR in the WAN scenarios, they have very similar behaviors and performance in the WAN scenarios.
Okay.
Okay. Is there any other questions? Okay, I have a question. Since your work is mainly designed for wireless network, so what about the power consumption? Because I remember that you employed multiple types of ACK mechanisms, and maybe you will have a recovery mechanism, and you maintain larger buffers. So what's about the power consumption?
This is also a very good question, because actually reducing the ACK frequency can save some power consumption, but actually we have already estimated that it's very limited, because if the host is not sleeping, then actually the power consumption will not be reduced very significantly. So your question is that because we add more logic in the host, in the end host, is it the power consumption will be larger? Actually, we can say it can be negligible, because actually if the node is not sleep for mobile devices, then the power consumption it's similar actually. And also actually we didn't introduce much process overhead, because the archetype for example the archetype is only just add one TCP option bit to recognize it. So actually the process overhead is very less.
Okay, thanks for your question. Thanks for your answer. Okay, now let's move on to the last talk in this session, and this is also the last talk in this Apnet. Okay, the last speaker, Biao, is from Alibaba, and he receives his bachelor degrees in computer science from Zhejiang University and his PhD degree from SFU, and he's working on network virtualization and cloud networking in Microsoft Windows team and Alibaba cloud network product team. And now he is the leading he is leading the smart network operation team in Alibaba Group. Okay, let's welcome Biao. Is Biao in the room? Okay, Biao.
Hello?
Okay, I can hear you now.
Okay, cool, thanks. Let me share my screen. 1 second. Can you first see the screen right now?
I can see your screen, and you may start now.
Okay, cool. My name is Biao. I'm from Alibaba Group, and today my topic is our V-Trace system is an automatic diagnosis system for persistent packet loss in a cloud-scale overlay network. It's a cooperation work between us and the Zhejiang University. So I will talk about it right now. And before I start, I will show you what it looks like in a cloud network. Actually, cloud network has millions of tenants. For them, they will have some traffic going through their tenant resource, for example, a virtual machine to the other virtual machine, cross different cloud resources, such as a virtual switch and a virtual router. And in a complicated scenario, they might even cross a VPC, which is a virtual private cloud network. So when that happens, if something bad goes on, it might get packet dropped in anywhere. For example, it might get dropped in a V router, or it also might get dropped in a core switch in underlay network. So it's actually a multi-layer network. In overlay, people see their virtual switch, virtual router. In underlay, we have our physical core switch, CSW, HW, and vSwitch. So that forms how the whole cloud network works right now. And when packet lost, there are many reasons packet might get lost. In one case, people might do some misconfiguration. For example, they misconfigure the ACL rules, and that can cause some packet get lost in virtual switch. In the other case, the cloud service providers, they might do some update to the resources or the underlay networks. When they do an update, that might also cause some packet loss. In both cases, we can classify the faults in two cases. One is we have some VFD faults. VFD means virtual forwarding devices, such as our virtual switch, virtual router. In this case, the VFD might get misconfigured, and so it drop packets consistently. The other case is a non-VFD faults. For example, our tenant, they might misconfigure their ACL rules, or they might just run out of their rate. For example, they bought a NAT gateway with 100 gigabyte bandwidth, but if they really run up to the limit of 100 gigabits, they will get packet loss also. So all these cases, they will see, okay, our packet get lost. In worst case, if the packet loss is consistent, there will be a network disconnection, and the network disconnection is very fatal. When that happens, people's business will get lost. Their customers cannot connect to their websites. They cannot watch videos through their URL. So that's a very urgent case we have to solve. In the other case, there might be some transitional problems, but that is more difficult to solve. So vTrace is trying to solve first of all, we are trying to solve right now the persistent packet loss, to solve it in a cloud scale, in a multi-layer network here. So actually, there are many scenarios we can see in an overlay network. For example, in internet, we might access our internet resources through VPC and the SLB. In our case, we might have different VPC connect to each other. In that case, the path will be different. The third case is we have our customer data center. They will connect to the cloud through a dedicated line, and that will cross different paths, especially different underlay physical switches to connect to our data center in customer side. So, but actually, as you can see, the paths will be very different, and then the underlying implementation of these devices are also very different. How do we find out when something goes wrong? In fact, we have to find it very quickly. For example, in this case, our customer find out they cannot connect from VM2 to VM7, and they might ask for some help. In a traditional way, our engineer will try to do a TCP dumping, or to try to do a package capture along all the paths. And then in the worst case, we don't know which path the customer traffic is going through. So that might take several hours to find out which path the traffic is actually going through, and which device we have to dumping or package capture. And in this case, it takes very long, and the customer satisfaction is very bad. So how do we solve it quickly? For example, in a few seconds, to find out across millions of devices across the whole globe, we find out which path the traffic is going through, and where the packets get lost, and the reason why. So that comes to our proposal, or is the topic. It's called vTrace. That is our solution here. So the design goal here is to design a system to display the complete journey of each target packet. So we don't need to guess where the packet is go to and how does go there. The other goal is to find out which node is the bad guy. Why is the reason? And the third one is define the root cause. Why it get the packet lost? Is it because ACL configuration, or is it because rate limit? To find the root cause so that we can give to the suggestion how to solve it. To meet the goal, we have to also need to solve three problems. First of all, if the bad thing, the packet loss is happening right now, we have to extract the information right away, so we cannot let the scenario goes off. The second thing is, how do we find out, do the diagnosis using a very low performance impact? So we cannot do the diagnosis which introduce a very bad performance impact to customer business. The third thing is, we have to do it when tenant doesn't need to do anything. If every time customer miss a problem, we ask them to work with us to find out the problem. That is also not acceptable for most of our customers. So that's the third thing we have to solve. So how do we get a balance between this root cause and the impact, and also achieve a non-invasive result here? This is the key important thing we have to solve in V-trace design. So we can see actually there are many prior related works here. The one type of work is called active network monitoring. In that case, we deploy some probe in customers' VM and do the ping pong, pin mesh or whatever, and that has a drawback is that the active monitoring packet might not go through where the traffic, the customer real traffic goes through. The path might be different, so it might not reflect the real problem path. The second type is called passive network monitoring. In this case, we have to ask customer to help us connect the data for us, and this is most likely not possible for millions of business enterprise customers. They might not give us a lot of data to analyze. The third type of method is called network debugging method. In this case, we do some monitoring and the path tracing, but that would not reflect the underlying root cause. It might give us which node is dropping the packet, but it will not give you the reason. So that's also a drawback. So V-trace is trying to solve this problem, giving the root cause, giving you the path, and at the same time, don't require any customer collecting data for us. So there are three essential steps to finish this whole automatic diagnosis process. The first one is do the packet tracing to trace the packet we are interested in. The second thing is to do in-depth processing to find out what the packet is doing in each node and give the information to the third part, which is called path reconstruction. In the third pass, we are doing the path construction and also give you the reason why this node is dropping the packet. So these three steps finish the whole V-trace design. Before we get to the V-trace implementation, let's see if we are doing it in a naive way, which is we can just do a packet per packet mirror. So each packet we do a mirror and send the same packet to an analyze engine or log system to do an analyze. But in this case, we will find out this way we cannot give the reason why the packet get lost, because it just mirror the packet, but it doesn't show you the debug information. For example, which flow table it has go through, and does it go through the ACL table? Does it go through a rate limit and mesh action? So it doesn't give you any information how this packet gets processed in each node. That we introduce that we cannot give the reason why this packet, how does it process, or why this packet get lost in the node. The second way is we implement a very powerful VFD. This VFD will do per packet in-depth checking. This will show you, this sample code will show you how we can do this if possible. So for each if-else logic in all our VFD, we write if else, if anything goes wrong, we do a debug output. And then in this case, we could put hundreds of probe and the debug information. But that, in this case, it will introduce a very heavy performance impact. Up to 18% the performance will get impact in this way. So that is also not possible, not acceptable for us. Actually, after we have spent a lot of time thinking about how to do a persistent packet loss, we found out we don't need to do a per packet analyze for all the packets consistently. If there is a persistent packet loss, we only need a subset of target packets and do an in-depth analyze in a low performance impact way. And then that will give us a very good output and the result and show what it might go wrong here. So how do we implement such a system that uses a subset of target packets and process it in a minimum impact performance way? That is the key to do the packet connection part. So this is our design to do this packet capture here. So that as you can see here, we have a source it's sending a data, it's sending packet through a VFD1, VFD2, VFD3, and until to the destination. So we have a control plane here. This control plane here, it will send a configuration how to measure and collect the data. There's such kind of policy along all the VFDs. And this packet capture is a 5-tuple mesh and action capture. It will capture the packet we are interested in. And also it will also send a command saying that we only capture a limited amount of packet. For example, 200 packet, that's good enough for us right now to figure out, to construct the whole path. When this policy is configured to VFD, the VFD will try to do a match and action way. So it will match the 5-tuple, and if the packet match this policy, they will be logged to a log agent, and then this log agent will send the information, all the information we need to analyze, send this information to the JStorm engine and analyze the packet. So the log will have a 5-tuple information, the packet ID we want, and the VFD information, and also a cost. Cost means whether it gets dropped and why it gets dropped. So after the first VFD, the second VFD, it does only the DSP mark, because at the first VFD when we match the 5-tuple, we change the DSCP so that this DSCP only mark this packet as an interested packet we want to analyze. That's the only step we have to go through a slow path. In a VFD2 and a VFD3, we don't have to go through the slow path. We only go through the fast path using a DSP matching, and then that's very quick. So in the VFD2 and the VFD3, we only use the DSP mark to match, and the net performance impact is very, very low. After the packet goes through all the paths, it will generate a distributed log to different log agents. And then all this log will get connected to a log center. And in that way, we can analyze the whole log in the same path. This is the JStorm reconstruction part. So how do we construct the path? So if we are using the network topology, you will find out in cloud scale overlay network, this topology is not possible to construct. It is changing all the time. Customer can deploy new network elements or deploy new resources at any time, so the topology just keeps changing. So you cannot use a fixed network topology to construct a path. The other way, we can use the packet ID and the time to sort to find out which packet is first, which packet is second. But the problem is that our servers are across the whole globe, so that the time is already out of sync. You cannot use the times to sort the packet and figure out which the path is. So how do we solve it? The way we are trying to solve it is that in the logs, we generate logs at both egress and the ingress and the egress point. At the ingress and the egress point, if the logs is generated in the same server, in the ingress egress, we can sort them by the same time, because the timestamp is generated by the same server. So hopefully in the same server, the timestamp will keep moving forward. They will not be out of sync. But when we want to know what's the order between A and the B, we use in the log we have the destination output information. That is when we send through the egress point, we'll say this packet will move to where, and when the node B receives the information, it will say, okay, I'm in B, I receive the packet. In this case, these two logs, we will sort them according to who they are and where this packet is going to, and sort them according to the out direction information and the current information, location information, to sort them according to these two parameters. In this case, we will find out, okay, B is after A and C is after B. And this way, we can keep doing the same thing for each packet, because every packet we have a packet ID, and we saw the packet, we saw logs according to the packet ID, and generate a different set of logs for each packet. We do this kind of sorting and find out the packet path. Okay, so after we implement this vtrace system, what's the impact on the following performance? We have a task setup with 10 tasks, vtrace tasks, and 100 target packet per task. So as you can see, if the packet size is larger than 256 bytes, the performance impact is almost minimum. It's around 1% impact to the performance, to the forwarding performance. But if the packet is very small, for example, is less than 128 bytes, the performance impact is up to 12%. So fortunately, in the business and in the custom business, most of the packet will be larger than 256 bytes. So in most cases, we don't see a trivial, we don't see an important, a big performance impact to the customer's business. But when it's necessary, we can do some performance. We can do the vtrace in a small packet size that will introduce around 12% impact to the forwarding performance. So when there is no vtrace, we have to manually check all the VFD hop by hop with TC dump and determine the network cost by network expert. But when we use vtrace here, it is automatically finding out all the paths. How does this packet goes? What is the path of this packet and why it gets dropped? So it does it in a few minutes, and it can scale up to millions of customers doing the thing at the same time. So that the performance is way better than the traditional way. So the last question is vtrace right now deployable? So as you can see, now right now vtrace is deployed over 220 months in Alibaba Cloud, and actually it has been heavily used here. And we have actually some interesting finding that actually most of the diagnosed requests are false positive, which means most of the problem actually is the customer doing some misconfiguration that causes a lot of problem. And the customer misconfiguration related to ACL and the rate limit, that consists of most of the packet loss reasons here. So this is the table that we have found, the type of costs we have gathered through the 20 months here. So most of the problem is non-VFD problems. A customer who doesn't know very expert knowledge about network, they do some bad configuration about the security policy, and they do some bad configuration about the routes. All these cases will cause some packet loss here. Okay, so the last, I will do some takeaway here to summarize the whole talk. So there are a lot of advances in vtrace. Actually, we have demonstrated a way to do the packet coloring, the matching and locking idea, and using a JStorm big data engine to do the packet reconstruction. And it's the first time we use a JStorm stream computing way to do a packet analyze and path analyze. And actually it's very practical. Right now we have already deployed in Alibaba Cloud for 20 months, and right now it's all across 30 large data centers, and has been used tens of hundreds of times here. And in the future, actually we are trying to do the vtrace to use vtrace to solve the transient packet drops, because right now we only solve the persistent packet drops problem. But in the future, we're trying to find out how to solve the transient packet drops, and that is a little difficult here. And the third thing is we are trying to solve the packet drops also in the physical network area. Okay, that's my talk. Thank you.
Okay, thanks for the nice talk. And is there any questions from the audience? You may raise your hand. Okay, I have a quick question. My question is that vtrace seems that is mainly designed for software routers. So can it be also be applied to hardware switches?
Right now, actually, we are already working with the hardware team to do the correlated analyze. In fact, the vTrace, it only needs some logs or data output from the devices. As long as the hardware sends out the logs or the data that meets our format, we can analyze in the same time. So the key analyze engine is the same. It just needs the log to be sent out.
Okay. Thanks. And so if there's no more questions, and we may discuss with the speaker offline. And that's all of this session. And this is also the ending of this year's Apnet. And Professor Kai-Chen, do you have any comment, or we may just end now?
Yeah. So yes, no, not too much to say, but we hope all the audience in the Zoom and online enjoyed this 2 days program. We indeed have a lot of very nice talk, very interesting talk. And after the conference, we will ask for the permission of all the speakers, and we will post their videos online if they agree. Okay, and we hope to see you face to face in our next year Apnet. Yeah, okay, that's the end.
Okay, thank you. Okay, see you.
Bye-bye.
Bye-bye.